Hey guys, good evening and welcome back again to your Unacademy Reading English channel. I hope all of you are doing great, having a good time. So people, quickly let me know in the chats if all of you can hear me, if I'm perfectly audible and visible to every one of you. Let me know quickly in the chats. Good evening everyone, good evening and welcome back. Good evening and welcome back. So let me know people in the chats quickly, if all of you can hear me, if I'm perfectly audible and visible to everyone. Yeah? Let me first of all check your chats. Not audible. Am I not audible? Can you quickly let me know in the chats quick? I think I am perfectly audible, yes? All right, people. All right. So I believe every single thing is perfect, yeah? So my dear students, as you all must be knowing, today we are going to start with one more amazing chapter of your chemistry, that is your ionic equilibrium, right? We are done with the chemical equilibrium in the last week, I believe, right? In the today's session, we are going to complete one more amazing chapter, interesting chapter, I must say, that is going to be your ionic equilibrium. Well, before starting the ionic equilibrium chapter, can you let me know in the chats how many of you are done with the chapter chemical equilibrium? Just let me know once in the chats quick. Let me know once in the chats quick. How many of you are done with the chapter chemical equilibrium? Let me know quick in the chats. Quickly, people, everyone. Quickly, let me know in the chats. Everyone. How many of you are done with the chapter chemical equilibrium? Just say yes or no in the chats. I just want to know that first. And accordingly, I'll start the chapter. Accordingly, I'll start the chapter. All right. All right. Perfect. Perfect, guys. Perfect. Perfect. Got it. Done. So, the ones who have studied this particular chapter before, or the ones who have not studied this particular chapter before, you need not to worry about anything. Okay? Every single thing will be started from the basics. Every single thing will be discussed from the scratch, right? Whether you have studied this particular chapter before or not, does not matter at all. We're starting all the things from the basics itself. It is just whatever things I'll be writing on the screen. I would want you guys to take a note of every single thing, because every single thing is going to be equally important in the today's session, right? Whatever theory can be asked in this particular chapter, whatever problem patterns can be asked in this particular chapter, all the things I'll be covering from the basics itself, right? It is just you need to be with me till the end. And I believe it's a small chapter, it's not a big chapter, right? I believe this particular chapter will be completing in like 6 to 7 hours maximum. Okay? Perfect? Exactly. The handwritten notes I'll be sharing on my Telegram. The ones who are not the part of Telegram, just be the part of it. The name of the Telegram channel is Wassim Bhat Chemistry Official, wherein I keep on sharing the handwritten PDFs. At the same time, I keep on sharing the DPPs of all the chapters which we complete here on this particular channel. Okay? So, today in 6 to 7 hours, we'll be completing this chapter. After that, I'll be sharing the handwritten PDF and the DPP of this particular chapter in my Telegram, right? So, be the part of it if you're not. Perfect. Best time to complete the syllabus. Best time to complete the syllabus is technically January end. January end is the best time to complete the syllabus. After that, the 3 months which you'll be having, those 3 months should be completely dedicated for the revision and the mock test and the extra problem practice. Okay? That is the ideal time to complete the syllabus when it comes to the NEET preparation. Okay? Yes, you can, if you are preparing for JE also, you can watch it. No issues at all. You can consult this lecture for JE mains as well. Not for advanced though, right? For mains, yes, it is super sufficient. All right, so let's get going then. Let's get started with the chapter Ionic Equilibrium. Before starting the chapter, the ones who have not liked the session yet, the ones who have not shared it, do smash the like right now, mark your attendance. Yeah. At the same time, do share this particular session with every single guy whosoever is preparing for NEET 2025 or even 2026 or even JEE mains examination. Do share this particular video with everyone who cannot afford the quality content, right? I think it's your moral responsibility to share this with every single such guy. Okay, and the ones who have not subscribed to the channel yet, I would highly recommend you guys to subscribe to this particular channel, which never compromises on any sort of content. Okay? Chalo, let's get going then. Let's get started with the chapter Ionic Equilibrium. And before starting the chapter, let me give you the table of the content. What all topics are there in this chapter, which we are going to cover in sequence in the today's session. Okay? So first of all, let me tell you the first topic that we shall be covering today. What is that? That is going to be the complete basics, which involves the electrolyte and its types. This is going to be the first topic, electrolyte and its types. This is the first topic which we shall be covering in the today's session, number one. Number two, my dear students, we shall be discussing about the degree of ionization. The degree of ionization is going to be our next topic. After that, we shall be discussing about the Ostwald's dilution law. Ostwald's dilution law. Well. Before Ostwald's dilution law, we shall be covering the ionization constant. We shall be covering the ionization constant of a weak electrolyte. Ionization constant of a weak electrolyte. After that, there is going to be one more topic, that is the dissociation constant. The dissociation constant of weak acids and weak bases. Dissociation constant of weak acids and weak bases. Right after that, we shall be moving into one of the important topics of this chapter, that is your common ion effect. And after discussing the common ion effect, we shall be talking about the ionic product of water. Ionic product of water. After discussing the ionic product of water, we'll straight away jump into the super important topic of this chapter, that is pH calculation. The most important topic, pH calculation. After discussing the pH calculation, we shall be discussing about Ka and Kb for a conjugate acid-base pair. For a conjugate acid-base pair. After this particular part, after this particular topic, we shall be discussing about one more important topic, that is your salt hydrolysis. And once we are done with the salt hydrolysis, after that, one more important topic that comes under this chapter, that is your buffer. In the buffer, we shall be discussing about buffer capacity as well. Buffer capacity. And then later on, we shall be discussing about the solubility and solubility product. Solubility and solubility product and its applications. And its application. The last topic of this particular chapter is going to be the simultaneous solubility. Well, this is going to be the flow of the today's session. This is going to be the flow of the today's session. Well, this particular session, again, I'm telling you, it's not a huge chapter, it's a small chapter only when it comes to your NEET examination, right? So we shall be covering this particular chapter in just, I believe, some 6 to 7 hours it will take to complete this particular chapter. So are you all ready for it? Let me know once in the chats. Let me know once in the chats, people. Are you all ready for it? Are you all ready? I would want you guys to let me know in the chats with some fire emojis quick. Are you all ready for it? I want the chats to flow continuously. Yeah? I want the chats to run. Then I shall be starting the session. Pradeep, in this particular chapter, you'll be expecting some 2 questions for sure. Okay? Some 2 questions. But this particular chapter is needed if you want your electrochemistry, your kinetics to be very, very, very strong. Then this chapter plays a role there also. Okay? And our next chapter, after ionic equilibrium, our next chapter is going to be your general organic chemistry, GOC. I think that session is already public. You would have seen the thumbnail, I believe. Yeah? Yes, Alvin, you can consult it for JEE Mains as well. No issues. Perfect. So should we get starting then? Should we get started? I believe yes, we should get started now. My dear students, the first and the basic topic with which I shall be starting this particular chapter, what is it? It is going to be electrolyte. In this chapter, we shall be discussing, we shall be dealing only and only with the electrolytes. Okay? This particular chapter is all about the electrolytes. Now, first of all, how do we define the term electrolyte? What is meant by the term electrolyte? My dear students, if you look at the definition, those substances which on dissolving in water, dissociates means breaks down. Those substances which on dissolving in water breaks down into their ions. Those substances which are dissolving in water dissociates, breaks down into their ions. You'll be calling those substances as electrolytes. Okay? You would have seen a lot of substances which on dissolving in water, they break down into their ions. They dissociate into their ions. And you shall be simply calling those substances as the electrolytes. For example, let's say I've got a substance AB. Let's say I'm taking a general substance AB. My dear students, when I introduce this substance into water, if this particular substance, if it breaks down into its ions, and its ions are going to be A positive and B negative. If this particular substance in water breaks down into its ions, then I'll be calling this particular substance as an electrolyte. This particular substance I'll be calling as an electrolyte. For example, all of you must have heard about HCl, right? HCl, which is a very strong acid, correct? And yes, students, when you introduce HCl into water, what happens? This HCl, upon introducing in water, it dissociates into its ions. And its ions are simply going to be H positive and Cl negatives. And that particular substance, which on dissolving in water, dissociates into its ions, you'll be calling it an electrolyte, right? For example, you are taking NaOH, which is the example of a strong base, right? My dear students, it's very much simple. When you introduce this NaOH in water, it dissociates, it breaks down into its ions. And its ions are going to be Na positive aqueous plus OH negative aqueous. So this is again what I'll be calling as, this NaOH, again what I'll be calling as the electrolyte, right? So what are electrolytes in general? I would say electrolytes are the substances which on dissolving in water breaks down into their ions. Okay? Which on dissolving in water breaks down into their ions. Now, these electrolytes, they are classified into 2 categories. We have got 2 categories of electrolytes. One is what you call a strong electrolyte, and another one, that's what you call as weak electrolyte. There's a very small difference between the two. Strong electrolyte and weak electrolyte. What is a strong electrolyte? My dear students, strong electrolyte is the one which on dissolving in water undergoes 100% ionization. that particular substance which on dissolving in water breaks down completely into its ions, gets 100% ionized. That electrolyte is what you call as the strong electrolyte. Okay? So first of all, what is the strong electrolyte? That particular substance which on dissolving in water breaks down completely into its ions, gets 100% ionized. That's what you'll be calling a strong electrolyte. Number one. Number two. My dear students, I believe you must be remembering the term that is discussed in chemical equilibrium, alpha. Alpha we used to call as degree of dissociation. But here, the same alpha, we won't be calling it as degree of dissociation. We shall be calling it as degree of ionization. Okay? Alpha over here in this particular chapter, I shall be calling it as degree of ionization. Okay? And my dear students, degree of ionization alpha, it is always equal to the percentage ionization of an electrolyte divided by 100. Alpha is always equal to percentage ionization of an electrolyte divided by 100. Now, my dear students, just use your brain a bit. Strong electrolyte, its percentage ionization is 100%. It gets 100% ionized in water. So, in case of strong electrolyte, if I ask you, what should be the value of alpha? In case of strong electrolyte, the value of alpha should be equal to percentage ionization. How much is that for strong electrolyte? Strong electrolyte gets 100% dissociated, ionized. Divided by what? Divided by 100. The value of alpha for a strong electrolyte always is equal to 1. So, if I talk about the strong electrolyte, in case of the strong electrolyte, the degree of ionization alpha is equal to what? Is equal to 1. Right? This is one more point which you are going to remember about strong electrolytes. Now, my dear students, what are the examples of strong electrolytes? That is one more point. What are the examples of the strong electrolytes? Let me tell you, all the strong acids, all the strong bases, all the strong bases, and all the water-soluble salts, they are the examples of strong electrolytes. All the strong acids, strong bases, as well as the water-soluble salts, they are the examples of the strong electrolytes. For example, do you know any strong acid? I believe yes. HCl, it's a strong acid, right? HCl, it's a strong acid. H2SO4, it's a strong acid. HClO4, it's a strong acid, right? All the strong acids, they are the examples of strong electrolytes. And if these strong acids are the examples of strong electrolytes, that means when you introduce these strong acids in water, they dissociate 100% into their ions. They get 100% ionized. They get 100% converted into their ions on introducing into water. Similarly, what are the examples of strong bases? NaOH, every one of you would be knowing. It is the example of strong base, right? NaOH. For example, cesium hydroxide, CSOH. It is the example of a strong base, right? KOH is the example of strong base. Barium hydroxide, BaOH whole twice. This is also the example of what? This is also the example of the strong base. And all the strong bases again are the examples of what? All the strong bases again are the examples of strong electrolytes. That means when you put them into water, they get 100% ionized, they get 100% dissociated into their ions. Yes? Right, people? Similarly, all the water-soluble salts, those salts which are soluble in water, right? Those salts which are soluble in water. For example, if you take general salts of alkali metals, for example, if you take NaCl, NaCl is a salt of alkali metal, sodium, right? It's a general salt of alkali metal. General salts of alkali metals, they are considered to be water soluble. And if they are water soluble, that means they are going to behave like the strong electrolytes. Okay. Now, similarly, remember one more thing. Whenever you see a salt of NH4 positive, whenever you see any salt of NH4 positive, or whenever you see any salt of NO3 negative, salts of NH4 positive and the salts of NO3 negative, they are also considered to be water soluble. They are also considered to be water soluble. And all the water soluble salts, they are what? They are your strong electrolytes. That means when you put them in water, they are going to dissociate into their ions completely. I believe this is clear to everyone. Okay? So these are some of the points which you need to remember about strong electrolytes. Strong electrolytes are the ones which are 100% ionized in their aqueous solution. Their degree of ionization exactly is 1. All the strong acids, all the strong bases, all the water-soluble salts, they are the examples of strong electrolytes, which when dissolving in water, breaks down completely into their ions. Okay? Right? Yeah, ye live hai. Yes, it's a live session. I believe this is super clear to everyone. And all these things I've mentioned over here as well. When I talk about strong electrolytes, they are completely ionized in their aqueous solution. All strong acids, strong bases, water-soluble salts are the strong electrolytes. General salts of alkali metals, salt of NH4 positive, salt of NO3 negatives, they are considered to be water soluble. Okay, and if they are water soluble, they are definitely going to get 100% ionized. Okay, so for example, guys, if I'm taking H2SO4, what is it? It is a strong acid. It is a strong acid. If it is a strong acid, it is the example of a strong electrolyte. And when it is introduced in water, it gets 100% converted into its ions. And its ions are going to be 2 times H positive aqueous. And with this, you are going to write SO4 di-negative aqueous. Right? If I ask you what is going to be its alpha value, you'll directly say its alpha value is going to be 1. Perfect. Now, for example, you have got barium hydroxide, BaOH whole twice. It is a strong base. If it is a strong base, it is again going to be the example of a strong electrolyte. And if it is the example of strong electrolyte, you know, when you introduce this in water, it is going to get 100% ionized into its ions. Ions are going to be barium di-positive aqueous plus 2 times OH negative aqueous. If you ask me what is going to be its alpha value again is going to be 1. Okay? Right? Clear, guys? For example, if I take NH4Cl, perfect, NH4Cl, in case of NH4Cl, you have got NH4 positive and Cl negative, right? So NH4Cl is basically a salt of what? It is a salt of NH4 positive. And salts of NH4 positives, they are water soluble. Salts of NH4 positives, they are water soluble. If it is water soluble salt, that means it is the example of strong electrolyte again. And if it is the example of strong electrolyte, on introducing in water, it is 100% going to get ionized into its ions, which are NH4 positives and Cl negatives. And if I ask you, what is going to be its degree of ionization? It's again going to be 1 only. Yes? Similarly, guys, let's say I've got NaNO3. Let's say I've got NaNO3. Look at the ions first of all. Na positive, NO3 negative. This is again the salt of NO3 negative. It is the salt of NO3 negative. And I told you a few minutes back, salts of NH4 positive and the salts of NO3 negative, they are water soluble. And if they are water soluble, they are going to behave like the strong electrolytes. That means on introducing them in water, they are going to get 100% ionized. They are going to get 100% converted into its ions. And its ions are Na positive aqueous plus NO3 negative aqueous. If I ask you what is its degree of ionization alpha, it's again going to be 1 only. I believe this is something which is clear to every one of you. So this was all about the strong electrolytes, right? Now guys, there is one more important thing. Since I told you, a strong electrolyte, it gets 100% ionized. It gets 100% converted into its ions, right? When the strong electrolyte gets 100% converted into its ions, can a strong electrolyte remain in equilibrium with its ions? I would need answer from you. I would need the answer from you. If a strong electrolyte, if it gets 100% converted into its ions in water, so can a strong electrolyte remain in equilibrium with its ions? No, the answer is no. Strong electrolyte in the aqueous solution does not remain in equilibrium with its ions. Why is that? Because for equilibrium, there should be forward reaction as well as backward reaction. For equilibrium, there should be forward reaction as well as backward reaction. Since the strong electrolyte, it gets 100% converted into its ions. When the strong electrolyte gets 100% converted into its ions, after that, there'll be no strong electrolyte left. All that is converted into its ions. So, if there is no strong electrolyte left, what does that mean? There'll be no forward reaction. Okay? After some time, there'll be no forward reaction. These are irreversible reactions, I would say. Right? Perfect. So, strong electrolyte in aqueous solution does not remain in equilibrium with its ions. Remember this particular point as well. Now, if I talk about the weak electrolytes, now, weak electrolyte. Now, you can easily understand what is a weak electrolyte. My dear students, weak electrolyte, it gets partially ionized in its aqueous solution. When you introduce a weak electrolyte in water, it does not get 100% dissociated. It does not get 100% ionized. It gets partially ionized. So first point, your weak electrolytes, they are partially ionized in their aqueous solution. Number one. Number two. What are the examples of the weak electrolytes? My dear students, all the weak acids, just a second. All the weak acids, all the weak bases, right? They are the examples of the weak electrolytes. So they do not get 100% ionized. They get partially ionized. In their aqueous solution. All the weak acids, all the weak bases, they are considered to be weak electrolytes. Okay. For example, you have got CH3COH. It's a weak acid. For example, you have got formic acid, HCOH. It's a weak acid, right? Similarly, you have got NH4OH. It's a weak base. And let me tell you, all the weak acids, all the weak bases, they are the perfect examples of what? Weak electrolytes. And weak electrolytes, they get partially ionized. For example, have a look. See guys, if you have got the electrolyte AB, let's say you have got the electrolyte AB. I'm assuming this electrolyte as a weak electrolyte. If it is a weak electrolyte, it is not going to get 100% ionized in its aqueous solution. But when you introduce this weak electrolyte in water, it is not going to get 100% ionized. It is going to get partially ionized. That means some percentage of this electrolyte, will get converted into its ions. But not all the weak electrolyte is going to get converted into its ions. Only a small percentage of it is going to get converted into its ions, right? And remember, a weak electrolyte, it always remains in equilibrium with its ions. Its ions are A positive and B negative. Okay? For example, you have got CH3COOH. It is the example of a weak acid. So, it is a perfect example of a weak electrolyte. If it is the example of the weak electrolyte, when you introduce it in water, it is not going to get 100% ionized. Only a small percentage of it will ionize in water. Only a small percentage of it will get converted into its ions in water. And this weak acid is going to remain in equilibrium with its ions. Its ions are CH3CO negative. With this, you have got H positive, right? Similarly, for example, you have got NH4OH. It is again the example of a weak base. Weak base means weak electrolyte. If it is a weak electrolyte, it is going to remain in equilibrium with its ions, and its ions are NH4 positive aqueous. With it, you'll be writing OH negative aqueous. Okay. Now, people, understand what I'm going to say. Understand what I'm going to say. Understand what I'm going to say. See, if I talk about degree of ionization of a weak electrolyte, alpha. What is alpha all about? Alpha means percentage of the electrolyte ionized divided by 100. Okay. Since it's a weak electrolyte, so only a small percentage of it is going to get ionized in water. And after that, for example, let's say when 3%, let's say when 3% of the weak electrolyte in water got ionized, right after that, equilibrium got established between the electrolyte and its ions. So right now, if I ask you, what is going to be the value of alpha for this weak electrolyte? It is going to be 3 divided by 100. 3 divided by 100, that means 0.03. So its alpha here is 0.03. Let's assume we have taken this weak acid. For example, when you introduce this weak acid in water, let's say when this weak electrolyte got 1% ionized. When this weak electrolyte got 1% ionized, right after that, equilibrium got established between the weak electrolyte and its ions. So its alpha here is going to be 0.01, right? So my dear students, what I want to convey here, what I want you guys to remember here, what is that exactly? Remember the value of alpha, the value of degree of ionization for a weak electrolyte. It is always greater than 0, less than 1, right? It is valid for what? It is valid for a weak electrolyte. Remember this particular point as well. Okay? Remember this particular point as well. There is one more example of a weak electrolyte. What is that? All the sparingly soluble salts. What are sparingly soluble salts? We have to study them in detail afterwards in this chapter only. Right now, you can remember it like this. Sparingly soluble salt is the one whose solubility in water is very, 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 very low. Sparingly soluble salt is the one whose solubility is very low. How much exactly? That will be discussed afterwards. Okay. What are the examples of the sparingly soluble salts? Remember these examples. Generally AgCl, PbCl2, mercurous chloride, Ag2SO4. These are the examples of sparingly soluble salts whose solubility is very, very, very less, right? And all the sparingly soluble salts, they are also considered to be weak electrolytes. And if they are weak electrolytes, that means in water, they are going to remain in equilibrium with its ions, right? They are going to remain in equilibrium with their ions. I believe I'm clear with what is a strong electrolyte and what is a weak electrolyte. Can you let me know in the chats quickly if you got the idea of what is a strong and what is a weak electrolyte? Everybody in the chats. Everybody in the chats. Quick. This was the quick introduction. This was a quick introduction of electrolyte and the types of electrolyte. Yeah? Okay, guys? Thank you, Ria. Perfect, people. Now. Let's get going. Let's get started with the first topic of our chapter. Right now, I was just talking about some basic things. Right? Okay? Right now, I was just talking about the basic things. Now, we are going to straight away go into our first topic. Right? Guys, remember one important thing which I told you already. Weak electrolyte in its aqueous solution. Weak electrolyte in the aqueous solution always remains in equilibrium with its ions. Or if you want me to write this point, I'm going to write it for you. Remember, weak electrolyte in its aqueous solution is always going to remain in equilibrium with its ions. Remember this particular point. Weak electrolyte in its aqueous solution, it's going to remain in equilibrium with its ions. Because in this chapter, everywhere I'll be using this particular term. Yeah? Now, straight away, let's get going. Let's get started with the first topic. What is that? That is the ionization constant of a weak electrolyte. ionization constant of a weak electrolyte. First of all, my dear students, ionization constant of a weak electrolyte, I will be representing with Ki. Ionization constant of a weak electrolyte, I'll be representing by Ki. Now understand. Imagine that I have got a weak electrolyte AB. Imagine that I have got a weak electrolyte AB. This AB is a weak electrolyte which I'm taking into consideration. Okay, this AB is a weak electrolyte. Now people, when you introduce this weak electrolyte in water, it will partially ionize, right? Only a small percentage of it will get converted into its ions. When you introduce this in water, when you introduce AB in water, only a small percentage of it will get converted into its ions. And then the remaining electrolyte and its ions, they are going to remain in equilibrium with each other. So when this AB aqueous, when you introduce this in water, it will get converted into their ions. Ions are A positive aqueous and B negative aqueous. These are its ions. Okay. My dear students, for example, if I write time t is equal to 0, at time t is equal to 0, initially, let's assume the concentration of weak electrolyte was C molar. Let's assume the concentration of this weak electrolyte was C molar, right? Let's assume it was C molar. In chemical equilibrium, did we used to start with concentration directly, or we used to start with moles? If you remember, we used to start with moles. A0, 0. Then A minus A alpha, A alpha, A alpha. That's what we used to do in chemical part. We used to start with moles, A0, 0. Then at equilibrium, it used to be A minus A alpha, A alpha, A alpha. Here, my dear students, you are not going to start with moles. You'll be starting with the concentration directly. Right? And let me tell you, whatever treatment we used to do with the moles in the chemical equilibrium, whatever treatment we used to do with the moles, same treatment we are going to do with the concentration. Okay? So I'm writing it over here. Treat concentration in the similar way as moles are treated. Treat concentration in the similar way as moles are treated. Now understand. Initially at time t is equal to 0, the concentration of weak electrolyte was C molar, right? So this would have been 0, this would have been 0. Why? Because I'm writing time t is equal to 0. This reaction has not started yet. Now, my dear students, when this weak electrolyte, whose concentration we have C molar, when it's introduced in water, a small percentage of weak electrolyte gets converted into its ions, right? And the remaining weak electrolyte and its ions, then they are going to remain in equilibrium with their ions, right? So I would say at equilibrium, let's assume degree of ionization is alpha. So I would say at equilibrium, the concentration of electrolyte left is going to be from C molar. How much gets converted into its ions? From C alpha would get converted. So how much concentration of this weak electrolyte would be left in the container at equilibrium? It will be simply C minus C alpha. Like we used to do with the moles, A0, 0, then A minus A alpha. Here I'm going to start with concentration, right? So at equilibrium, the concentration of weak electrolyte left in the container is going to be C minus C alpha, right? Now, 1 mole of AB gives 1 mole of A positive. So C alpha is going to give us C alpha. Here also it's going to be C alpha. So if I ask you what are these terms? Are these moles? No. These are basically the concentrations. These are the concentrations of AB, of A positive and B negative present in the solution when equilibrium is established between them, right? These are the concentrations. Perfect. And my dear students, you already know when equilibrium is established here, at equilibrium, once equilibrium is established, after that, the concentrations of reactants products, they are not going to change. So I would say these are the final concentrations of reactants products in the container, right? These are the final concentrations. They are not going to change because now the rate of forward and backward reaction has become equal. So concentrations of reactant products, now they are not going to change because equilibrium is established. Right? Now, people, just tell me one thing. Just tell me one thing. In chemical equilibrium, what we used to call this Kc as? In chemical equilibrium, what we used to call this Kc as? We used to call it as the equilibrium constant. Right? My dear students, here, Kc would be called as Ki. Nothing more than that. Kc would be represented with Ki. And this Ki would be called as ionization constant. It would be called as the ionization constant of a weak electrolyte. Right? Actually, what is this Ki? This Ki is nothing but it is Kc only. It is Kc only. Right? But here, it is just the terminology is different, meaning is same. Terminology is different, meaning is same. Now, my dear students, how do we write the expression for Kc for this particular reaction? It's going to be concentration of A positive in the container at equilibrium raised by stoichiometric coefficient 1. Concentration of B negative in the container at equilibrium raised by stoichiometric coefficient 1 divided by concentration of AB at equilibrium raised by stoichiometric coefficient 1. Okay. So, Ki has to be equal. What is the concentration of A positive in the container at equilibrium? You will say it is C alpha. C alpha multiplied by B negative concentration, again C alpha, divided by AB concentration at equilibrium, which is C minus C alpha. Okay? C minus C alpha. Now, my dear students, after this, if you elaborate this a bit, right? This becomes C square. Here you can take C common. So one of the C gets cancelled out. So I'll be left with C alpha square divided by 1 minus alpha. So you have to remember this expression for now, right? From now on, you are going to remember this expression of ionization constant, which is C alpha square divided by 1 minus alpha. This is how you write the ionization constant of that weak electrolyte which dissociates under the stoichiometry 1:1. Which dissociates under the stoichiometry 1:1. Okay? So Ki is always equal to C alpha square divided by 1 minus alpha. When the electrolyte dissociates under the stoichiometry 1:1:1. Yeah? Now, my dear students, after this Ki expression, we are going to make certain assumptions. Remember and understand all these things, what I'm going to say. My dear students, after writing the Ki expression, we are going to make certain assumptions. And what are those assumptions? What are those assumptions? I'll assume let alpha value is less than 0.05. I'm assuming alpha of this weak electrolyte to be less than 0.05. What does that mean? What does that mean? That means I'm assuming this weak electrolyte, this weak electrolyte, it has partially ionized. How much it has ionized? Less than 5% it has ionized in water. Less than 5%, I'm assuming this weak electrolyte, less than 5% it has got ionized in water, and right after that, equilibrium has been established. So I'm assuming let alpha value is less than 0.05. So what does that mean? That means I'm assuming the percentage ionization of this weak electrolyte in water as less than 5%. Less than 5%. Since I'm assuming alpha value to be very less than 0.05, at this particular point of time, when alpha is less than 0.05, can I say instead of 1 minus alpha, I can only write 1? Because alpha is very small. So alpha I'm neglecting in comparison to 1. So instead of 1 minus alpha, I'm just writing 1. So if instead of 1 minus alpha, I'm just writing 1, so can I write this expression again now? This expression is going to be Ki is equal to just C alpha square. It used to be divided by 1 minus alpha. Now we are assuming alpha is less than 0.05. So instead of 1 minus alpha, we're only writing 1. So my dear students, here you can calculate the alpha value, which comes out to be under root of Ki divided by C. You can calculate the alpha value, which comes out to be under root of Ki divided by C. This alpha value, it is equal to under root of Ki by C. But understand and remember one thing. Since I assumed alpha to be less than 0.05, and here I got the value of alpha as under root of Ki by C. My dear students, if I give you the value of Ki for the weak electrolyte, if I give you the value of C, if I give you the value of Ki, if I give you the value of C, can you calculate the actual value of alpha? Yes, from here you can calculate the value of alpha. If you know the value of Ki, if you know the value of C, by putting the values, you can get the value of alpha. Now, there are two possibilities which arise here. The alpha which you get from here, if the value of alpha comes out to be actually less than 0.05, that means at that point of time, our assumption is right. Whatever things we have assumed, they are absolutely right. But if alpha comes out to be greater than 0.05 by this particular expression, that means we cannot neglect alpha in comparison to 1 at that point of time. Okay? Remember these 2 points. They are very important. See, here I assumed let alpha is less than 0.05. At that point of time, I can say instead of 1 minus alpha, just write 1. So alpha comes out to be under root of ki by c. If you know the value of ki, if you know the value of c, you can get the value of alpha. Now, if alpha actually comes out to be less than 0.05, that means at that point of time, our assumption is right. And if alpha comes out to be greater than 0.05, it's greater than 0.05, at that point of time, whatever things we have assumed, they are not right, they are wrong. So you cannot neglect alpha in comparison to 1 at that point of time when alpha comes out to be greater than 0.05 from this equation. Okay? Am I clear with this? Am I clear with this? Am I clear with this, people? Now you must be thinking, what exactly am I telling? Alpha, this, less, more. This is something which you'll understand only when we'll solve one question. This is something which you'll understand properly when we'll be solving one question. Have a look. Have a look, guys. Calculate the concentration of each ion. Calculate the concentration of each ion at equilibrium. Calculate the concentration of each ion at equilibrium for a 0.1 molar solution of a weak electrolyte AB. If Ki is equal to this, if Ki is equal to this. So these are two questions. This will make your concept of ionization constant very strong. So understand what exactly I'm going to say. As far as this particular question is concerned, which electrolyte are we taking? We are taking the electrolyte AB. Right? And as per the question, they have mentioned that the electrolyte is weak. If it is a weak electrolyte, that means when you introduce this in water, it is going to remain in equilibrium with its ions. Ions are going to be A positive aqueous, B negative aqueous. Right? So my dear students, if I ask you, initially at time t is equal to 0, what is the concentration of the electrolyte which we are taking? Concentration of electrolyte is 0.1 molar. All right. So initially this will be 0, this will be 0. Let's assume degree of ionization is alpha. So I would say at equilibrium, this is supposed to be C minus C alpha. This is supposed to be C alpha, and this is supposed to be C alpha. Right? Now after this, since the stoichiometry is 1 is to 1 is to 1, right? So if I want to write the expression for Ki, you know, Ki expression is going to be C alpha squared divided by 1 minus alpha. Right? Now, my dear students, let the value of alpha be less than 0.05 at this particular point of time. Instead of 1 minus alpha, I'll just write 1. Instead of 1 minus alpha, I'll just write 1. And if instead of 1 minus alpha, we are writing just 1, so our Ki value comes out to be simply C alpha square. And from here, I can calculate the value of alpha, which is going to be under root of Ki by C. Right? Now, in the first question, my dear students, is the value of Ki given? Yes, 10 raised power minus 5. What is the value of C? Concentration. C is 0.1, so 10 raised power minus 1. So alpha value here comes out to be root of 10 raised power minus 4, which is going to be 0.01. Have a look at this particular alpha value. Have a look at this particular alpha value. It is coming out to be less than 0.05. It is coming out to be less than 0.05. That means what our assumption we have made over here. What assumption we made? We made alpha value. We assumed alpha to be very less. That's why instead of 1 minus alpha, we just wrote 1. And alpha later on is coming out to be actually less than 0.05. Right? So whatever assumption we have made here, that's absolutely correct. And my dear students, since you got the value of alpha, what am I supposed to calculate? I'm supposed to calculate the concentration of each ion in the final solution. Which all ions are present in the solution? In the solution, A positive is present. In the solution, B negative is present. And the concentration of these ions is equal to what? Concentration of these ions is equal to C alpha, right? So I can say concentration of A positive and concentration of B negative in the final solution when weak electrolyte is in equilibrium with its ions. Both are equal to C alpha. The value of C is how much? The value of C is 10 raised power minus 1. The value of alpha is 0.01, means 10 raised power minus 2. The value comes out to be 10 raised power minus 3 molar. So this is going to be the concentration of A positive and B negative in the final solution, people. I believe I'm clear to everyone. And this is something which we were supposed to calculate in the first question. This is something which we were supposed to calculate in the first question, right? Now, let's try to solve the second part of it. Second part of it will make things a little more clear. Second part of this particular question will make things more clear. Okay? Now, what is the second part? What is the second part? Second part is saying that assume Ki to be equal 10 raised power minus 2. Assume Ki to be equal 10 raised power minus 2. So what do I do now? What do I do now? Understand. See guys, in the second question, this is same, Ki value has to be C alpha square divided by 1 minus alpha. Now I'm assuming let alpha to be less than 0.05. 1 minus alpha has to be 1. So alpha has to be equal to under root of Ki by C, right? So in the second question, let's calculate alpha. In the second question, alpha has to be equal to under root of Ki by C. Now, if I ask you what is Ki value given? 10 raised power minus 2. What is the C value given? C value is 10 raised power minus 1. So the value is under root of 10 raised power minus 1, which is 1 by root 10. Root 10 is almost 3 point something. So it will be 0.3. It will be 0.3. So alpha from this expression is not coming out to be less than 0.05. Alpha from this expression is not coming out to be less than 0.05. So that means whatever assumption we have made here, that's wrong. We cannot neglect alpha in comparison to 1. We cannot neglect alpha in comparison to 1. So what do we do now? What do we do? We'll be writing the entire expression of Ki. C alpha square divided by 1 minus alpha. We are not going to neglect the denominator right now because we got to know alpha is not less than 0.05. So we are not going to neglect the denominator. What am I supposed to calculate? Concentration of each ion at equilibrium. Concentration of each ion at equilibrium. Understand. Now, as per the second question, Ki values 10 raised power minus 2 is equal. C values 10 raised power minus 1. Alpha square. Divided by what? Divided by 1 minus alpha. Okay. So 10 raised power minus 1, 10 raised power minus 1 cancel. So in the left side, I'll be getting 1 by 10. 1 by 10 is equal to alpha square divided by 1 minus alpha. So here I'll be getting a quadratic equation. 10 alpha square is equal to 1 minus alpha, or I can say 10 alpha square plus alpha minus 1 is equal to 0. Do you understand what's happening, guys? So look here. When alpha is not less than 0.05, at that point of time, we get a quadratic equation. And now we'll have to solve this quadratic equation. Now we'll have to solve this quadratic equation. And how you're going to solve this quadratic equation? Quadratic formula, minus b plus minus root of b square minus 4ac divided by 2a. After solving this quadratic equation, you'll be getting the actual value of alpha. After solving the quadratic equation, you'll be getting the actual value of alpha. And once you get the actual value of alpha, after that you will write concentration of A positive, B negative in the solution is equal to C alpha. Alpha you would have calculated from here. P value is given to us in the question 0.1. So you would be getting the concentration of each ion in the container. Do you understand? Do you understand the gravity of the situation, guys? Yeah? Do you understand this stuff? Do you understand why am I making these assumptions, etc., etc.? Right? Say it in the chats. Say it in the chats, everybody. Say it in the chats, everybody. This is super important, I must say. I hope you got the idea what this assumption, etc. I'm doing, right? And how we deal with it. Say it in the chats quickly. Then I'll be going ahead. Do you find it interesting now? Yeah, right? Perfect, amazing. Let's move on then. Let's move on. Now, my dear students, there is one more thing. What is that? That is ionization constant, or you can call it as the dissociation constant. Ionization constant, or you can call it as the dissociation constant. Ionization constant or the dissociation constant of a weak acid and a weak base. weak acid and a weak base. Okay. I think I won't be getting a lot of space here. So let me just do one thing. Let me take a separate page here, a blank space. See guys, till now I was taking a weak electrolyte in general as AB. I was taking a weak electrolyte as AB, right? I was taking weak electrolyte as AB. Now, particularly what am I doing? I'm going to take the weak electrolyte in particular as a weak acid. Now I am taking weak acid as the weak electrolyte. Till now I was talking in general terms, weak electrolyte, AB. Now, I know weak acids are the examples of the weak electrolytes. So now I'm taking weak electrolyte as a weak acid. For example, I'm taking HA. This HA is a weak acid. If it is a weak acid, when you put it into water, it's going to remain in equilibrium with its ions. Its ions are H positive aqueous and A negative aqueous. These are its ions. These are its ions, right? Now, my dear students, let's say initially its concentration is C. This is 0, this is 0. Degree of ionization alpha. So this is C minus C alpha. This is C alpha. This is C alpha, right? Till now, for the weak electrolyte, I was using the term Ki, ionization constant. This was the general term which was used for the weak electrolyte. But remember, when the weak electrolyte is particularly the weak acid, then Ki is replaced by the term Ka. And this Ka I would be calling as the dissociation constant, or you can call it as the ionization constant of what? Of a weak acid. Now, its expression is written in a similar way. Ka expression is going to be concentration of H positive in the container at equilibrium raised power stoichiometric coefficient, concentration of A negative at equilibrium raised power 1 divided by concentration of HA at equilibrium raised power 1. Now, my dear students, if I ask you, what would be the value of Ka? This particular term, it is C alpha. This particular term, it's again C alpha. This particular term, it's C minus C alpha. So, final expression is going to be C alpha square divided by 1 minus alpha here also. This is the expression. Now, after this, what do we do? After this, what do we do, people? Tell me, what do we do? Now, we'll be assuming certain things. Let the value of alpha be less than 0.05. At that point of time, instead of 1 minus alpha, I'll just write 1. And when instead of 1 minus alpha, I'm just writing 1. So, Ka then becomes equal to C alpha square. And your alpha comes out to be under root of Ka divided by C. Right? But this alpha is valid when this is the value of alpha when alpha is equal. This is the formula which we get when we assume alpha to be less than 0.05. Okay. Now here understand one simple thing. One simple thing I want you guys to understand. What is that? My dear students, if you see Ka and alpha, are they directly related or inversely? They are directly proportional, right? So I must say, more the value of Ka, more the value of dissociation constant of the weak acid. More the value of dissociation constant of the weak acid. More the value of Ka. More the value of Ka means more is going to be the value of alpha. Right? What is meant by more value of alpha? Alpha value is more. What does that mean? That means degree of ionization is more. That means percentage ionization of the electrolyte is more. That means this electrolyte, if its Ka is more, its alpha has to be more. If its alpha is more, that means its percentage ionization is more. That means this weak electrolyte has got more converted into its ions. And if this weak electrolyte, if this weak acid has got converted more into its ions, what would be the concentration of H positive in the container? Would the concentration of H positive in the container be more or less? I would say concentration of H positive in the final solution would be more. And my dear students, you know it. If the concentration of H positive in the solution is more, what does that mean? That means the strength of the acid. The strength of acid has to be more, right? Strength of acid depends on the H positive ions present in the solution. More the H positives generated from the acid, more is going to be the strength of the acid, right? So, strength of acid is going to be more. So, can I say this Ka and strength of the acid is directly proportional to the dissociation constant of the weak acid, right? Dissociation constant of the weak acid. correct? And my dear students, in organic chemistry, in organic chemistry, you would have seen this particular term, pKa. What is pKa? What is pKa? P stands for, P is just a mathematical operator. P stands for minus log, so minus log of Ka. pKa means minus log of Ka. If Ka value is more, if Ka value is more, if Ka value is more, mathematically I would say, then log of Ka value becomes more. If log Ka becomes more, there's a minus sign here. So this whole term with the minus, it will be less. If this term is less, that means pK would be less. So remember, it's inversely proportional to what? P of Ka. It is inversely proportional to P of Ka, right? So sometimes they'll ask you the question related to acidic strength. Sometimes they'll ask you a question related to Ka. Sometimes they'll ask you a question related to P of Ka. And I believe this is super clear to everyone, right? So this was the dissociation constant of the weak acid. Okay. Now we are going to discuss the dissociation constant of the weak base. Dissociation constant of a weak base. Understand, guys. Let's say the weak electrolyte which I'm taking now, let's say that is BOH. Let's say this is a weak base. Imagine this is a weak base. If it is a weak base, that means it's a weak electrolyte. If it is a weak electrolyte, in aqueous solution, it is going to remain in equilibrium with its ions. Ions are B positive aqueous and OH negative aqueous. Right? Let's say at time t is equal to 0, its concentration is C. This is 0, this is 0. Degree of ionization alpha. So at equilibrium, what do you suggest? This is going to be C minus C alpha. This will be C alpha. This will be C alpha. Correct? This is something which we already know. Now people, tell me just one thing. Since it's a weak electrolyte basically. For the weak electrolytes, what do we define? Ionization constant, Ki. But this Ki, right now, when the weak electrolyte is a weak base, when the weak electrolyte is a weak base, Ki is replaced by the term Kb. Just the terminology is different. Rest the meaning is same. So Kb here would be called as the dissociation constant, or you can say ionization constant of a weak base. What do you think will be its expression? Its expression is going to be same. See, 1:1:1 stoichiometry. So expression is going to be same. What is it? C alpha square divided by 1 minus alpha. C alpha square divided by 1 minus alpha. Now after this, what do we do? You know it. Let the value of alpha be less than 0.05. Therefore, instead of 1 minus alpha, I'll just write 1. If instead of 1 minus alpha, I'm just writing 1. If instead of 1 minus alpha, I'm just writing 1. So Kb is reduced to what? Kb becomes equal to just C alpha square, or I would say alpha becomes equal to under root of Kb divided by C. Alpha becomes equal to under root of Kb divided by C. Right? Now people, tell me one thing. Alpha and Kb, directly or inversely, directly. Can I say more the value of Kb of a base, more the value of dissociation constant of a weak base, more will be the value of alpha? More will be the value of alpha. If more is the value of alpha, that means more is the degree of ionization of the weak electrolyte. More is the degree of ionization of this weak base. What does that mean? That means more is the percentage ionization of the weak base. That means this weak base has got ionized more. If Kb value is more, alpha is more, degree of ionization is more. What does that mean? That means percentage ionization of this weak electrolyte is more. That means this weak electrolyte has got converted more into its ions, due to which concentration of OH negatives in the solution, would it be more or less? Concentration of OH negatives in the final solution would be more. Yeah? Right, people? So, if the concentration of OH negative in the final solution is more, what does that mean? That means strength of the base, strength of the base is going to be more. Strength of the base is going to be more. So, my dear students, you can have a look. More the value of Kb, more the value of dissociation constant of the weak base, more is going to be the strength of the base. More is going to be the strength of the base. So, I would say simply like this. Strength of the base is directly proportional to the value of Kb for the base. More the value of Kb for the base, stronger is going to be the base, right? And if Kb is more, that means pKb has to be less. What would be pKb here? pKb here will be minus log of Kb. Am I clear with all this stuff? Am I clear with all this stuff, people? Am I clear with all this stuff? Quickly. Am I clear with all this stuff? Quick, everybody in the chats. Everybody in the chats. Quick. Yeah? All right. One simple question I'm giving you. One simple question. Dear students, for example, we have got 0.1 molar weak acid HA1. Then we have got 0.1 molar weak acid HA2. Then we have got 0.1 molar weak acid HA3. These are three weak acids. I'm giving you their values as well, Ka values. Ka for this acid is 10 raised power minus 5. Ka for this acid is, for example, 10 raised power minus 6. Ka for this weak acid is 10 raised power minus 7. Can you arrange these weak acids on the basis of acidic strength? This is your A, this is B, and this is C. Can you arrange them on the basis of the strength of acid? Can you let me know which weak acid is going to be comparatively stronger? You just need to check the value of Ka. More the value of Ka, stronger is going to be the acid. This is the acidic strength. This is the acidic strength, right? This is the acidic strength. So can you let me know which weak acid is going to produce more H positive in the solution? Which weak acid is going to produce more H positive in the solution? This is going to be the order, right? Perfect. I believe again this is clear. Can you give me the order of Ka? Well, you know order of Ka. Ka is A greater than B greater than C. Can you give me the order of pK? Yes, it's going to be C, B, and A. I believe I'm clear with this. If yes, let me know once in the chats quick. This is something which I believe would be super clear to everyone. Similarly, if you are given with weak bases and if you are given with their Kb values, you can arrange them as per the strength of the base. You can arrange them as per the strength of their base, basic characters. Yeah? Amazing. Let's try to solve this particular question. Simple, basic. See, as far as the question is concerned, calculate the concentration of H positive of a 0.05 molar CH3COOH solution. So as per the question, what have we taken? We have taken CH3COH. It's a weak acid. If it is a weak acid, it is going to remain in equilibrium with its ions. Its ions are CH3CO negative and H positive, right? You know the procedure at time t is equal to 0. Its concentration is represented by C. That's given to me as 0.05 molar. So in the beginning, this is 0, this is 0. Let's say the degree of ionization is alpha. So at equilibrium, this is going to be C minus C alpha. This is going to be C alpha. This is going to be C alpha, right? Now, this is a weak base. Sorry, this is a weak acid. If it is a weak acid, write the expression for K. That has to be C alpha squared divided by 1 minus alpha. Let me assume certain things. Let's assume alpha to be less than 0.05. At that point of time, instead of 1 minus alpha, you can just write 1, right? Therefore, your Ka becomes equal to C alpha square, and hence alpha comes out to be equal to under root of Ka by C. As per the question, Ka value is given to me in the question, which is 1.25 into 10 raised power minus 6. C value already I know, that is 0.05. Same procedure I'm following, guys. Same procedure. This is 1, this is 25 times. So this is root of 25 into 10 raised power minus 6, which comes out to be 5 into 10 raised power minus 3. Alpha came out to be equal to 5 into 10 raised power minus 3, which is less than 0.05. That means assumption which we have made, that's absolutely correct. So we got the value of alpha. This is our alpha value. And if this is our alpha value, what am I supposed to calculate? Concentration of H positive in the solution. And concentration of H positive in the solution at equilibrium is nothing but C alpha. What is C value? C is 0.05. And alpha we have calculated as 5 into 10 raised power minus 3. So the overall value will be 25 into 10 raised power minus 5 molar. This is the concentration of H positive in the final solution, which I was supposed to calculate. Yes. Quickly, people, let me know in the chats if it is clear. See, you are not supposed to do all these things again. Okay? I'm sorry. You are not supposed to follow this particular procedure again from the beginning. You just could have written alpha is equal to under root of Ka by C. A is given, C is given. Check the value of alpha. If alpha is less than 0.05, then calculate the concentration of the ion. That's it. Now, look at this particular question, guys. Look at this particular question. Look at this particular question. Calculate the ionization constant of a weak base. That means Kb we have to calculate. Calculate the ionization constant of a weak base, NH4OH. If the concentration of OH negative, in its 0.1 molar aqueous solution is 0.05 molar. It's again a simple now. It's again a simple question now. See guys, we are right now starting with a weak base, that is NH4OH. So this weak base is going to remain in equilibrium with its ions, and I must say its ions are NH4 positive aqueous, and with this we have got OH negative aqueous, right? You know it. Now, initially, as per the question is concerned, the concentration of NH4OH is given to me as 0.1 molar. So this would be 0, this would be 0. Now, at equilibrium, if the degree of ionization is alpha, so this has to be C minus C alpha, this has to be C alpha, this has to be C alpha. Is it correct till here? Yes. Now people, just tell me one thing. As far as the question is concerned, the concentration of OH negative in the aqueous solution, the concentration of OH negative in the aqueous solution is equal to what? Is equal to 0.05 molar. Can I say it is basically the concentration of OH negative in the container at equilibrium? Because once equilibrium is established, after that, the concentration of ions, they do not change. Now, in the question they mentioned, concentration of OH negative in the solution, that is 0.05. That means concentration of OH negative at equilibrium, that is 0.05 molar. Right? So, OH negative concentration is nothing, it is C alpha. So, C alpha is given to me as 0.05. So, from here, I can calculate alpha, which is 0.05 divided by C. Now, as per the question, what is the value of C? C value is 0.1. So, alpha is coming out to be 0.5. Alpha is coming out to be 0.5, which is more than 0.05. So, that means if you want to calculate the value of Kb, which has to be equal to C alpha square divided by 1 minus alpha, here you cannot neglect alpha in comparison to 1. Because alpha value, it is coming out to be greater than 0.05. Right? So people, what is the value of C? C value is 0.1. Raised power minus 1. What is alpha? Alpha I got to know, 0.5 cos square, C alpha square divided by 1 minus 0.5 is 0.5. 1.5 cancel. The final value will come out to be 0.05. If I'm clear with this particular question, you need to let me know right now in the chats. Everybody with some fire emojis, quick. Quick people, everybody in the chats, quick. Everybody in the chats, quick. If this is super clear to everyone. Everybody in the chats, quickly. All clear? All clear, guys, quickly. Perfect. Perfect, guys. Now, let's move on to one more topic. What is that? What is that? That's what you call us. That's what you call as Ostwald's dilution law. Ostwald's dilution law. So people, what this Ostwald's dilution law is all about? It's a simple statement, basically. It's a simple statement. What is it? See, as per your Ostwald's dilution law, let me tell you. Ostwald's dilution law states that with dilution, degree of ionization, with dilution, degree of ionization of a weak electrolyte, increases. With the dilution, degree of ionization of a weak electrolyte, what happens to that? With the dilution, degree of ionization of a weak electrolyte, that increases. What does it mean? Say, for example, imagine this is a container which I'm taking. Okay, this is a container. Imagine this particular container is filled with water. It is filled with water. Okay, it's filled with water. Now, my dear students, imagine that in this container which is filled with water, I'm introducing a weak electrolyte AB. If I'm introducing a weak electrolyte AB, now, since it's a weak electrolyte, it will partially ionize and it's going to remain in equilibrium with its ions. Ions are A positive aqueous and B negative aqueous, right? Yes, so this weak electrolyte, it is in equilibrium with its ions. Initially, if its concentration is C, 0, 0, degree of ionization is alpha. So at equilibrium, this has to be C minus C alpha, this has to be C minus C alpha, this has to be C minus C alpha. You know it. Now, if I want to write the expression of Ki, ionization constant, it has to be nothing but C alpha squared divided by 1 minus alpha. Okay, this is the ionization constant. This is the ionization constant of the weak electrolyte. Now, if I assume, let alpha to be less than 0.05, therefore, 1 minus alpha, you can write as 1. Therefore, Ki becomes nothing but only C alpha square. So alpha comes out to be equal to under root of Ki divided by C. Alpha comes out to be under root of Ki by C. This is something also you know. My dear students, just understand one thing. What is C? C represents concentration. Concentration means molarity. Defined as moles per unit volume of the solution in liters. This is C, concentration, moles per unit volume. Now, just tell me one thing. For example, in this container, let's say I'm doing the dilution. Dilution means addition of extra solvent. The solvent used here is water. So, imagine I'm introducing more water in the same container. That means what am I doing? I'm doing the dilution. I'm introducing more water in the container. If I'm introducing extra water in the container right now, what will happen to the total volume of the solution? I would say total volume of the solution will increase. Now, people, if total volume of the solution increases, what will happen to concentration? What will happen to the value of C? I would say C value will decrease because inversely proportional. If C decreases, alpha and C inversely proportional. If C is decreasing because of dilution. Because of dilution, C is decreasing. Therefore, alpha value would be increasing. This is what your Ostwald's dilution law is all about. With dilution, the degree of ionization of a weak electrolyte, it increases. With the dilution, the degree of ionization of a weak electrolyte, that increases. That means with the dilution, if I keep on doing the dilution, this weak electrolyte would be getting converted more into its ions. With dilution, the degree of ionization of a weak electrolyte, that increases. So this weak electrolyte will be getting more and more converted into its ions due to dilution. Right? Can I say, if I keep on doing the dilution continuously, can I say alpha value of this weak electrolyte will keep on increasing? It will keep on increasing. I would say, if I keep on doing the dilution continuously, the value of alpha of a weak electrolyte will keep on increasing. Can I say there will be a time where alpha will attain its maximum value? And what is the maximum value of alpha? Maximum value of alpha is 1. There will be a time, if I keep on doing the dilution continuously, there will be a time when alpha would attain its maximum value. And maximum value of alpha is 1. And alpha value 1 means, now I would say, the weak electrolyte at this particular point of time, would be behaving like a strong electrolyte. That means this weak electrolyte would have got converted 100% into its ions, and that is something, that dilution is something which we call as infinite dilution. So at infinite dilution, when you keep on doing the dilution continuously, the value of alpha of this weak electrolyte will keep on increasing. That means this weak electrolyte will continue to get converted into its ions. It will be continuously getting converted into its ions. There will be a time when this weak electrolyte would have got 100% converted into its ions. That is the time when this weak electrolyte will be behaving like this strong electrolyte, right? And that dilution is something which we call as infinite dilution. So remember, at infinite dilution, weak electrolyte would be 100% dissociated into its ions, and its alpha would have attained its maximum value. That maximum value of alpha is equal to 1. I believe I'm clear with this. Right? I believe I'm clear with this. Okay? I believe I'm clear with this. Perfect. Now, let me tell you one more thing. What is that? That is effect of temperature. On degree of ionization of a weak electrolyte. Effect of temperature on the degree of ionization of a weak electrolyte. Understand what I'm going to say. Understand, people, what I'm going to say. First of all, let's say I've got the weak electrolyte AB. You're introducing this in water. Since it's going to remain in equilibrium with its ions, you know it. It's A positive plus B negative. Okay, it's A positive plus B negative. Correct? My dear students, let me tell you one thing. The ionization constant Ki. What is ionization constant? It's basically equilibrium constant, Kc. It's basically equilibrium constant, right? This Ki I call as ionization constant of the weak electrolyte. Ionization constant of a weak electrolyte, which is basically your Kc, equilibrium constant. And this weak electrolyte, when introduced in water, now it's in equilibrium with its ions. Let me tell you, ionization of a weak electrolyte. Is an endothermic process. Ionization of a weak electrolyte. Which process this is? Ionization of the weak electrolyte. Which process? It is an endothermic process. If it is an endothermic process, do you remember in chemical equilibrium we have discussed equilibrium constant. Equilibrium constant is directly proportional to temperature in case of the endothermic reactions. We have discussed this in chemical part. In chemical equilibrium, we have discussed equilibrium constant. It's directly proportional to temperature. For which reactions? For endothermic. This particular process is endothermic. Right? So, equilibrium constant over here, which is Ki, which is what I call as ionization constant here. So, ionization constant here will be directly proportional to temperature. So, what does that mean? That means when you increase the temperature, on increasing the temperature, equilibrium constant has to increase. Equilibrium constant here I'm calling as Ki. So, Ki will be increasing. Ki, what is the expression for Ki? Ki expression means concentration of A positive, concentration of B negative at equilibrium divided by concentration of AB, right? So, on increase the temperature, Ki value has to increase. If Ki has to increase, that means numerator has to decrease, denominator has to decrease. How will be numerator increasing? Numerator will be increasing when concentration of A positive and B negative will be increasing. And how concentration of A positive and B negative will be increasing? When this reaction will be moving in the forward direction. And when the reaction shifts towards forward, what happens? What does that mean? That means the degree of ionization of this electrolyte is increasing. Perfect. So remember, on increasing the temperature, degree of ionization of the weak electrolyte, that also increases. Right? Perfect. Am I clear with this? People? Say it in the chats quick. Yeah? Say it in the chats quick, everybody. Everybody. Amazing. Let's move on to one more important concept which I believe is used almost everywhere in your ionic equilibrium. What is that? That's your common ion effect. Common ion effect. Let's get to know what this common ion effect exactly is all about. My dear students, I would want you guys to read the statement once. Common ion effect. It is defined as the suppression of degree of ionization of a weak electrolyte. The suppression of degree of ionization of a weak electrolyte when a strong electrolyte containing a common ion is added to it. When a strong electrolyte containing a common ion is added to it. What is meant by this? Is just a second. Be like this. Be like this. Just a second, huh? Just a second, people. I need to turn the lights on. I need to turn the generator on. Just a second. It's done. All right now. So, common ion effect. The suppression of degree of ionization of a weak electrolyte when a strong electrolyte containing a common ion is added to it. Understand what exactly I'm going to say. Imagine that you have got a container. This is the container which we have. I'm assuming this particular container is filled with water right now. Right? This particular container, it's filled with water right now. For example, in this container, I'm going to introduce a weak acid. Let's say CH3COH. If I'm introducing a weak acid, CH3COH, that means this weak acid will remain in equilibrium with its ions. Its ions are CH3CO negative and H positive. Correct? Let's say its initial concentration was C. This would have been 0. This would have been 0. Let's say its degree of ionization was alpha. So at equilibrium, this has to be C minus C alpha. This has to be C alpha. And this has to be C alpha. Okay? Or I need some space. Just a second. Let me write it slightly above. So let's assume that its initial concentration was C. This was 0. This was 0. Now at equilibrium, this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. Okay? So what did I do? I introduced this weak acid in water. And this weak acid now is in equilibrium with its ions. Right? So this particular system is at equilibrium right now. The system is at equilibrium. And you know, when the system is at equilibrium, as per thermodynamics, the system is present at its maximum stable state. So system is right now at its maximum stable state. Now, if I'm going to do certain changes to the system right now, which principle we are going to use? Le Chatelet principle. Which principle we are going to use now? If I'm going to do certain changes now, that means Le Chatelet principle is going to come into play. And what Le Chatelet principle says in short, whatever changes you do to the reaction, equilibrium is going to do opposite of that. Since this particular weak electrolyte is in equilibrium with its ions, so the system is at stability right now. If I want to alter the stability, if I want to do some changes right now, equilibrium is exactly going to do opposite of that, as per Le Chatelet. Now understand. Let's assume that the weak electrolyte which is there in the container, let's assume alpha value of this weak electrolyte is less than 0.05. Let's say alpha value of this weak electrolyte is less than 0.05. Now, my dear students, imagine in the same container, I am introducing a strong electrolyte like HCl. For example, in the same container, since in the container, weak electrolyte is in equilibrium with its ions. Now, in the same container, what am I introducing? A strong electrolyte, HCl. This strong electrolyte HCl would be getting completely dissociated into its ions. Ions are H positive aqueous and Cl negative aqueous. Right? Let's say its concentration is C1. Initially, this will be 0, this will be 0. Now, with a strong electrolyte, 100% dissociated. So, nothing left. 1 mole gives 1, C1 gives C1. This is C1. Now, observe one thing. In the same container, what do we have? In the same container, we have got a weak electrolyte, a strong electrolyte, both having one ion in common. Which ion is that? H positive. Both having one ion in common. Okay? Both having one ion in common. Tell me one thing. Earlier, weak electrolyte was in equilibrium with its ions. Now, I'm introducing HCl. because of the introduction of HCl in the same container, can I say I am technically trying to increase the concentration of H positive in the container? Because of the addition of HCl, I am technically increasing the concentration of H positive in the container. Since this reaction was in equilibrium, now we are trying to increase the concentration of H positive. How? By addition of HCl. And if the concentration of H positive increases, what will happen? Le Chatelet principle. If I'm increasing the concentration of H positive, system will try to decrease the concentration of H positive. How exactly it will decrease the concentration of H positive? When this reaction will shift, when equilibrium shifts in the backward direction. And when this reaction shifts in the backward direction, that means H positives will start reacting again with CH3CO negatives and will form what? Will form CH3COH back. So, due to the addition of HCl, concentration of H positive is increasing in the container. So, this reaction will shift in the backward direction due to Le Chatelet. And if the reaction shifts backward, what does that mean? This ion and this ion, they are reacting and forming what? CH3COH back. What does that mean? That means the degree of ionization of the weak electrolyte, is it increasing or decreasing? I would say degree of ionization of the weak electrolyte is further decreasing. Already it was less than 0.05. Now it's further decreasing. And that decrease in the degree of ionization, of a weak electrolyte, when a strong electrolyte having a common ion is added, that decrease in the degree of ionization of a weak electrolyte is something which we call as common ion effect. So in common ion effect, what happens? The degree of ionization of a weak electrolyte, it decreases. And this suppression, this decrease in the degree of ionization of a weak electrolyte, when a strong electrolyte having a common ion is added, that's something which I call as common ion effect. Now, what are the consequences of this common ion effect? What are the consequences? Let's get to know. What are the consequences? First of all, I got to know. Alpha value already was less than 0.05. Now it has further decreased. That means wherever you want to neglect alpha, you can do that. Wherever you want to neglect alpha, you can do that. Right? Because alpha has further decreased. Now if I ask you, which is my common ion? Common ion was H positive. What is the concentration of H positive coming from CH3COH? I would say concentration of H positive coming from CH3COH was C alpha. Concentration of H positive coming from HCl was C1. So total H positive concentration would be C1 plus C alpha. This would be the total H positive concentration. And instead of C1 plus C alpha, I can now only write as C1 because alpha has decreased. If alpha has decreased, that means C alpha has decreased. Alpha was already less than 0.05. Now alpha has further decreased. If alpha has decreased, that means C alpha value would have also decreased. So instead of C1 plus C alpha, I can just write C1. Okay. Now, my dear students, what was my common ion here? Common ion was H positive. So concentration of common ion. Finally, if I ask you, what is the concentration of common ion? Concentration of common ion came out to be C1. And what was this C1? C1 was the concentration of H positives coming from the strong electrolyte. So, a note over here. Remember this particular point. Concentration of common ion is entirely decided by what? Concentration of common ion is entirely decided by which electrolyte? Is entirely decided by the strong electrolyte. Concentration of the common ion, it's entirely decided by the strong electrolyte. Now, my dear students, if I ask you to write the dissociation constant expression for this weak acid, it's simply going to be concentration of CH3CO negative multiplied by concentration of H positive divided by concentration of CH3COH. Now tell me one thing. What is the concentration of CH3CO negative now? It is C alpha. What is the concentration of H positive now? It is C1 divided by. What is the concentration of CH3COH? C minus C alpha. Take C as common. 1 minus alpha. Since alpha has further reduced due to common ion effect, so instead of 1 minus alpha, you can just write 1. C gets cancelled. Instead of 1 minus alpha, you can just write 1. So Ka comes out to be equal to alpha into C1. Alpha will be equal to Ka divided by C1. Alpha would be equal to Ka by C1. Now, if I ask you which alpha this is, Is this the old alpha or the new alpha after common ion effect is operated? I would say this is the new alpha after common ion effect is operated. This is the new alpha after common ion effect is operated. Earlier alpha was when the weak acid was in equilibrium with its ions. Its alpha was under root of Ka by C. Under root of Ka by C. Now due to common ion effect, new alpha is Ka by C1. This is the new alpha. Now if I ask you, finally, tell me the concentration of CH3CO negative in the final solution. The concentration of CH3CO negative in the final solution is nothing but C times alpha. So this is C. Now the alpha is new, so it has to be Ka by C1. This is how you calculate concentration of CH3CO negative in the final solution, and this is how you calculate the concentration of common ion H positive in the final solution. I believe I'm clear with this. I'll give you one more example so that it'll be properly clear to you. Okay? One more example I'm giving you of the common ion effect. Understand? Now you are going to answer every single thing, whatever I'll be asking you. See guys, for example, this is the container which I have. This container is filled with water. Now I'm introducing a weak base, NH4OH. If I'm introducing a weak base, NH4OH, what's going to happen? If I'm introducing a weak base, NH4OH, what's going to happen? It will remain in equilibrium with its ions. Ions are NH4 positive aqueous, and with this you'll be writing OH negative aqueous. Correct? If its concentration is C, this is 0, this is 0. This will be C minus C alpha, this is C alpha, this is C alpha. Right now in the container we have got the weak base which is in equilibrium with its ions, and I'm assuming its alpha right now is less than 0.05, and alpha here will be under root of Kb by C. Alpha here will be under root of Kb by C, because in the container there is only weak base present in equilibrium with its ions. Now in the same container, imagine I'm adding NaOH. In the same container, imagine I'm adding NaOH. NaOH is a strong base. If it's a strong base, it's a strong electrolyte. If it is a strong electrolyte, it will get 100% ionized into what? Na positive and OH negative. Let's say its concentration was initially C1, 0, 0. Now this is 0, this would be C1, this would be C1. Tell me one thing. In the container, what all things we have? In the container, we have got weak electrolyte and a strong electrolyte. Both are having one ion in common. Which one is that? Both are having one ion in common. So which effect is going to operate here? Common ion effect, due to which this reaction shifts backward. So degree of ionization of the weak electrolyte will further decrease. It will further decrease. Already degree of ionization of the weak electrolyte was less than 0.05. Now it will be further decreased, and that decrease in the degree of ionization of the weak electrolyte when a strong electrolyte having a common ion is added. What do you call that effect as? The common ion effect. Right? So, what is the concentration of the common ion? Concentration of common ion will be C alpha plus C1, which will be simply written as C1 now. Okay? Because this C alpha would have decreased. Right? So, instead of C1 plus C alpha, I'm just writing C1. Now, people first of all tell me, what is the concentration of common ion now? Common ion is OH negative. Concentration of common ion is entirely decided by the strong electrolyte, that is equal to C1. Okay? Now, what was the old value of alpha? Old value of alpha was under root of Kb by C. This was old value of alpha when there was only weak electrolyte in the container, right? Now, if I ask you, what will be the new alpha? For that, write the expression of Kb. For that, write the expression of Kb for this weak base, which is going to be concentration of NH4 positive, that is C alpha. Concentration of OH negative, that is just C1 now, divided by concentration of NH4OH, that is C minus C alpha. Now, instead of 1 minus alpha, you can just write 1. This C and this C cancels out. So, new alpha here comes out to be Kb by C1. This is my new alpha after common ion effect is operated. If this is my new alpha, so tell me what will be the concentration of NH4 positive in the final solution. Concentration of NH4 positive in the final solution is C multiplied by, now it's new alpha, so C multiplied by Kb divided by C1. Am I clear? Am I clear, people? Am I clear? Am I clear? Quick. If this is clear, then you should be in a position to solve this question quickly. You should not take a lot of time to solve this question. Okay? Calculate the concentration of each ion in equilibrium in an aqueous solution containing. First question, only in the container, that is 0.1 molar. That is 0.1 molar NH4OH. So the first question is simple. In the container, there is only weak base, which is in equilibrium with its ions. So this is my first question. In the container, there is only weak base present. Which weak base? NH4OH. NH4OH. Only this is present in the container. So it would be present in equilibrium with its ions, NH4 positive aqueous, and with this you have got OH negative aqueous, right? Let its concentration is C in the beginning, 0, 0, and this C value is 0.1 molar. Let's say its degree of ionization is alpha. At equilibrium, C minus C alpha, this is C alpha, this is C alpha. When in the container, only there is this weak base present, which is in equilibrium with the ions, right? Which is in equilibrium with the ions. Now, how do I calculate its alpha? Its alpha is simply going to be, since it's 1:1:1, so alpha is simply going to be under root of Kb by C. So under root of, what is Kb? 1.8 into 10 raised power minus 5. What is C? 10 raised power minus 1. Root of 1.8 is 1.34. It will be finally into 10 raised power minus 2, which is coming out to be less than 0.05. That means our assumption is right. This is the actual value of alpha. If this is the actual value of alpha, calculate the concentration of each ion. So concentration of NH4 positive at equilibrium is equal to the concentration of OH negative at equilibrium. Both are equal to what? Both are equal to C alpha. C value is 0.1. Alpha is this. So C multiplied by alpha, it will be 1.34 into 10 raised power minus 3 molar. So first question is done. When only in the container there was weak base present. Now the second question. So there is already NH4OH in the container, in equilibrium with its ions. Already this is something which is present. In the container. Now, in the same container, and right now, when only there is weak base in equilibrium with its ions, right now its alpha is 1.34 into 10 raised power minus 3, right? Now, in the same container, what are we adding? We are adding NH4Cl. Do you see this NH4Cl? It is the salt of NH4 positive. And if it is the salt of NH4 positive, it is water soluble. And all the water soluble salts, they are strong electrolytes. So this would get dissociated completely into its ions. Ions are NH4 positives and Cl negatives. Now, what is the concentration of NH4Cl which you are introducing? 0.1. Initially, this would be 0. Now, this is 0. This would be C1. So now this is something which is happening in the same container, right? You know it. Okay. So, weak electrolyte, strong electrolyte. Both are having one ion in common. Which one is that? NH4 positive. So, common ion concentration technically has to be equal to C alpha plus C1. But due to common ion effect, alpha value would have decreased. So, instead of C1 plus C alpha, I'll just write C1. So, my first question is sorted. Done. What is the concentration of NH4 positive now in the container at equilibrium? It is equal to C1, right? And C1 is nothing but 0.1 molar, right? Now, second question. What is the concentration of OH negative in the final solution? Concentration of OH negative in the final solution is equal to C alpha, C times alpha. Now, C as such, what would be the new alpha? Old alpha was under root of Kb by C. New alpha would be Kb by C1. Few minutes back we have discussed. New alpha would be Kb by C1. So, C is 0.1. Kb value is how much? 1.8 into 10 raised power minus 5. And C1 value is 0.1, right? C1 value is 0.1, correct? Right, people? So this term cancels out. This is the value of new alpha. Look at the old alpha, 10 raised power minus 3. What is the new alpha? 10 raised power minus 5. That means alpha value of weak electrolyte has actually decreased, right? Alpha value of the weak electrolyte has actually decreased. Correct? Initially, it was 1.34 into 10 raised power minus 3. Due to common ion effect, alpha of the weak electrolyte decreases, right? See how much it has decreased. Now it is 1.8 into 10 raised power minus 5. So tell me, sorry, this is not alpha, guys. Alpha is how much? Only Kb by C1. Kb is this much divided by C1. C1 is 10 raised power minus 5. So alpha is 1.8 into 10 raised power minus 4. New alpha is 1.8 into 10 raised power minus 4. Okay, if new alpha is 1.8 into 10 raised power minus 4, so new OH negative concentration would be 1.8 into 10 raised power minus 5 molar. Okay, old OH negative concentration was this much. New OH negative concentration is this much. So OH negative concentration has decreased. Why? Because alpha has decreased. Initial alpha, earlier old alpha was 1.34 in 10 raised power minus 2. New alpha is how much? 1.8 in 10 raised power minus 4. So alpha has decreased. Yes, I hope this particular question is clear. And if this question is clear, you should be in a position to solve this one as well. Without writing all these equations and stuff, you should be in a position to solve this question. Question is, calculate the concentration of H positive and CH3CO negative at equilibrium if 0.5 molar HCl is added in an aqueous solution containing 0.1 molar CH3COH. That means in the container, there is already CH3COH. It's a weak acid. Now you are introducing HCl. You are introducing HCl. Its initial concentration is 0.1 molar. Its concentration is 0.5 molar. What am I supposed to calculate? I'm supposed to calculate the concentration of H positive and CH3CO negative. It would be dissociated as CH3CO negative plus H positive. This would be dissociated as H positive plus Cl negative, correct? So, weak electrolyte, strong electrolyte. Both are having one ion in common. And common ion concentration is entirely decided by the strong electrolyte. So, it will be directly 0.5 molar. First question is done. 0.5 molar. Second question. What is the concentration of CH3CO negative? Concentration of CH3CO negative here will be C alpha finally. Sorry. Concentration of CH3CO negative would be C alpha. Concentration of CH3CO negative at equilibrium would be C alpha. But now it's new alpha. New alpha is Ka by C1. Right? So C is the concentration of weak electrolyte, 0.1. Ka value is given to me, 1.8 in 10 raised power minus 5. C1 value is the concentration of this one, that is 0.5. Right? So it is going to be what? It's going to be 3.6 into 10 raised power minus 6 molar. This is the concentration of CH3CO negative in the final solution. Right? Perfect. Without doing any sort of writing the equations, C1 plus C alpha, C alpha, C alpha, all that, we remember things directly now. Similarly, can you solve this question without even using pen paper? Can you solve this question without using pen paper? Tell me the answer in the chats. I'm looking at the chats. Everybody. I am looking at the chats. Tell me the answer without using pen paper. Calculate the concentration of H positive at equilibrium if 0.1 molar HCl is added in an aqueous solution containing 0.1 molar CH3COH. Again, weak electrolyte, strong electrolyte, both having one ion in common. That common ion is H positive. So what would be the concentration of that common ion? What would be the concentration of that H positive? Tell me. Guys, you should be in a position to answer this question without using pen paper. Quickly, everybody, what should be the answer of this question? I want everyone to solve this. And tell me in the chats. In the question, they are asking about the concentration of common ion, and concentration of common ion is entirely decided by the strong electrolyte, right? So, concentration of H positive in the final solution has to be equal to what? 0.1 mole. This is the answer of the question. Correct? Correct, people? Did you understand how we are using the common ion effect and solving the questions? Tell me. So old alpha is under root of K by C. New alpha is either Ka by C1 or Kb by C1, depending on whether the weak electrolyte is weak acid or weak base. I hope this is again clear to every one of you. Okay. Now guys, comes one more thing. What is that? That is ionic product of water. And after this, we are going to move into pH. Okay, ionic product of water. What is this ionic product of water? Try to understand. See, my dear students, if I talk about pure water, H2O liquid, pure water. Okay, pure water is also considered as a weak electrolyte. Pure water is also a weak electrolyte. Okay. And if pure water is a weak electrolyte, it is going to remain in equilibrium with its ions. And its ions you can represent like this, H positive and OH negative. This is how you can represent them. Right? Or you can say this H positive will further interact with water. It is going to become H3O positive. That is further going to interact with water. One and the same thing. Okay? This is the simplest way of writing this equation. Pure water, it's a weak electrolyte which is remaining in equilibrium with its ions. So basically, you've got a container which contains water, pure water. That pure water is in equilibrium with its ions. And if pure water is in equilibrium with its ions, if I want to write the expression of ionization constant, since it's a weak electrolyte, it's a weak electrolyte, it's a weak electrolyte. If I want to write its ionization constant, how will I be writing? Concentration of H positive raised power 1, OH negative raised power 1 divided by concentration of H2O. So Ki multiplied by concentration of H2O has to be equal to concentration of H positive in the container and OH negative in the container. See, this water here is in liquid state, right? Water here is in liquid state. Perfect. So its active mass is constant. So basically this particular term is constant. This term is already a constant. Constant multiplied by constant is a new constant which I'm representing with Kw. And Kw expression is nothing but concentration of H positive in the container multiplied by OH negative in the container. And this Kw here is something which is what you call as ionic product of water. This is what you call as ionic product of water. And this particular expression of Kw, it is valid at all temperatures. It is valid at all temperatures. Now just tell me one thing. Since it is behaving as a weak electrolyte, right? And ionization of the weak electrolyte, that is endothermic. Ionization of the weak electrolyte, that is endothermic. If ionization of a weak electrolyte is endothermic, that means on increasing the temperature, if it is endothermic, for endothermic processes, equilibrium constant is directly proportional to temperature. And your equilibrium constant here was what? It was your Ki. So Ki here is directly proportional to temperature, right? And your Kw depends on Ki. So can I say in short, on increasing the temperature, since on increase the temperature, degree of ionization of weak electrolyte increases. If degree of ionization of weak electrolyte increases, that means more H positives, more OH negatives are generated in the solution. If more H positives, more OH negatives are generated in the solution, so value of Kw will be increasing. Remember, Kw depends on temperature. I'm writing this statement here. Kw, ionic product of water, it depends on what? It depends on temperature. And remember, Kw is directly proportional to temperature. On increasing the temperature, the value of Kw increases. Correct till here? The value of Kw increases. Now, understand one simple thing. I got to know Kw, ionic product of water, is nothing but concentration of H positive in the solution, concentration of OH negative in the solution. Now, let me tell you, at 25 degrees centigrade, do remember this particular data. At 25 degrees centigrade, concentration of H positive and OH negative in the solution, it is always equal to 10 raised power minus 7 molar. At 25 degrees centigrade, concentration of H positive and OH negative in the solution is always equal to 10 raised power minus 7 molar. So I would say Kw at 25 degrees centigrade is basically concentration of H positive multiplied by OH negative. This 10 power minus 7, it becomes 10 raised power minus 14. Correct? It becomes 10 raised power minus 14. So technically the value of Kw at 25 degrees centigrade is equal to 10 raised power minus 14. Now guys, see what I'm doing. Applying minus log on both the sides. If I multiply this equation with minus log, it becomes minus log of Kw is equal to minus log of H positive multiplied by OH negative is equal to minus log of 10 raised power minus 14. Right? Now guys, before further solving this, remember P is a mathematical operator which stands for minus log. P is a mathematical operator which stands for minus log. So if I sometimes write pH, that means I'm talking about minus log of H positive ion concentration. Sometimes if I write POH means minus log of OH negative ion concentration. If I sometimes write pKa, it means minus log of Ka. If I sometimes write pKw, it represents minus log of Kw. So P is nothing but it's a mathematical operator that stands for minus log. P is a mathematical operator that stands for minus log. Tell me one thing now. Minus log of Kw. Instead of minus log, I can write P. So it's P of Kw is equal to P of Kw is equal to. This becomes log of m into n, which is log of m plus log of n. Then eventually it becomes pH plus POH is equal to minus log of 10 raised power minus 14. 10 raised power minus 14 comes to the front, right? Okay. 10 raised power minus 14 comes to the front. Sorry. 10 raised power minus 14 comes to the front. Minus minus plus, so it becomes only 14. So this particular equation, it is valid only at 25 degrees centigrade. This equation is valid only at 25 degrees centigrade. And you call, if you remember, the scale which you study, pH scale 0 to 14. So that is basically the scale which is valid only at what? That is the scale which is valid only at 25 degrees centigrade, 0 to 14. Okay. Now guys, understand some important things. Some important things. You know, if the concentration of H positive in the solution is equal to concentration of OH negative in the solution, right? I would say the solution is neutral. And at 25 degrees centigrade, the pH of the solution has to be 7. pH of the solution would be 7. Now, if the concentration of H positive is greater than that of concentration of OH negative in the solution, right? The solution is supposed to be acidic, and at 25 degrees centigrade, its pH has to be less than 7. Okay. Similarly, if the concentration of OH negative is greater than that of concentration of H positive in the solution is said to be basic, and at 25 degrees centigrade, its pH has to be greater than 7. Its pH has to be greater than 7. Okay. This is something which I believe everybody would be knowing. Now the point which I'm going to tell you now, that is the most important point. What is that? See guys, on increasing the temperature, when you increase the temperature, what happens to Kw? On increasing the temperature, Kw increases. On increasing the temperature, Kw increases. Something which we discussed a few minutes back. Kw is directly proportional to temperature. When you increase the temperature, this water starts getting converted more and more into its ions, right? More and more into its ions. But on increasing the temperature, water starts getting more and more into its ions. Water starts getting converted more and more into its ions. But do you see, on increasing the temperature, no doubt, these are increasing in the solution. But, both are increasing by same amount. On increasing the temperature, water starts getting ionized more. So in the container, H positive concentration, OH negative concentration, both increase by the same amount. Therefore, if both are increasing by the same amount, I would say neutrality of water. Neutrality of water remains the same. Neutrality of water remains the same. What does that mean? That means if you have got water at 25 degrees centigrade, if you have got water at 35 degrees centigrade, if you have water at 80 degrees centigrade, water at every temperature would be neutral. Water at every temperature would be neutral, because on increasing the temperature, Kw increase. Kw increase means concentration of H positives and OH negatives. They will increase, but they'll increase by same amount. So concentration of H positive, OH negative at every temperature in pure water would be the same. So the water is going to be neutral at every temperature. Water is going to be neutral at every temperature. But remember, on increasing the temperature, pH of water decreases. pH of water decreases. Now you must be thinking why. On one side, I'm telling you that water at every temperature, it's neutral. But on other side, I'm telling you, on increasing the temperature, pH of water decreases. How can you justify this statement? See guys, how we are going to justify this statement. See, on increasing the temperature, remember the pH scale, which you have studied in class 9, 10, 0 to 14, that pH scale. On increasing the temperature, pH scale shrinks. On increasing the temperature, pH scale shrinks. What does that mean? That means, try to understand what exactly I'm going to say. That means, if your pH scale was this, 0 to 14, at what? At 25 degrees centigrade. At 25 degrees centigrade. Now, for example, at 80 degrees centigrade, you are not going to use the same pH scale. On increasing the temperature, pH scale, it is going to shrink. Now, for example, at 80 degrees centigrade, the pH scale which we are going to use now, that would be 0 to 30. That would be 0 to 30. When you increase the temperature, pH scale shrinks. Now, what happens to this? What happens to this? At 25 degrees centigrade, this was your pH scale. The middle point was 7 here. So this 7 was representing the neutral point. But on this scale, right now, the middle point would be 6.5. So this 6.5 would be representing the neutral point. 6.5 here would be representing the neutral point. Here on this scale, at 25, 7 was representing the neutral point. At 80 degree, 6.5 is representing the neutral point. Now, imagine you have got a glass of water here. Water is at 25 degrees centigrade. Here, again, you have got water at 80 degrees centigrade. Water at 25 or water at 80 degree. Water has to be neutral. I told you already. Or increase the temperature. Neutrality of water remains the same. So water at 25, water at 80. It has to be neutral. Neutral means here the water is neutral, here the water is neutral. Here the water is neutral means its pH is 7. Here the water is neutral means its pH is 6.5. So when you are increasing the temperature of water, when you are increasing the temperature of water, in order to keep the water neutral, I would say its pH is decreasing from 7 to 6.5. Earlier 7 was representing the neutral point. Now 6.5 is representing the neutral point. Do you understand this? Do you understand this? So on increasing the temperature, pH scale shrinks. pH scale shrinks, right? I would say pH of water decreases. pH of water decreases, but that does not mean neutrality changes. Neutrality of water remains the same. Neutrality of water remains the same. Correct? If this is clear, let me know once in the chats. Let me know once in the chats. Quick, everybody. Let me know once in the chats. Quick, everybody. Everybody, people. Everybody, guys. All clear? All clear with this? Yeah? Perfect. Now, people, tell me one thing. Just tell me one thing. For example, I'm asking you a question. Calculate the pH of water at 25 degrees centigrade. This is a simple question. You know its answer. Its answer is 7. But how it comes out to be 7? How it comes out to be 7? See, guys, we are supposed to calculate pH of water at 25 degrees centigrade. Since you know Kw is equal to concentration of H positive multiplied by concentration of OH negative, right? And at 25 degrees centigrade, you know concentration of H positive, OH negative in water, both are 10 raised power minus 7. So it comes out to be 10 raised power minus 14, right? This is at 25 degrees centigrade. At 25 degrees centigrade, Kw is equal to 10 raised power minus 14. Now, guys, understand one thing. We are supposed to calculate pH of water, since water is neutral at all temperatures. If water is neutral at all temperatures, I would say concentration of H positive and OH negative would be equal. If concentration of H positive, OH negative is equal, so instead of these two, here in this equation, I can write concentration of H positive square is equal to 10 raised power minus 14. Therefore, concentration of H positive would be equal to 10 raised power minus 7 molar. What am I supposed to calculate? pH. You know, P stands for minus log. Minus log of what? Minus log of H positive concentration. Since you calculated H positive concentration, that's 10 raised power minus 7. So pH of the solution has to be 7. pH of the solution has to be 7, right? So water, its pH at 25 degrees centigrade is nothing but 7. I hope this is clear. If I make certain changes, for example, I'm asking you a question. Calculate the pH of water at 80 degrees centigrade. If Kw is equal to, let's say Kw is equal to 10 raised power minus 13. Calculate the pH of water at 80 degrees centigrade. If Kw is equal to 10 raised power minus 13. Again, you are going to solve the question in a similar manner. I'll be writing something like this. Kw, which is nothing but concentration of H positive multiplied by concentration of OH negative, right? And at 80 degrees centigrade, this Kw is equal to 10 raised per 13. Now, water at every temperature is neutral. Neutral means H positive, OH negative concentration has to be the same. So I'll be writing concentration of H positive square is equal to 10 raised per minus 13. So I would say concentration of H positive will be 10 raised per minus 6.5 molar. If you got the concentration of H positive, can't we calculate pH? P stands for minus log of H positive concentration. So the value comes out to be 6.5. So now at 80 degrees centigrade, I must say pH of water is not 7, it is 6.5. Okay? It is 6.5. If I ask you pOH, don't use the equation, this one, pH plus pOH is equal to 14. This equation is valid only at 25 degrees centigrade. Right now, temperature is how much? 80 degree. So, equation would change. It is going to be pH plus pOH is equal to. This was 10 raised per minus 13. Earlier, at 25, it used to be 10 raised per minus 14. If Kw was 10 raised per minus 14, pH plus pOH is equal to 14. Therefore, when Kw is equal to 10 raised per minus 13, I would say pH plus pOH would be equal to 13 here. Scale has changed. Scale has changed. Do you understand this? Where at 25 degrees centigrade, when Kw was 10 raised per minus 14, at that point of time, pH plus pOH was 14. Now at 80 degrees centigrade, if Kw is equal to 10 raised per minus 13, that means now pH plus pOH would be equal to 13. So if I ask you what would be the value of pOH here, so 13 minus pH, 13 minus 6.5, the value comes out to be 6.5 only. Do you understand? Do you understand, people? Do you understand this? Am I clear? Am I clear? Am I clear? Yes, Siva, exactly. So now we are going to enter into what? We are going to enter into an important topic. What is that going to be? That is going to be pH calculation. But pH calculation we shall be doing after the break. What is the time now? It's 7:42. Let's get back at 8:15 p.m. So break till 8:15. But I would want every one of you to be back on time. Okay? Because now something interesting is going to start. Now something interesting is going to start. Okay? Perfect? Perfect, guys? I would want every one of you to be back on time. Chalo, see you exactly at 8:15. Till then, you guys can have your tea, coffee, whatever you would want to have. Yeah? See you in a while. Are you guys back? Yes. Are you all back? Perfect. So, people, tell me quickly, whatever things we discussed till now, are all the things clear? Let me know once in the chats. Whatever things, whatever topics we discussed till now, is every single thing clear? Is every single thing clear? Quickly. Let me know quickly in the chats, everyone. Whatever topics we have discussed till now, are all the topics absolutely clear till now? Perfect. Perfect, perfect. So now we are going to enter into one more important part of the chapter. What is that? That is pH calculation. That is going to be pH calculation. This is one of the most important topics of the chapter, and let me tell you, whenever a question is asked from the ionic equilibrium, most of the times the question is asked from this particular topic, that is pH calculation. Okay? Whenever a question is asked from the ionic equilibrium part, the question is most of the times, I would say 70-80% of the times asked from this particular topic, that is pH calculation. So, in pH calculation, what all things we are going to do? My dear students, in pH calculation, we are going to discuss about how to calculate pH of different solutions. How to calculate pH of different solutions. That is something which we'll be discussing here. Okay? So first of all, let me tell you one important thing. You know, when I talk about pH of a solution, what does it mean? What does pH mean? Let me tell you, P stands for, P is a mathematical operator, which stands for minus log. Minus log of what? Minus log of H positive. Minus log of H positive. Minus log of H positive is what you call as pH. So basically, whenever you are supposed to calculate pH of any solution, whenever you are supposed to calculate pH of any solution, the first thing which you are supposed to do is to calculate the H positive concentration in the solution. And my dear students, once we calculate H positive concentration in the solution, you just have to multiply that with minus log. You'll be getting the pH of the solution, right? So remember it from now onwards. Whenever you are supposed to calculate pH of any solution, our first thing is going to be to calculate the H positive concentration in the solution. Once we get the H positive concentration in the solution, multiply that with minus log, get the pH. That's it. That's it, guys. Okay, number one. Number two, there's a term which we'll be also using here, that is POH. That is POH. Again, P stands for minus log. Minus log of what? Minus log of OH negative concentration. For example, suppose you are supposed to calculate POH of a solution. In order to calculate POH of a solution, the first thing, you will be calculating the concentration of OH negative in the solution. And once we are done with the calculation of OH negative in the solution, multiply that with minus log, you'll be getting POH of the solution. Okay? So, pH is equal to minus log of H positive, POH is equal to minus log of OH negative. And my dear students, you know, at 25 degrees centigrade, this is something which I've already told you, at 25 degrees centigrade, pH plus POH is nothing but it is equal to 14. So these are few things which you need to take into consideration. These are few things which you need to remember. These are few things which you need to remember. Okay. Now, let's start with this pH calculation now. Understand what exactly we are going to do. My dear students, the first case 1, that is going to be the calculation of pH of a strong, monoprotic acids. Or let me not use the term monoprotic. Let me just write a term, calculation of pH of strong acids. This is our first case here in the pH calculation. Calculation of pH of strong acids. How do you calculate pH of the strong acids? Understand what exactly I'm going to do. Properly try to understand things. My dear students, for example, I'm writing a statement. 10 raised power minus 3 molar HCl aqueous solution. 10 raised power minus 3 molar HCl aqueous solution. For example, I'm supposed to calculate pH of this particular solution. Let's say I'm supposed to calculate pH of this particular solution. How exactly am I going to do it? The first thing. Since you are introducing HCl in what? You are introducing HCl in water. And my dear students, when you introduce HCl in water, since HCl is a strong electrolyte, it will get completely dissociated into its ions. Ions are H positives and Cl negatives. As simple as that. Right? Now, initially at time t is equal to 0, you are taking the concentration of HCl as 10 raised power minus 3 molar. So this would be 0. This would be 0. Now, it's a strong electrolyte, so it would be completely dissociated. Completely dissociated means I'll be left with nothing. 1 mole gives 1 mole. 10 power minus 3 is going to give me 10 power minus 3 is going to give me 10 power minus 3 molar. Similarly, this is going to be 10 raised power minus 3 molar. As simple as that. If I ask you, what is the concentration of H positive in the solution? The solution which we have taken, what is the concentration of H positive in this solution? You'll directly say concentration of H positive in the solution is equal to 10 raised power minus 3 molar. Right? 10 raised power minus 3 molar. I believe I'm clear. If concentration of H positive here is equal to 10 raised power minus 3 molar, can't we calculate pH of the solution? P stands for minus log of H positive concentration. So it directly comes out to be what? It directly comes out to be 3. You can simply calculate the pH like this. Number 1. Number 2. For example, you have got 10 raised power minus 4 molar HCl aqueous solution. Can you do its pH calculation? Absolutely. These are simple cases which I'm taking. So first of all, you are introducing HCl into water. When you introduce HCl into water, this HCl being the strong electrolyte, it would be completely dissociated into H positive and Cl negative. So you are starting with 10 raised power minus 4 molar. So in the beginning, this is 0. This is 0. Now it's a strong electrolyte, completely dissociated. So I'll be left with nothing. This will be 10 raised power minus 4 molar. This will be also 10 raised power minus 4 molar. So if I ask you, what is the concentration of H positive in the solution? Concentration of H positive in the solution is 10 raised power minus 4 molar. So can we calculate pH? Absolutely. pH of the solution is minus log of H positive concentration. So the value directly comes out to be 4. So pH of this particular solution is 4. Right? Perfect. For example, let's say I'm writing 10 raised power minus 2 molar H2SO4 aqueous solution. Let's say I need to calculate its pH. Use the same thing. First of all, H2SO4, you are introducing this H2SO4 in water. When you are introducing H2SO4 in water, H2SO4 again being the strong electrolyte would be completely dissociated into its ions. Its ions are going to be 2 times H positives and SO4 dinegatives. Now, my dear students, imagine initially its concentration is 10 raised power minus 2 molar. This will be 0. This will be 0. Now, since it's a strong electrolyte, it will be getting completely dissociated. So I'll be left with nothing. 1 mole gives 2 moles. So 10 power minus 2 is going to give us 10 raised power 2 into 10 raised power minus 2 molar. This is the concentration of H positive coming from H2SO4. Now 1 mole gives 1 mole, 10 power minus 2 gives 10 power minus 2. So if I ask you, what is the concentration of H positive in the solution coming from the acid? It is 2 into 10 raised power minus 2 molar. Therefore, if I want to calculate pH, P stands for minus log of H positive, which is 2 into 10 raised power minus 2. Just solve it. Log of M into N is a log of M plus log of N. Log of M into N is equal to log of M plus log of N. So log 2 is nothing but 0.3. Log of M raised power N is N log M. So minus 2 comes to the front. The value comes out to be 1.7. So pH of this particular solution is nothing but 1.7. Correct? I hope I'm clear with this. Now guys, try to understand few more things. For example, I'm writing 10 raised power minus 7 molar HCl aqueous solution. Let's say I'm taking 10 raised power minus 7 molar HCl aqueous solution. The procedure which I have been showing you for the pH calculation till now. Let's do one thing. Let's use the same procedure first. Let's see what do we get. Let's use the same procedure. Same procedure means you are introducing HCl into water. When you introduce HCl into water, it would get completely dissociated into its ions. Ions are H positive and Cl negatives. So initially its concentration is 10 raised power minus 7 molar, 0, 0. Now it's a strong electrolyte, completely dissociated into its ions. So I'll be left with nothing. 1 mole gives 1, 10 power minus 7 is going to give us 10 power minus 7. Similarly, 1 gives 1, 10 power minus 7 gives us 10 power minus 7. Correct? So as per this process, what is the concentration of H positive in the solution? It is 10 raised power minus 7 molar. As per this process, right? Therefore, if you want to calculate pH, what should be the pH? Minus log of 10 raised power minus 7. So pH of this solution should be 7. Right? pH of this solution should be 7. But guys, understand one thing. If pH of the solution is 7, that means this solution which I have taken, it should be neutral. But look at the solution. Is it the neutral solution or acidic solution? It is the acidic solution. It is the acidic solution. It is the acidic solution. So pH cannot be 7. pH cannot be 7 here. Okay. So what do we do? What do we do? Let me show you one process of solving this properly. See guys, understand what I'll be saying. First of all, you're introducing HCl in water. So basically, initially, imagine that you have got a container and that container is filled with water. Now, in that water, you're introducing HCl. If you remember, water itself is a weak electrolyte. Water itself would have got converted into H positives and OH negatives. Correct? Due to the self-ionization of water, which we discussed. Right? So before adding HCl, there were H positives in the container, which came from the ionization of water. Right? There were already H positives in the solution, which were present due to water, due to the self-ionization of water. And what is the concentration of H positives due to self-ionization of water? If you remember, at 25 degrees centigrade, that's 10 raised power minus 7 molar. Correct? So already in the container, there were H positives from the self-ionization of water. Now in that water, you are introducing HCl. Due to HCl, how many H positives are coming? Due to HCl, this is the H positives which are coming. So if I ask you, what would be the net total H positive ion concentration? What would be the total H positive ion concentration in the container, in the solution? I would say it would be this plus this. This would be the total H positive ion concentration. This plus this means 2 into 10 raised power minus 7 molar. This is the total H positive ion concentration. If you got the total H positive ion concentration, can't you calculate pH now? Minus log of net H positive ion concentration, which is 2 into 10 raised power minus 7. When you solve this, the value comes out to be 6.7. So pH of this particular solution here comes out to be 6.7. So this is going to be the actual pH of the solution. Do you understand this? Do you understand this, people? Simple and basic stuff. Right? Similarly, for example, I am writing 10 raised power minus 8 molar HCl aqueous solution. Let's say I'm asking you to calculate its pH. Normally, you will say HCl you are introducing in water. Okay, HCl you are introducing in water. So it would have got dissociated as H positive and Cl negative. Right? So initially, its concentration is 10 raised power minus 8 molar. This would be 0. This would be 0. Now it's a strong electrolyte. This would be 0. This would be 10 raised power minus 8. And this would be 10 raised power minus 8. So the concentration of H positives which we are getting from acid, is equal to 10 raised power minus 8 molar. Right? If I take minus log of it, its pH would come out to be 8. If I take minus log of this value, its pH would come out to be 8. But if pH is 8, that means the solution has to be basic. But is the solution basic or acidic? Solution is acidic. So what do I need to do? I have to take H positives, which would have come from the self-ionization of water, into consideration as well. So already in the water, there would have been H positives. How many at 25 degrees centigrade? 10 raised power minus 7 molar. If I ask you, what would be the net H positive ion concentration in the final solution? This plus this. 10 raised power minus 8 plus 10 raised power minus 7 molar. This is the total H positive ion concentration. If I take 10 raised power minus 8 as common, this would be 1 and this would be 10. So it comes out to be 11 into 10 raised power minus 8 molar. This is the total H positive ion concentration in the solution. My dear students, if this is the total H positive ion concentration in the solution, now just calculate pH. P stands for minus log of net H positive ion concentration. This is going to be minus log of 11 into 10 raised power minus 8. So it is going to be minus of log of m into n. So log m plus log of n. So minus log of 11 is equal to 1.05. This would be minus 8. The value comes out to be 6.95. I would say pH of this particular solution here would be 6.95. I believe this is clear to everyone, right? So this is how we do the calculation of the pH of strong acids. I hope I'm clear. This was my first case in the pH calculation. Look at the second case, guys. Second case is going to be simple. pH of strong bases. How do I calculate pH of strong bases? How do I calculate pH of strong bases? Understand, I'll be following the same process. Try to understand carefully what I'll be doing. First of all, I'll take simple examples. Let's say I've got 10 raised power minus 4 molar NaOH aqueous solution. I want to calculate its pH. Now, first thing which I already know, NaOH is a strong base. If it is a strong base, when you introduce it into water, when this strong base is introduced in water, it would be completely dissociated into its ions. Ions are Na positives and OH negatives, right? So initially, at time t is equal to 0, its concentration is 10 raised power minus 4 molar. So this would be in the beginning 0. This would be 0. Now it's a strong base, strong electrolyte, completely dissociated. I'll be left with nothing. 1 gives 1. So 10 power minus 1 gives 10 power minus 4 gives 10 power minus 4. 1 gives 1, 10 power minus 4 gives 10 power minus 4. So, if I ask you right now, what is the concentration of OH negative in the solution? You would say, concentration of OH negative in the solution is 10 raised power minus 4 molar. If the concentration of OH negative in the solution is 10 raised power minus 4 molar, tell me, what would be the pOH value? P stands for minus log of OH negative concentration. So, minus log of 10 raised power minus 4, the value comes out to be 4. If you got the pOH, now I can use the formula pH plus pOH at 25 degrees centigrade is 14. Therefore, pH has to be equal to 14 minus pOH. The value comes out to be 10. So this is the pH of the solution which I have taken. Do you understand this? And since pH comes out to be 10, that means the solution is basic, which we already knew. It is basic. Yeah? Perfect? Absolutely. Now, for example, let me take something like this. 10 raised power minus 3 molar. Barium hydroxide, BaOH whole twice aqueous solution. Let's say I need to calculate its pH. How do I do it? Simple. First of all, barium hydroxide, BaOH whole twice. It's again a strong base. If it is a strong base, completely dissociated into its ions. Ions are Ba di positives and OH negatives. Right? Now people, tell me one thing. Initially at time t is equal to 0, what is the concentration of barium hydroxide which is given to me? 10 raised power minus 3 molar. This would be 0. Now, it's a strong base. Strong base means strong electrolyte. Completely dissociated. I'll be left with nothing. 1 gives 1. 10 power minus 3 gives 10 power minus 3. 1 mole gives 2 moles. So 10 power minus 3 gives 2 into 10 raised power minus 3. So if I ask you, what is the concentration of OH negative in the solution? You would say it is 2 into 10 raised power minus 3 molar. If you got OH negative concentration, now we can calculate POH. P stands for minus log of OH negative, which is minus log of 2 into 10 raised power minus 3. Now, just a matter of calculation, POH is equal to minus as such, log of m into n is basically log of m plus log of n, right? Minus times. Log 2 is 0.3. This would be minus 3 in the beginning. So I would say POH is coming out to be 2.7. If POH comes out to be 2.7, therefore pH would be equal to 14 minus 2.7. The value is going to be 11.3. So pH of this particular solution is 11.3, right? Perfect. Right, people? Now you must be thinking, why did I not take OH negative concentration coming from water into consideration here in this case or here in this case? Because see guys, OH negative concentration coming from water at 25 degrees centigrade would be 10 raised power minus 7. So I would say actual OH negative concentration will be this plus 10 raised power minus 7. But 10 power minus 7 is very small as compared to 10 raised power minus 4. So this term I'm neglecting here, right? This term I'm neglecting here. I believe I'm clear. Now, for example, if I ask you a question like this, tell me the pH of 10 raised power minus 7 molar NaOH aqueous solution. If I ask you what would be its pH, what would be your answer? What would be your answer here? pH of 10 raised power minus 7 molar NaOH aqueous solution. What would be your answer here? See, you would say NaOH is a strong base. Absolutely. NaOH is a strong base. So, I would say OH negative ions coming from NaOH has to be equal to 10 raised power minus 7. So, as per this, POH should be 7. If POH is 7, that means pH should be 7. But pH is equal to 7 means neutral solution. But it's a basic solution. So, what do I need to do? I have to take OH negatives coming from water as well. Due to the self-ionization of water, OH negative concentration at 25 degrees centigrade is 10 raised power minus 7. And this is the OH negative coming from NaOH. So if I ask you, what is the total net OH negative ion concentration in the container? You'll say this plus this. So 2 into 10 raised power minus 7 molar. This is the net OH negative ion concentration. If it is the net OH negative ion concentration, we can calculate POH. P stands for minus log of what? OH negative net. So I would say it is minus log of 2 into 10 raised power minus 7, which is equal to minus log of 2 plus log of 10 raised power minus 7. So log of 2 is 0.3. Log of 10 raised power minus 7 is equal to minus 7. The value comes out to be 6.7. So this is POH. But what am I supposed to calculate? POH or pH? I'm supposed to calculate pH. So pH has to be equal to 14 minus POH. So it is 14 minus 6.7. The value comes out to be 7.3. So this is the pH of the solution. Am I clear with this? Am I clear with this, people? Tell me quickly. Yeah? I hope I'm clear with this. Right? Similarly, can you do this calculation? If I write 10 raised power minus 8 molar NaOH aqueous solution. As per the normal procedure, you will say its POH will be 8, pH will be 6. But if pH is 6, as per the normal procedure, you will say OH negative concentration is 10 raised power minus 8. POH is 8, therefore pH is 6. But if pH is 6, then this should be acidic, but it's actually basic. So what do I need to do? First of all, I'll write OH negative ions coming from NaOH are how many? 10 raised power minus 8 molar. OH negative ions coming from water due to the self-ionization of water, that is 10 raised power minus 7 molar. So net OH negative ion concentration is equal to this plus this. So 10 raised power minus 8 plus 10 raised power minus 7. If I take 10 raised power minus 8 as common, this would be 1 plus 10. So it is actually 11 into 10 raised power minus 8 molar. This is the net OH negative concentration. If this is the net OH negative concentration, I can calculate POH. P stands for minus log of what? Net OH negative concentration. So minus log of 11 into 10 raised power minus 8. So I would say POH would be equal to minus times log of M into N. Log of M into N is log M plus log of N. Now log of 11. Log of 11 is 1.05. Log of 10 raised power minus 8. Log of M raised power N log M. So minus 8 comes to the front. Log 10 eventually is 1. So POH comes out to be how much? 6.95. If POH is equal to 6.95, therefore pH would be equal to 14 minus POH. It would be 7.05. This would be the pH of the solution. Am I clear with this? Am I clear with this? Am I clear with this, guys? Say yes or no in the chats. Vijayan, what are you asking? Sir, please help me. For what? What help do you want from me? What help do you want from me? Vijayan, bro, she is not the part of Unacademy. You are right now in Unacademy. She's not the part of Unacademy. Bro, what are you doing? What are you saying? Guys, is it clear till here? No, Ria, you don't have to remember all the log values. Just remember log 1 till log 11. That's sufficient for you. That's sufficient for you. All clear till here? So this was the calculation of pH of strong acids, then pH of strong bases. Now, let's move on to the third category. If you have got a mixture of two acids, if you have got a mixture of two strong acids, how do you calculate its pH? Mixture of two strong acids. Okay? Mixture of two strong acids. See, guys, for example, if I've got an aqueous solution of some strong acid, similarly, I've got one more aqueous solution of another strong acid. So just imagine like this. I've got a container in which I've got an aqueous solution of HCl, for example. Similarly, here also I've got one more container wherein we have got an aqueous solution of H2SO4, for example. So I've got two solutions of two strong acids, right? I've got two solutions of two strong acids. This is solution of strong acid 1. This is the aqueous solution of strong acid 2. Okay? Imagine that normality of this solution is N1, volume of this solution is V1. Imagine that normality of this solution is N1, volume of this solution is V1. Similarly, imagine normality of this solution is N2, volume of this solution is V2. Correct? Let's say I'm mixing these two strong acidic solutions. My dear students, when I mix these two strong acidic solutions, what do I get? When I mix these two strong acidic solutions, what do I get? I'll be getting a final solution. I'll be getting a final solution, right? I'll be getting a final solution here. If I'm mixing these two, I'll be getting a final solution here, right? I'll be getting a final solution here. My dear students, I want to calculate pH of this final solution. pH of the solution, pH of the mixture containing two strong acids. This is the solution number 1 of some strong acid, solution number 2 of some other strong acid. You are mixing these two. You are getting a mixture of two strong acids, right? I need to calculate its pH. How do I calculate its pH? How do I calculate its pH? P stands for minus log. So minus log of net H positive ion concentration. Minus log of net H positive ion concentration. So first of all, I need to calculate the net H positive ion concentration in the final mixture. Once I get the net H positive ion concentration, total H positive ion concentration in the resulting mixture, then I'll be multiplying that with minus log. I'll be getting the pH, right? Now, since it is an acidic solution, you are mixing the two. So the final mixture which you get over here, it is going to be acidic in nature. It is going to be acidic in nature. Since it is going to be acidic in nature, so its pH is going to be less than 7. Its pH is going to be less than 7. Let me tell you one thing, one simple thing. The net H positive ion concentration in the mixture is going to be simply N1V1 plus N2V2 divided by V1 plus V2. This is how you calculate net H positive ion concentration in the mixture. And once you get the net H positive ion concentration in the mixture, then you can easily write pH as minus log of net H positive ion concentration. And eventually you can calculate pH of the solution. Let me give you one example. Let me give you one example here. For example, let's say I'm writing a stuff like this. 100 ml of 0.1 molar H2SO4 is mixed with 100 ml of 0.1 molar NaOH. 100 ml of 0.1 molar H2SO4 aqueous is mixed with 100 ml of 0.1 molar NaOH aqueous. Calculate the pH of the mixture. Calculate the pH of the mixture. How exactly you are going to solve this? The same procedure which I have shown you. First of all, how many solutions I have? I have two solutions. Solution number 1 and solution number 2. I'm mixing these two solutions. And what do I get at the end? I'm getting a mixture. Here. So solution number 1 plus solution number 2, and here I'm getting a mixture. I need to calculate pH of this mixture. Which is minus log of net H positive ion concentration in the mixture. Right? Now understand, guys, what I'll be saying. The first solution which I have, its volume is 100 ml. Molarity of this solution is 0.1. Now tell me one thing. What is the N factor of H2SO4? If I ask you what is the N factor of H2SO4, N factor of H2SO4 has to be 2. Because H2SO4, it is going to give 2 H positives. Number of H positives an acid donates, that defines its basicity. And whatever is the basicity of the acid, that's what you call as N factor. So N factor of H2SO4 is 2. Now, my dear students, one result which I believe everyone would be knowing, normality is nothing but molarity multiplied by N factor, right? So normality of first solution will be molarity of first multiplied by N factor of first. What is molarity here? 0.1. What is N factor? 2. So 0.1 into 2 comes out to be 0.2 only. So this is the normality of the first solution. Correct? Right? Similarly here in this particular case, volume here is given to me as 100 ml. Molarity of this solution is given to me as 0.1. Right? Since N factor of this NaOH would be 1. Molarity multiplied by N factor, that gives me normality. So normality is equal to this multiplied by this, which will be 0.1. Okay. So, if I ask you, what would be the net H positive ion concentration in this mixture? You'll use a simple result which I gave you. N1V1 plus N2V2 divided by what? Divided by V1 plus V2. Now, what is N1 into V1? N1 multiplied by V1. This multiplied by this comes out to be 20 plus N2 multiplied by V2. N2 multiplied by V2 comes out to be 10 divided by V1 plus V2. 100 plus 100 makes it 200. So the value is simply going to be 30 divided by 200. So it is nothing but 3 divided by 20 molar. This is the net H positive ion concentration in the solution. If this is the net H positive ion concentration in the solution, so can't I calculate pH from here? pH of the solution? I mean pH of the final mixture. pH of the final mixture is minus log of net H positive ion concentration in the mixture, which is going to be minus log of, what is the net H positive ion concentration? 3 by 20. Right? It is going to be 3 divided by 20. I believe I'm clear with this. I believe I'm clear with this, right? So guys, it is going to be minus log of m by n is going to be log of m minus log of n. So minus times. What is log 3? 0.47. What is log 20? Log 20, when you solve, it comes out to be 1.3, right? It comes out to be 1.3. So 1.3 minus 0.47 would be approximately how much? 1.3 minus 0.4 would be 0.9. So it's going to be 0.83. So this is the pH of the final solution. Am I clear with this, guys? Am I clear with this? Say it in the chats quick. Say it in the chats. Sir, but NaOH is a strong base. Oh, wait. Sorry. What am I doing? Wait. This is HCl here. Sorry. This is HCl here. This is HCl here. Okay. Oh. Big blunder it was. Strong acid. I'm mixing two strong acids, right? This is not NaOH, guys. This is HCl. Be careful with it, okay? Clear, guys? Is it clear? Is it clear? Let me know in the chats quick. Anyways, n factor of HCl is also 1. So nothing needs to be changed in the calculation. Calculation is proper. It is just, I thought it was HCl written, but I don't know how come I wrote NaOH here. So this was the calculation of pH of a mixture containing two strong acids, right? Now, how many cases are we done with? 3 cases. Fourth case is going to be pH of a mixture containing two strong bases. pH of a mixture containing two strong bases. pH of a mixture containing two strong bases. Now, how do I solve this? For example, I've got an aqueous solution of some strong base 1. I've got one more aqueous solution of a strong base 2. Okay. I've got an aqueous solution of strong base 1, and at the same time, I've got, for example, an aqueous solution of strong base 2. Now, for example, I'm mixing them up. When I mix them up, what do I get? I'll be getting a mixture. I'll be getting a mixture of strong base 1 plus strong base 2. I got the mixture of strong base 1 plus strong base 2. What do I need to calculate? I need to calculate pH of this mixture. How do I calculate it? See, guys. For example, normality of this solution is N1, volume is V1. Normality of this solution is N2, volume is V2. So first of all, the final mixture over here, is it going to be acidic or basic? The final mixture is going to be basic in nature. Its pH has to be what? It has to be greater than 7. Now, my dear students, what do I need to do here? See, since the final solution is basic in nature, so what I'll be doing, I'll be calculating the total OH negative ion concentration in the final solution, which is going to be again N1V1 plus N2V2 divided by V1 plus V2. And once I get the OH negative ion concentration here, I will be calculating POH. P stands for minus log of what? OH negative here, right? And once I get POH from here, then you know pH plus POH at 25 degrees centigrade is 14. So from this particular equation, you can exactly calculate pH of the solution. This is the process which you'll be following. Yeah? For example, let me give you one question. Let me give you one question. Let's say similar question. 100 ml of 0.1 molar NaOH aqueous is mixed with 100 ml of 0.1 molar BaOH whole twice aqueous. Calculate pH of the mixture. Calculate pH of the mixture. First of all, try to analyze one thing. It is a strong base. This is also a strong base. So, when we mix them, we have got a mixture of two strong bases. We have got a mixture of two strong bases. Now, how do we calculate pH of the mixture of two strong bases? You know it already. Have a look. What is the volume of the first solution? 100 ml. What is the molarity of this particular solution? 0.1. What about the N factor of NaOH? N factor of NaOH is 1. So, normality of the first solution is equal to molarity multiplied by N factor. So, 0.1 into 1 comes out to be 0.1 only. Correct? Similarly, go for the second solution. Its volume is 100 ml. Its molarity is 0.1. N factor of BaOH whole twice is 2. So, normality of the second solution is molarity multiplied by N factor, 0.2. Correct? Now, since we are mixing two strong bases, so in the final mixture, what would be the net OH negative ion concentration? In the final mixture, it's going to be N1V1 plus N2V2 divided by what? Divided by V1 plus V2. Now, what is N1V1? N1 into V1, 100 into 0.1 is 10 plus N2V2, 0.2 into 100, that's 20, divided by V1 plus V2, that's 200. So, it is again 30 divided by 200, which is nothing but 3 divided by 20 molar. This is the net final OH negative ion concentration in the mixture. If this is the net OH negative ion concentration in the mixture, what can I calculate? POH. P stands for minus log. Minus log of what? Net OH negative concentration. So it is minus log of 3 divided by 20 and minus log of 3 by 20. Few minutes back only we solved this. Minus log of 3 by 20 comes out to be how much? 0.83. Is it? Yeah, 0.83. So if it comes out to be 0.83, I can now calculate pH of the solution, which is 14 minus POH. So it is going to be 13.17. This is the pH of the final solution. Do you understand this? Do you understand this, guys? Do you understand this? So this was our case number 4. I'll show it's more questions in some time. Okay, case number 4. Now, let me move on to case 5. This is important. Case 5. That is mixing of strong acid and strong base. Mixing of strong acid and strong base. Understand, guys, and remember things. For example, I've got an aqueous solution of a strong acid, and at the same time, I've got an aqueous solution of strong base. These are the two solutions which I have. Aqueous solution of strong acid, aqueous solution of a strong base. Let's assume its normality is N1, volume is V1. Let's assume normality of this solution is N2, volume is V2. Now, for example, you're mixing them. Now, people, when you mix them, what do we get? What do we get? It's common sense. You're mixing acid and base. When you mix acid and base in the container, what will happen? Acid will react with base and will form salt and water. And will form salt and water, right? Will form salt and water. This acid is going to react with this base and will form salt and water here. Perfect? It is going to form salt and water here. Now, guys, understand. Understand. The mixture which we get here, we need to calculate its pH. We need to calculate its pH. Okay. Now, here comes the first case. If N1V1 will be equal to N2V2, that means if equivalence of acid will be equal to equivalence of base, equivalence of acid will be equal to equivalence of base. That means this is the case of complete neutralization. This is the case of complete neutralization. And in case of complete neutralization, at 25 degrees centigrade, pH of this mixture would be what? It would be 7. The resulting solution is going to be neutral. If the equivalence of acid and equivalence of base, if N1V1 is equal to N2V2, if equivalence of acid and equivalence of base are equal, so this is going to be the case of complete neutralization, wherein all the acid and all the base, they would have reacted and formed salt and water. So in the final solution, there will be only salt and water present. There will be no acid, no base. Because all the acid, all the base, they would have reacted and formed salt and water. There will be no acid left, there will be no base left. Right? So the resulting solution would be neutral at 25 degrees centigrade. Yes? Now, you are going to answer me this. If, for example, if N1V1 is greater than N2V2, if equivalence of acid are more than that of equivalence of base, if equivalence of acid are more than that of equivalence of base, so I would say in the final solution, there would be salt, there would be water, and there would be some acid left as well. If equivalence of acid would be equal to equivalence of base, if equivalence of acid is greater than that of equivalence of base, so that means base would have completely reacted. In the final solution, there will be some amount of acid left as well. So what do I need to calculate? I will be calculating the net H positive ion concentration in the final solution, which will be equal to more equivalence minus less equivalence, N1V1 minus N2V2 divided by what? Divided by V1 plus V2. This is how you calculate net H positive ion concentration in the mixture. And once you calculate net H positive ion concentration in the mixture, you can just multiply this with minus log. You'll be getting pH. And pH over here would come out to be less than 7 because the final solution is going to be acidic in nature. Right? Right, people? Sir, when will you be completing thermochemistry? Thermochemistry video I posted 4 days back. Go to the video category and check it. Okay? That's why I tell you to join the Telegram channel. Perfect, guys. Now, the third case here. If, for example, if N2V2 are greater than N1V1, tell me what will happen now. So, equivalence of base are greater than that of equivalence of acid. So, when they mix, what would happen? First, salt and water would get formed. Apart from that, there would be some base left in the container. So, if I want to calculate net OH negative ion concentration in the mixture, it is going to be equal to more equivalence minus less equivalence. More is N2V2. N2V2 minus N1V1 divided by V1 plus V2. This is how you calculate net OH negative ion concentration right now. And once you calculate OH negative ion concentration in the mixture, then you can calculate pOH. And once you calculate pOH, you can eventually calculate pH. Right? And pH here in this particular case will be greater than 7 at 25. And the resulting solution is going to be basic in nature. These are the 3 things which you have to remember. That's all. That's all, people. Correct? Now, let's exactly see certain questions so that you'll understand all this stuff. Have a look. For example, 100 ml of 0.1 molar HCl is mixed with 100 ml of 0.1 molar NaOH. Right? Calculate the pH of the mixture at 25 degrees centigrade. A simple and basic question I'm giving you. Simple and basic question. Okay, this is the first question. You give it a try till then. Till then, I'll write one more question here. You give first question a try and let me know the answer in the chats. Can you solve them? What is going to be the pH of the first solution, guys? What would be the pH of the first solution? Quick. What would be the pH of the first solution? This is something which you should be able to solve, guys. It's a simple one. It is a simple one. You should be able to solve this. See, strong acid, strong base. Strong acid, strong base. V1 is 100 ml. Molarity of this solution is 0.1. Normality of this solution would be also 0.1 because its n factor is 1. Molarity into n factor is equal to normality. Second one. Second solution. Volume of second solution is 100 ml. Right? Molarity of the second solution is 0.1. Right? So normality of the second solution is molarity multiplied with its n factor. Its n factor is also 1, so 0.1. Okay. Do you see N1 into V1? What is the value of N1 V1? Value of N1 into V1 is going to be 10. Value of N2 V2 is also going to be 10. So if N1 V1 is equal to N2 V2, so this is the case of complete neutralization, and at 25 degrees centigrade, its pH has to be 7. Correct? Look at the next one now. This is strong acid. This is strong base, right? Its volume is how much? 100 ml. Its molarity is 0.1. So its normality would be, normality is equal to molarity into n factor. N factor of H2O is 2. So 0.1 into 2 is equal to 0.2. Look at the second solution. Volume of second solution is 100. Molarity of the second solution is 0.1. So normality of the second solution is equal to molarity multiplied with its n factor. Its n factor is 1. So it's 0.1. So whose equivalents are more, acid or base? Let's check that. What is the value of N1 into V1? N1 into V1 value is 20. What is the value of N2 multiplied by V2? N2 multiplied by V2 is 10. So I would say equivalents of acid are more. If equivalents of acid are more, that means the resulting solution, final solution is going to be acidic, and net H positive ion concentration in the final solution would be equal to more equivalents minus less equivalents. So 20 minus 10 divided by V1 plus V2. 100 is 200. So it is 10 by, it is going to be 10 by 200, which means 1 by 20 molar. This is the concentration, net H positive ion concentration in the final solution. If this is the net H positive ion concentration in the final solution, if this is the net H positive ion concentration in the final solution, therefore pH has to be equal minus log of net H positive ion concentration. When you solve this, the value comes out to be how much? This will be log 1 minus log 20. Log 1 is 0. Log 20 is 1.3. So 1.3 is the pH of the final solution. I believe all these things you can easily solve. Yeah? I feel this next question you can do on your own, right? First of all, check whose equivalents are more. And over here in this particular case, equivalence of base would be more. So resulting solution is going to be basic. So for example, what I'm trying to say is, see, V1 here, volume of the first solution is 100 ml. Molarity of this solution is equal to 0.1, right? So its normality would be equal to molarity multiplied by n factor of HCl is 1. So 0.1. Similarly, volume of second solution is 100 ml. Sorry. Molarity of this second solution is equal to 0.1. So normality of the second solution is equal to molarity multiplied by its n factor. Its n factor is 2. So 0.1 multiplied by 2 is 0.2. Right? Now, whose equivalents are more? N1 V1 value. N1 V1 comes out to be 10. N2 V2. N2 V2 comes out to be 20. So I would say equivalents of base are more. So resulting solution is going to be basic. So calculate the net OH negative ion concentration in the final solution, which is more equivalents minus less equivalents. More equivalents minus less equivalents divided by total volume is 100 under 200. The value comes out to be 1 upon 20 molar. So this is the net OH negative ion concentration. If this is the net OH negative ion concentration, we can calculate POH minus log of net OH negative ion concentration in the container, which is minus log of 1 by 20, which comes out to be 1.3, right? So this is POH. But am I supposed to calculate POH? No. I'm supposed to calculate pH, which is 14 minus POH. The value comes out to be 12.7. So 12.7 is the pH of the final solution. I believe this is clear to every one of you. If yes, let me know once in the chats quick. Let me know once in the chats quick, guys, if it is clear. Let me know once in the chats quick if it is clear. Let me know once in the chats quick if all of this stuff is clear till now. Yeah? All right, look at this question. So before solving this question, if I tell you pH of solution is 2, if I say something like this, pH of the solution is 2, tell me what would be the H positive concentration of the solution. You would say H positive concentration is equal to 10 raised per minus 2 molar, right? Because if pH is equal to X, what does that mean? That means concentration of H positive in the solution is 10 raised per minus X molar. Correct? Similarly, if I say pOH of the solution is X, that means OH negative ion concentration in the solution is 10 raised per minus X molar. Correct? Correct, people? Yeah? Now, look at this particular question. This you should be able to solve on your own. You've got two strong acids. You're mixing two strong acids. You're mixing two strong acids. Let's say the first strong acid is HA1. The second strong acid is HA2. These are the two strong acidic solutions which you are mixing. Volume of this solution is 50 ml. Its pH is given to me as 1. If pH is equal to 1, that means H positive concentration in this solution is 10 raised per minus 1 molar. Right? Okay, simple. Similarly, HA2. This is again monoprotic. I'm assuming the acids to be monoprotic. Right? Second solution. Its volume is how much? Volume of the second solution is 50 ml. pH of this second solution is 2. So H positive ion concentration in the second solution is how much? It would be 10 raised per minus 2 molar. This is something which is given. Now you are mixing them. When you are mixing them, you will be getting a mixture of two acids, two strong acids. You got a mixture of strong acid 1 plus strong acid 2. You got a mixture of strong acid 1 plus strong acid 2. Now what I'm supposed to calculate? I'm supposed to calculate the net H positive ion concentration here. Once I calculate it, then I'll be calculating pH, which stands for minus log of H positive net. Right? This is my procedure which I'll be following. Now guys, one thing. HA1 is a strong acid. HA1 is a strong acid. So in aqueous, in water, it would have dissociated completely as H positive plus A1 negative. This is how it would have dissociated, right? They are mentioning that concentration of H positive in this solution, concentration of H positive in this solution is equal to 10 raised per minus 1, right? So if the concentration of H positive in the solution is 10 raised per minus 1, therefore the initial concentration of acid should have been 10 raised per minus 1, because initially this would have been 0, this would have been 0. Now this 0, 10 power minus 1, 10 power minus 1. This should have been the case. This should have been the case. If the concentration of H positive here in the first solution is 10 raised per minus 1, that means the initial concentration of the acid should have been 10 raised per minus 1. I hope you're understanding this, right? So I would say initial concentration of HCl, or I would say it's something like this. Molarity of the solution, molarity of the HCl solution is equal to 10 raised per minus 1. Therefore, normality would be equal to molarity multiplied by N factor. N factor of this monoprotic acid is 1, because it's going to give only 1 H positive. So it's 10 raised per minus 1. Correct? Similarly, molarity of this would be 10 raised per minus 2. And its normality would be how much? 10 raised per minus 2 only. Now, net H positive ion concentration. Two strong acids. N1V1. N1 multiplied by V1. So 50 multiplied by 0.1. 50 multiplied by 0.1. 50 multiplied by 10 raised per minus 1 is 5. Plus N2V2. N2 and V2. This multiplied by this would be how much? Would be 0.5. N1 plus N2 V2 divided by V1 plus V2. V1 plus V2, 50-50 is 100. So the value is going to be 5.5 divided by 100 molar. This is the net H positive ion concentration. If you got the net H positive ion concentration minus log of 5.5 divided by 100, which is going to be minus log of M by N, is log of M minus log of N. N is 100, 100 means 10 ka square, right? As per the question, log of 5.5 is given. How much? 0.74. Log of M raised per N, right? Log of M raised per N is N log M. So minus 2 comes to the front. The value comes out to be 1.26. This is the pH of the final solution. If this is clear, let me know once in the chats. Simple. Let me know once in the chats if all the stuff is clear. Let me know once in the chats if all this stuff is clear, guys. Quick. How many cases have we discussed till now for pH calculation? Just let me check. We have 5 cases we have discussed. Moving on to the 6th case. Moving on to the 6th case. What is that? That is pH of a weak. pH of a weak monoprotic acid. pH of a weak monoprotic acid. So till now, whatever acids and bases I have taken, all the acids bases were strong. All the acids bases were strong. Now, I'm going to take a weak monoprotic acid. For example, understand. Let's say I've got a weak acid HA. Let's say it's a weak acid. If it is a weak acid, when you introduce this in water, weak acid means weak electrolyte. It is going to remain in equilibrium with its ions. Ions are H positives and A negatives. Correct? Let's say initially its concentration is C, 0, 0. Degree of ionization is alpha. So at equilibrium, concentration of this acid should be C minus C alpha. This should be C alpha. This should be C alpha. As simple as that. Now guys, if I want to write the expression of Ka, dissociation constant of this weak acid, how much it's going to be? It's going to be C alpha square divided by 1 minus alpha. Right? It's going to be C alpha square divided by 1 minus alpha. Now if I make certain assumptions, let alpha is less than 0.05. At that point of time, instead of 1 minus alpha, we are just going to write 1. So Ka comes out to be equal to C alpha square, or I would say alpha comes out to be equal to under root of Ka by C. This is the value of alpha here. This is something which we have discussed long back. This is the value of alpha here. Now, if this is the value of alpha, just try to understand one thing. Just try to understand one thing. I have introduced weak acid in water. So for example, I've got a container which was filled with water. Now we have introduced weak acid. This weak acid, it has got some percentage of it has got dissociated into its ions, H positives and A negatives. So in the solution, there are H positives. In the solution, there are H positives, right? What do I need to calculate? pH of the solution, pH of the weak acidic solution. And pH of the solution is what? Minus log of H positive concentration. So first of all, I need to calculate the H positive concentration in the solution. I need to calculate H positive concentration in the solution. And as you can see, H positive concentration in the solution is nothing, that is C alpha. So it has to be equal to C. Alpha is under root of Ka by C. Under root of Ka by C. Or it is going to be Ka. C inside means C square. C cancelled. So K into C is going to be the concentration of H positive. So I would say concentration of H positive in the solution is Ka multiplied by C whole raised power 1 by 2. This is how you can calculate concentration of H positive in the solution. And once you calculate concentration of H positive in the solution, then you can calculate pH. How exactly? Minus log of H positive concentration. So minus log of, what is the H positive concentration here? This is Ka multiplied by C whole raised power 1 by 2. Right? So here I am going to derive a result basically, which is going to ease out a lot of things. Log of M raised power N, which is N log M. So 1 by 2 comes to the front. Then log of M into N means the log of M plus plus log of n. So I would say pH is equal to 1 by 2. Take this minus inside. This is minus log of Ka minus log of C. So I would say pH is equal to half of minus log of Ka means P of Ka minus log of C. This is the result which is used to calculate pH of a weak monoprotic acid if its alpha is less than 0.05. This is the result which I would want you guys to remember. This is the result which I would want you guys to remember. pH of a weak monoprotic acid, it is always equal to half of pKa minus log C. But this result of pH calculation is valid only if alpha value of the weak acid is less than 0.05. I would want you guys to remember this result. I would want you guys to remember this result. Okay? Am I clear with this? Yeah? Perfect. I'll show its example in some time. First, I need to show you one more thing. pH of a weak base of the type BOH. pH of a weak base, calculation of pH of a weak base of the type BOH. For example, imagine you have got a weak basic solution. How do you calculate pH of that? How do you calculate pH for that? Again, it's similar. Imagine you have taken a weak base as BOH, introduced this in water. So it is going to remain in equilibrium with its ions. Ions are B positive aqueous and OH negative aqueous. Right? BOH, a weak base, you have introduced in water. Now this weak base is in equilibrium with its ions. So initially its concentration C, 0, 0. Degree of ionization alpha. So this is C minus C alpha and C alpha. Right? Now, if you write the expression of Kb, dissociation constant of the weak base, it has to be equal to C alpha square divided by 1 minus alpha. Again, I'm assuming let alpha is less than 0.05. Therefore, instead of 1 minus alpha, I can write 1. So Kb here will be equal to C alpha square, and alpha comes out to be equal to under root of Kb divided by C. This is alpha. Now, since you have introduced weak base in water, right? Some part of this weak base has got dissociated into its ions. Ions are what? Ions are B positives and OH negatives. So in the solution, there will be OH negative ions. If I ask you, what would be the concentration of OH negatives in the solution? You will say it is nothing but C alpha. So OH negative concentration in the solution is C. Alpha is under root of Kb divided by C, right? Which can be written as root of Kb multiplied by C, or you can write it simply as Kb multiplied by C whole raised power 1 by 2. This is the OH negative concentration in the solution. If you got the OH negative ion concentration in the solution, then you can calculate POH, which stands for minus log of OH negative concentration. So minus log of what? Minus log of OH negative. OH negative is Kb multiplied by C whole raised power 1 by 2. So when you elaborate it, again you will get the result, a similar result like we got for weak acids. That was pH is equal to half of pKa. Now here we'll be getting POH is equal to half of pKb minus log of C, where C is the concentration of the base. But this particular result, which is used for the calculation of POH, it's only valid if alpha for the weak base is less than 0.05. Do you understand? Do you understand, people? Quickly, let me know once in the chats. Do you understand all this stuff? Let me know quickly in the chats if this is super clear. Yeah? Perfect. Now, let's try to solve few questions so that you'll understand all this stuff. Let's solve some basic questions which are of your NEET standard. Right? For example, you have got a question like this. Calculate the pH of 0.1 molar CH3COH if Ka is equal to 1.8 into 10 raised power minus 5. First of all, understand. Check whether the substance given, is it a weak acid or strong acid? I've told you in the beginning itself, CH3COH is a weak acid. So we have to calculate pH of the weak acidic solution. Now, first of all, I'll be checking its alpha value. Its alpha is equal to under root of Ka by C. Right? Under root of Ka value is 1.8 into 10 raised power minus 5. C is how much? Concentration, 0.1. Root of 1.8 is 1.34. And finally, it will be 10 raised power minus 2, which is less than 0.05. So we can use the formula directly. We can use the formula. We have checked its alpha value, which is coming out to be less than 0.05. So we can use the formula directly for the pH calculation. Formula you know. Formula you know. pH of the weak acid is equal to half of, it is P of Ka minus log of C. Right? So it's half of. P stands for minus log. One thing which I would want you guys to remember from now onwards. Remember guys, minus the log of 1.8 into 10 raised power minus 5. No need to solve this value again and again. Remember this for once and all. It's always equal to 4.74. Right? So P stands for minus log. P stands for minus log. Minus log of 1.8 in 10 raised power minus 5 would be 4.74 minus log of C. C is the concentration of acid. That's 10 raised power minus 1. So it is going to be half of 4.74 minus log of m raised power n is n log m, so plus 1. Right? So it's going to be half of 5.74. Half of 5.74. So 2.87 is the pH of the solution. Is it clear? Nothing to worry, right? So these sort of questions are asked. These sort of questions are asked in your examination. But be careful with one thing. You have to check whether alpha is less than 0.05 or not, because this formula is valid or only, this formula is valid only when alpha is less than 0.05. And for those solutes where alpha is more than 0.05, they are not normally asked in your NEET examination. They'll always give alpha less than 0.05 on. Okay? Don't worry about other things. Don't worry about the other things. I hope I'm clear with this stuff. All right? All right, people? Okay, what if alpha was greater than 0.05? Still, let me show it to you. Maybe, who knows what comes in the exam. Generally, they don't ask those questions, but still, what if they come up with that question and you will be done and dusted? For example, the question is calculate the pH of 10 raised power minus 6 molar CH3COH aqueous if Ka for acetic acid is equal to 1.8 into 10 raised power minus 5. Right? See guys. First of all, CH3COH. It's a monoprotic acid, weak monoprotic acid. It's a weak monoprotic acid. If it is a weak monoprotic acid, then check its alpha first of all. Alpha has to be equal to under root of Ka by C. Under root of Ka divided by C. Ka is going to be equal to 1.8 into 10 raised power minus 5. C value is how much? 10 raised power minus 6. So it comes out to be root of 18, which is not less than 0.05. Not less than 0.05. So what do I do here? I cannot use the formula. So if I cannot use the formula, what am I supposed to do? If I cannot use the formula, then what am I supposed to do? I'll follow the general procedure. How exactly I'll be following the general procedure? Have a look, guys. CH3COH. When you introduce this in water, partially ionized, It remains in equilibrium with its ions. Ions are CH3CO negative and H positive. Correct? Let's say its initial concentration as per the question is 10 raised power minus 6 molar. This is 0, this is 0. Degree of ionization alpha. So at equilibrium, this has to be C minus C alpha. This has to be C alpha. This has to be C alpha. Now, if I write the expression for Ka, Ka is nothing but C alpha square divided by 1 minus alpha. Now, if I ask you, can I neglect alpha here? I cannot neglect alpha. Because alpha value is not less than 0.05. I cannot neglect alpha. So what am I supposed to do? If you remember in the beginning, I told you, when alpha is not less than 0.05, at that time, you will have to make a quadratic equation and solve that, right? How do you get the quadratic here? See, Ka value, as per the question, is how much? 1.8 into 10 raised power minus 6 is equal to C value. What is C? C is 10 raised power minus 6. Alpha square. Sorry, this 1.8 into 10 raised power minus 5. C alpha square divided by 1 minus alpha. So, this becomes 1.8 is equal. This becomes 10 raised power minus 1, which can be written as alpha square divided by 10 multiplied by 1 minus alpha. Okay. Now just cross multiple things. When you cross multiple things, it is going to be 1.8, sorry, not 1.8. 1.8 into 10 is 18. 18 into 1 is 18. 18 minus 18 alpha is equal to alpha square. So here you can make the quadratic. Alpha square plus 18 alpha minus 18 is equal to 0. Now since you got the quadratic, here you will have to solve this quadratic equation with the help of quadratic formula. Minus b plus minus b square minus 4ac by 2a root, right? So here you will be getting the alpha value. And once you get the alpha value, then you are going to calculate the concentration of H positive in the solution, which is C into alpha. C value is given to me as per the question. Alpha value you would have calculated from here. So get the H positive concentration. If you got the H positive concentration, you will be calculating pH minus the log of H positive concentration. Just tell me whether you got to know how to do this calculation. This is one of the cases which might be asked. Probability is very, very, very low, but still, maybe if they come up with this sort of equation, you should be in a position to solve this. Yeah? Right? All right. Can you solve this sort of equation? Check it out. Achha, let me tell you one more thing. Whenever you are given with a substance, any substance, CH3COH, whatever, NH4OH, whatever, whenever you are given substance, if Ka is given for the substance, if Ka is given for the substance, that means the substance is first of all acid. And which acid? Weak acid. Which acid? Weak acid. If Ka for the substance is given or to be calculated, if Ka is given or to be calculated, then the substance is weak acid. If Kb for the substance is given or to be calculated, that means the substance is base. And which base? It's a weak base. So the substance whose Ka or Kb is given, that is weak. That's weak. Remember that. Remember that. Now, look at the question. Now look at the question. Now look at the question. Calculate the pH of 0.01 molar RNH2 whose Kb is given. Kb is given. Do you see Kb is given? Kb is given means we are given with a weak base. We are given with a weak base, right? You are putting this weak base in water, which is remaining in equilibrium with its ions. How do we calculate pOH of a weak base? If you remember, pOH of a weak base is nothing but half of P of Kb minus log of C. Minus log of C. This is the formula. But first of all, this formula is valid only when alpha is less than 0.05. So let me first of all check whether the alpha for this weak base is less than 0.05 or not, right? So first of all, calculate alpha. Alpha has to be equal to under root of Kb divided by C. Under root of what is Kb? 2 into 10 raised power minus 6. C is the concentration of this base, that is 10 raised power minus 2. So this is root of 2 into 10 raised power minus 4. Root of 2 is 1.4 into 10 raised power minus 2. So it is 0.014, which is less than 0.05. Correct. That means I can use the formula. That means I can use the formula for the POH calculation. POH is equal to half of P of Kb. P of Kb means minus log of Kb. Kb here is 2 into 10 raised power minus 6 minus log of C. C is the concentration of the weak acid, which is 10 raised power minus 2. Now a bit of calculation is needed. So it is half of log of m into n. Log of m into n. Log m plus log n. So log 2 plus what? Plus log of 10 raised power minus 6. And here it's minus log of 10 raised power minus 2 as such in the question. Now a bit of calculation. POH has to be equal to half of log 2 is 0.3. This minus 6 comes to the front. So it is 5.7. Right? It will be 5.7. So it is going to be 5.7. This minus 2 comes to the front. So plus 2. So it is 7.7 divided by 2. The value is 3.23 are 6. 2, 8, 16, 3.85. So POH of the solution is 3.85. If POH is equal to 3.85, therefore pH is equal to 14 minus POH, right? Which will be how much? 10.15. This is the pH of the solution. Am I clear with this stuff? So this was how you calculate pH of your weak acids or weak bases. Okay. Now guys, there is one more thing. That is the relative strength of two weak acids. For example, you have got two weak acidic solutions in two containers. Container number 1 contains a weak acidic solution. Container number 2 also contains one more weak acidic solutions. So both the acids are weak. Both the acids are, for example, weak. But comparatively, one acid will be stronger than other. Comparatively, one acid would be stronger than other. How do you compare the acidic strengths of two weak acids? How do we compare the acidic strengths of two weak acids? That is the point now. See what it's all about. Imagine, guys, this is one of the containers which I'm taking, and this is one more container. I have got two containers here, for example. I've got two containers. This container, imagine it's filled with water. Now, in that water, you are introducing a weak acid HA1. And this weak acid, it's going to remain in equilibrium with its ions. Ions are H positive aqueous plus A1 negative aqueous. These are its ions. Similarly, you have got one more weak acid as HA2. If this is HA2, it's going to remain in equilibrium with its ions. Ions are H positive aqueous plus A2 negative aqueous. Right? Let's say its initial concentration was C1. Degree of ionization is alpha 1. So this is 0, this is 0. Now at equilibrium, it is C1 minus C1 alpha 1. This would be C1 alpha 1. This would be C1 alpha 1. Similarly, let's say its initial concentration was C2, 0, 0. Degree of ionization alpha 2. So at equilibrium, it is C2 minus C2 alpha 2. This is C2 alpha 2. This is C2 alpha 2. Okay. Guys, tell me one thing. What is the concentration of H positives in the first container? C1 alpha 1. Concentration of H positives coming from, in the second container, C2 alpha 2. Okay. Let me first of all tell you, strength of an acid, it is directly proportional to the number of H positives coming from acid. Strength of acid, it is directly proportional to the concentration of H positives coming from acid. So if I ask you, how many H positives are coming from the first acid? How many H positives are coming from HA1? That is C1 alpha 1. How many H positives are coming from the second acid? HA2. It is going to be C2 alpha 2. It's going to be C2 alpha 2. Now, strength of acid is directly proportional to concentration of H positives coming from acid. More the H positives coming from the acid, more the H positives coming from the acid, stronger is going to be the acid, right? So if strength of acid is directly proportional to H positive concentration, I'll say strength of acid 1 divided by strength of acid 2 will be equal to, strength of acid 1 will be H positives coming from acid 1, H positives coming from HA1 divided by strength of acid 2, concentration of H positives coming from HA2. From HA1, it is C1 alpha 1. From HA2, it is C2 alpha 2. Now guys, one more thing. C1. Alpha 1 has to be equal to what? Under root of Ka1 by C1. Alpha 2 has to be equal to under root of Ka2 divided by C2. Perfect. Or you can write it finally like this. Under root of Ka1 C1 divided by Ka2 C2. Divided by Ka2 C2. Divided by Ka2 C2. So from now onwards, just remember one thing. Whenever you are supposed to check, whenever you are supposed to compare the strengths of two weak acids, whenever you are supposed to compare the strengths of two weak acids, remember, strength of weak acid 1 divided by strength of weak acid 2 will be directly equal to C1 alpha 1 divided by C2 alpha 2 or under root of Ka1 C1 divided by Ka2 C2. For example, if C1 value, alpha 1 value, C2 as well as alpha 2, if all these four parameters are given, if all these four parameters by chance are given, so you'll be putting all these four parameters in this expression. Let's say you are getting the value after solving S3. Let's say you are getting the value after solving S3. What does that mean? That means I got the value of strength of acid 1 divided by strength of acid 2 is equal to what? Is equal to 3. What does that mean? That means acid 1 is 3 times stronger than acid 2. That means strength of acid 1 is 3 times the strength of acid 2. So acid 1 is 3 times stronger than acid 2. That's how you basically compare the strengths of two weak acids, right? Now similarly, if Ka1 C1 is given, Ka2 C2 is given, put the values, put the Ka1 C1, Ka2 C2 and get the value, and accordingly you can check, you can say which weak acid is comparatively more stronger. Yeah? May I come in, sir? No. You're not welcome. Yeah. Did you understand this, people? Did you understand this stuff? Let me know once in the chats quick. Did you understand this stuff? Everybody. If this is clear, let's have a look on one more case of pH. What is that? That is the pH of a mixture. pH of a mixture containing. One is asking when will be the dinner break. Dinner break will be at 10:30. Okay. Dinner break will be at 10:30 for everybody, for me also. Wait. pH of a mixture containing two weak acids. pH of a mixture containing two weak acids. How do we do it? How do we do it? pH of a mixture containing two weak acids. For example, understand something like this. Let's say we have got a weak acid as HA1. One more weak acid as HA2. How many weak acids we have? Two weak acids, right? Now, when you introduce this in water, it will get ionized as H positive and with this A1 negative. Similarly, when you introduce this in water, what do we get? You get H positive and A2 negative. And A2 negative. Okay? Its initial concentration C1, 0, 0. Degree of ionization alpha 1. So at equilibrium, C1 minus C1 alpha 1. This is C1 alpha 1. This is C1 alpha 1. This is in the beginning, C2, 0, 0. Degree of ionization alpha 2. C2 minus C2 alpha 2. This would be C2 alpha 2 and this would be C2 alpha 2. For example, both these weak acids are present in the same container. Imagine both these weak acids are present in the same container. Imagine both these weak acids are present in the same container, right? So I am getting a mixture of two weak acids. I'm getting a mixture of two weak acids. If I'm getting a mixture of two weak acids, in order to calculate pH of the mixture, what do I need? I need H positive concentration in the mixture. I need the H positive concentration, total H positive ion concentration in the mixture. Now, if you ask me how to calculate the total H positive ion concentration in the mixture, I would say H positives are coming from this acid as well as H positives are coming from this acid. So concentration of H positives coming from this acid is C1 alpha 1. And concentration of H positives coming from this acid is nothing but C2 alpha 2. So this will give you the total H positive ion concentration in the mixture. And once you get the total H positive ion concentration in the mixture, you just have to multiply that with minus log. You will be getting the pH of the solution. Number one. Number two, there is one more way of calculating the net H positive ion concentration in the mixture. I'm not deriving the result, I'm giving you directly. Under root of Ka1C1 plus Ka2C2. This is one more expression which you can use to calculate the total H positive ion concentration in the mixture. And once you calculate total H positive ion concentration in the mixture, just multiply it with minus log, get the pH of the final solution. I believe it's clear. I believe it's clear. So there are two ways by means of which you can calculate the total H positive ion concentration, net H positive ion concentration in the mixture. One can be C1 alpha 1 plus C2 alpha 2, or another one is under root of Ka1C1 plus Ka2C2. Okay? Perfect. Is it clear till here? Tell me in the chats. Okay. One more thing. Imagine you have got two weak bases. Imagine here you had OH negative, here you had OH negative. Then at that time, you would be calculating total OH negative concentration in the mixture, which is again C1 alpha 1 plus C2 alpha 2, or under root of Kb1C1 plus Kb2C2. That is valid when you have got mixture of two weak bases. And that's understood, I believe. Yeah? I believe that's understood. Can you solve this question? You should be in a position to solve this particular question. Calculate the pH. 0.1 molar formic acid mixed with 0.1 molar acetic acid. So you are given with two weak acids, formic acid, acetic acid. Concentration of both these acids is same. So C1 and C2 are same. Assume 40% of both the acids getting dissociated. So both the acids are getting 40% dissociated. So alpha 1 as well as alpha 2 for both the acids is 0.4. Right? So what do I do? Alpha 1, alpha 2 given, C1, C2 given. So net H positive ion concentration has to be equal to what? C1 alpha 1 plus C2 alpha 2. That's it. What is C1? 0.1. Alpha 1, 0.4. C2, again 0.1. Alpha 2, 0.4. 0.04, 0.04. So 0.08, which is basically 8 into 10 raised power minus 2 molar. So this is the total H positive ion concentration in the solution, final solution. If you got the total H positive ion concentration, just calculate pH now. Minus log of net H positive, which is 8 into 10 raised power minus 2. So it's going to be minus log of 8 plus log of 10 raised power minus 2. Log of 8 is 0.9. Log of 10 raised power minus 2. And log m. So minus 2 comes to the front. The value comes out to be 1.1. This is the pH of the solution. That's it. Right? I hope you understood how to calculate pH of a mixture containing two weak acids. Now, what if in a mixture one acid is strong, one acid is weak? Yeah, that can be one more possibility. What if in a mixture, pH of a mixture containing strong acid and weak acid? This can be one more case, and pH of a mixture containing strong base and a weak base. this can be one more case. And in both these cases, we are not going to discuss them. We are directly going to use common ion effect. Why is that? Let me show it to you. In both these cases, we shall be using common ion effect to calculate pH. Why is that? If you remember common ion effect, for example, I'm giving you a question directly. Just a second. Look at the question. From here, you'll understand this. pH of 0.1 molar HCl mixed with 0.1 molar CH3COH. So in the container, weak acid, strong acid. Weak electrolyte, strong electrolyte. Both having one ion common. Which is the common ion? H positive. Do you remember concentration of common ion? Concentration of common ion is decided by the strong electrolyte. So tell me what will be the net common ion concentration. It would be simply 0.1. We have discussed this in common ion effect. If you got the net H positive concentration, so pH is nothing but minus log of H positive. So pH of the solution is 1. Nothing to do with all the things. Do you understand? Do you understand this, people? Yeah? I hope this is clear. This effect we have discussed, common ion effect. Weak electrolyte, strong electrolyte, both having one ion in common. So concentration of common ion is decided by the strong electrolyte. Strong electrolyte here is HCl. HCl would have dissociated as H positive plus Cl negative. Its concentration was 0.1 molar. 0, 0. Now this is 0. This is 0.1. This is 0.1. So concentration of H positive coming from strong electrolyte is 0.1, which I mentioned here. Because we have discussed it already. Concentration of common ion is decided by the strong electrolyte. So without even solving the question, we could get the answer. And this can be now weak base, strong base. If there is weak base, strong base, both having OH negative in common. So OH negative concentration will be decided by the strong base. Once you get OH negative concentration, you can calculate POH. And once you calculate POH, we can easily calculate pH, 14 minus POH. And with this, our pH calculation is over. Now we are going to discuss salt hydrolysis, but I think salt hydrolysis we'll discuss after the dinner break. So now I'm giving you a break, dinner break, till 10:30. But I would want every one of you to be back at 10:30. Okay? I would want every one of you to be back exactly at 10:30. Thank you, Mudassir. Thank you so much. Perfect? Or let's make it 10:35, guys. Wait. Let's make it as 10:35. Since it's a dinner break. And this chapter will not take more than 3 hours more. 3 more hours and we'll be done. Thank you, Anamika. Thank you so much. Thank you so much. Perfect. Guys, I would want everyone to be back on time. Is it a promise? Is it a promise, promise? Yes? No one is going to say yes. Yeah? I know it. Perfect. Chalo, I'll be exactly back at 10:35. You guys also be back at 10:35. Okay, let's catch up. See you. So, is everyone back? Is everyone back? I'm here, I'm here, I'm here. I did not leave. I'm here. Yeah? All right. So tell me whether all the topics, whatever things we have covered till now, is every single thing clear or not? Yeah? Let me know in the chats. Let me know in the chats if all the things are clear till here or not. Let me know quickly in the chats. The chapter will be over in like 3 more hours. Not more than that. 3 more hours maximum. Maximum 3 hours. We are just left with 3 topics. Salt hydrolysis, buffer, and solubility. They are the 3 topics which we are going to cover now. Should we start then? Already? Is everyone back? Perfect. So guys, now we are going to do one more important topic of the chapter, that is the salt hydrolysis. But before covering this particular topic, before doing the salt hydrolysis, we need to cover one more basic thing. What is that? That is your just a second. Why is it not working? All right. So now, first of all, we'll be covering one more topic, that is the relation between Ka and Kb for a conjugate acid base pair. For a conjugate acid base pair. A relation between Ka and Kb for a conjugate acid base pair. So my dear students, let me first of all make you understand what is meant by the conjugate acid base pair. It's a very simple thing. For example, imagine that you have got the acid Ha, right? Imagine that you have got the acid Ha. It's a weak acid, for example. For example, it's a weak acid. If it is a weak acid, so in aqueous solution, it's going to remain in equilibrium with its ions. Its ions are H positive aqueous and A negative aqueous. So over here, I've taken a weak acid, right? In aqueous solution, it's in equilibrium with its ions. Ions are H positive and A negative. Okay? Understand, guys. Let me tell you, acid after losing H positive, this acid is getting converted into what? After losing H positive, this acid is getting converted into A negative. So this A negative here, I will be calling as the conjugate base. I will be calling it as the conjugate base of the acid Ha. So after losing H positive, acid is getting converted into A negative, and this A negative I will be calling as the conjugate base of the acid taken over here. Okay? For example, you have got CH3COH. You have got CH3COH. In aqueous solution, you know, it is going to remain in equilibrium with its ions. Ions are CH3CO negative and H positive. Now, if this is the acid, yes, after losing H positive, it got converted into CH3CO negative. So this CH3CO negative I'll be calling as conjugate base of the acid CH3COOH. So after losing H positive, whatever acid gets converted to, that species is what you call as the conjugate base. So my dear students, when you put this acid into water, it gave H positive and A negative. Now this conjugate base here, the conjugate base which is formed here, this conjugate base is going to interact, this conjugate base A negative, it is going to interact further with water. It is going to interact further with water. And since water carries, it contains your two types of ions, H positives and OH negatives, you know it. So A negative, the conjugate base, which gets formed over here, now it's going to interact with water. Now if I ask you with which ion it's going to interact with, it is going to interact with H positive, and it will lead to the formation of HA. It will lead to the formation of HA, and with this you'll be getting OH negative here, right? This H positive interacted with this, and we are left with OH negative over here as such, right? So I took acid in the beginning, right? Acid I introduced in water, right? It gave its conjugate base. The conjugate base which gets formed here, it further interacts with water, gets converted into HA and OH negative. Now, my dear students, understand one thing, one simple thing. Since I started with acid, right? If I write Ka expression for this particular weak acid, dissociation constant expression for this weak acid, it is going to be concentration of H positive raised power stoichiometric coefficient 1 multiplied by concentration of A negative raised power stoichiometric coefficient 1 divided by concentration of HA. Divided by concentration of HA. Now the conjugate base which we got over here, it is interacting with water, right? So for this particular reaction, if I write KB expression is going to be concentration of HA multiplied by concentration of OH negative divided by concentration of A negative. This H2O, it is in liquid state, and for liquids, H2 mass is equal to unity. We have got nothing to do with them. Okay. Now, if you realize one thing, just realize one thing. If we just do one thing, if we multiply Ka and Kb, let's see what do we get. My dear students, if we multiply Ka and Kb, your Ka is nothing but concentration of H positive multiplied by concentration of A negative divided by concentration of HA, right? Multiplied by, what is Kb? Kb is concentration of HA multiplied by concentration of OH negative divided by concentration of A negative. See what all things will get cancelled out. A negative cancels out. HA cancels out. So I'm left with concentration of H positive multiplied by concentration of OH negative. And I hope you remember concentration of H positive multiplied by concentration of OH negative. That's something which you call as Kw, right? So I got one general expression here, that is Ka multiplied by Kb is nothing but it is equal to Kw. And my dear students, you know, at 25 degrees centigrade, if I write the same equation at 25 degrees centigrade, then Kw value will be equal to 10 raised power minus 14. Okay. So this is one important expression. This is one important expression. Ka multiplied by Kb is equal to what? Kw. And at 25 degrees centigrade, your Kw is nothing but 10 raised power minus 14. Okay. So if I ask you one simple thing over here, I'll just ask you one simple thing. And simple thing is like this. Let's say I've taken the acid as CH3COH. Dissociation constant here is Ka. I'm taking a base, for example, NH3. Its dissociation constant is Kb. Can I write like this? Ka multiplied by Kb is equal to Kw. Is this correct? Is this the result correct here? The acid which I've taken, right? The acid which I've taken, its dissociation constant is Ka. Base I've taken is NH3. Its dissociation constant is Kb. Ka multiplied by Kb is equal to Kw. Is this right? What do you think? Is this right or wrong? This is not right. Why is that? Why is that? We have to take Kb for what? The base should be the conjugate base of the same acid. It has to be the conjugate base of the same acid, right? And NH3 is not the conjugate base of this acid. What is the conjugate base of this acid? That is CH3CO negative, right? It's not the conjugate base. Perfect. I believe I'm clear with this. Now, let's move on to our actual topic. What is that? That is salt hydrolysis. Now, my dear students, before talking about salt hydrolysis, before discussing salt hydrolysis, you should first of all know what all different types of salts do we have. You should know what all different types of salts do we have. Okay. See guys, we have got many types of salts. Number one, the first salt is called as the salt of strong acid and strong base. This is the first category of salt. How do we get the salt first of all? You know, when acid interacts with water, when acid reacts with base, it leads to the formation of salt and water. When acid reacts with a base, it leads to the formation of salt and water, right? So, the first type of the salt is what I call a salt of strong acid and strong base. For example, I've taken the acid as HCl, I've taken the base as NaOH. They are going to react. They are going to lead to the formation of salt, that is NaCl, and with this NaCl, you'll be getting water. Now, if I ask you which salt this is, you will say it is the salt of strong acid and strong base. So this is the first category of the salt which we have. Salt of strong acid and strong base, right? Second, this was point number one. Yeah, this was point number one. Point number two. Now we have got salt of weak acid and strong base as well. We have got one more category of salt, that is the salt of weak acid and strong base. For example, let's say the weak acid which I'm taking, that is CH3COOH. It's a weak acid. It's a weak acid. Strong base, for example, is your NaOH, right? It's a strong base. When they react, they will lead to the formation of salt. Which salt do you get over here? CH3COONA, and with this, you'll be getting water as well. Now, my dear students, if I ask you which salt this is, you will say simply, it is the salt of weak acid and strong base. It is the salt of weak acid and strong base, right? Similarly, my dear students, we have got the third category of salt as well. That's what you call a salt of strong acid and weak base. Salt of strong acid and weak base, right? Now, you can take any strong acid, any weak base. Let's say I'm taking HCl as the strong acid. Weak base, let's say I'm taking NH4OH. This is your strong acid and this is your weak base now. They are going to react. They will lead to the formation of salt, which is NH4Cl. And with this NH4Cl, you'll be getting water as well. Now, if I ask you which category of salt this is, you will say this is the salt of strong acid and weak base. It's the salt of strong acid and weak base. Now, similarly, my dear students, you have got the salt of weak acid and weak base as well. You have got the salt of weak acid and weak base as well. Now, what is the example of the salt of weak acid, weak base? For example, you have got CH3COOH, which is a weak acid. Let's say you have got the weak base as NH4OH. It's a weak base. Now, acid and base reacts and they will lead to the formation of salt. Salt here is going to be CH3COONH4, and with this, you'll be writing water as well. So, my dear students, if you look carefully, if I ask you which category of salt this belongs to, this is the salt of weak acid and weak base. So, how many different types of salts do we have? How many different types of salts do we have? Quick. How many different types of salts do we have? Quickly. We have got 4 different types of salts, right? Perfect. Now people, you saw these are the different types of salt which we have. Now, first of all, the topic which we have to cover, what is that? That is salt hydrolysis. What is meant by salt hydrolysis? What is meant by the term salt hydrolysis? It's simple. See, acid plus base gives salt plus water. Acid plus base gives salt plus water. If you reverse the reaction, what should I write? Salt plus water, right? Salt plus water. See guys, salt hydrolysis is basically defined as the interaction of ions of salt with water to produce either acidic or alkaline solution. The interaction of salt with water. When you introduce salt in water, the ions of salt are going to interact with water, and later on they are going to produce either acidic or alkaline solution. And that interaction of salt with water, the interaction of ions of salt with water to produce either alkaline or acidic solution, the phenomenon is called as salt hydrolysis. For example, let's say you have got the salt as AB. It's a general salt, AB. This is the cation, A positive, and this is the anion, B negative. It's the salt, for example, right? Now, if you introduce the salt in water, in water, you know, you have got two types of ions, H positives and OH negatives, right? H positives and OH negatives. Now, my dear students, we have got few possibilities here. The first possibility is, if the cation of salt interacts with water, what happens? If the cation of salt interacts with water, I would say cation is going to interact with this OH negative of water, and it's going to form what? It is going to form AOH, and with this, you'll be getting H positive here, right? So first of all, over here, I'm showing you the cation of salt has interacted with water. Perfect. And when cation of salt interacts with water, this hydrolysis is what you call as cationic hydrolysis. It's called as cationic hydrolysis. Now, there is one more possibility. The anion of salt could have interacted with water as well. Now, this anion of salt can interact with which ion? It is going to interact with H positive here, right? So, it is going to form what? It's going to form HB, and with this, you'll be getting OH negative here. Since in this particular case, I would say anion of salt has interacted with water. So, this hydrolysis I'll be calling as anionic hydrolysis, right? So, what is salt hydrolysis in general? I would say salt hydrolysis is nothing but it is defined as the interaction of ions of salt with water to produce either acidic or alkaline solution. Right? Now, if the cation of salt interacts with water, this hydrolysis I'll be calling as cationic hydrolysis. If the anion of salt interacts with water, this hydrolysis I'll be calling as anionic hydrolysis. Now, we have to discuss this hydrolysis in detail, right? Now, I'll show you one derivation, and after that, I'll be giving you direct results. Understand, guys. Understand properly what I'm going to say. Let me show you hydrolysis. Let me show you hydrolysis of a salt of a weak acid and strong base. Let me show you this case first of all. Hydrolysis of the salt of weak acid and strong base. Now, first of all, what is hydrolysis? I told you already. Interaction of ions of salt with water. Okay. Now, my dear students, the salt which we have, it can be of many types. So, the first type of the salt which I'm taking here, that is the salt of weak acid and strong base. Before doing its hydrolysis, I would want you guys to take a note of one thing. One important thing. Take a note of one thing. See, that ion of salt interacts with water. That ion of salt interacts with water. Which would have come either from weak acid or weak base. In the salt, you have got two different ions, cation and anion, right? Now, that ion of salt interacts with water, which comes from either weak acid or weak base. For example, you have got NH4Cl. It's a salt. NH4 positive, Cl negative. NH4 positive has come from NH4OH. Cl negative would have come from HCl. So since it's a strong acid, this is a weak base. So I would say this is the salt of what? This is the salt of strong acid and weak base, right? Now, when you introduce this in water, which ion of the salt is going to interact with water? That ion of salt interacts with water, which comes from either weak acid or weak base. Here you have got the weak base, right? And this is the ion which has come from the weak base. So this ion is going to interact with water right now. I hope you're getting it. Similarly, for example, you're taking CH3CONA, which is CH3CO negative, Na positive. CH3CO negative is nothing but it has come from CH3COH. Na positive has come from NaOH, right? So this is weak acid, this is strong base. Perfect. So over here you've got two ions. One of the ion has come from weak acid, one of the ion has come from strong base. Now when you introduce this in water, which ion of salt is going to interact with water right now? That ion of salt interacts with water which comes either from weak acid or weak base. Here you have got the weak acid. So this ion of the salt is going to interact with water. Remember this. Okay? Remember this. So in the salt, the weak component basically. Weak component is the one which has come from either weak acid or weak base. The weak component is going to interact with water. Now, let's see the salt hydrolysis of the salt of weak acid and strong base. What is the example of the salt of weak acid and strong base? The one of the example is going to be CH3COONA. Okay, this is the salt which I'm taking. Now, my dear students, understand what I'm going to say. First of all, when you introduce the salt CH3CONA, when you introduce the salt in water, what's going to happen? The salt is going to dissociate as CH3CO negative aqueous plus Na positive aqueous. When you introduce the salt in water, first step, the salt is going to dissociate into its ions. Ions are CH3CO negative and Na positive. Let's say its concentration was C molar. In the beginning, this is 0, this is 0. Now imagine that this salt entirely got dissociated into its ions. So I'll be left with nothing. 1 gives 1, C molar gives C molar, and this is also C molar. Okay. So I've introduced the salt in water, and this salt has dissociated completely into its ions. Its ions are your CH3CO negatives and Na positives, right? Now guys, in this particular salt, CH3CO negative, Na positive. If I ask you, which ion, cation or anion, which ion is the weak component here? Which ion is the weak component here? In this salt, you have got two ions, CH3CO negative, Na positive. CH3CO negative has come from CH3COH, weak acid. This has come from NaOH, strong base. And that ion of salt interacts with water, which would have come from either weak acid or weak base. So over here, this CH3CO negative, this CH3CO negative is going to interact with water. It is going to interact with water, right? Now, just tell me one thing. This CH3CO negative, it is going to interact with which ion of water? It's going to interact with H positive of water, and it will lead to the formation of what? CH3COH, right? And in the water, OH negative remains as such over here. And this particular reaction, where the ion of the salt is interacting with water, this particular reaction you call as hydrolysis reaction. You call this as hydrolysis reaction. Now, my dear students, what is the concentration of CH3CO negative which I have taken? C molar. Let's say this is 0 in the beginning. This is 0 in the beginning. Till now, alpha used to be called as degree of ionization. Now, over here, I'm not going to use the term alpha. I'll be using the term H. H I'll be calling as degree of hydrolysis. Terminology is different, meaning is same. Till now, I was using the term alpha. Now, instead of alpha, I'll be calling it as H, degree of hydrolysis. Since this reaction has got a separate name, hydrolysis reaction, so its alpha will be called as H, degree of hydrolysis. Rest, everything is same. So now tell me, this was the initial stage, T is equal to 0. Now at equilibrium, this would be C minus CH. This would be CH. This would be CH. Correct? Right? Now, my dear students, first of all, till now, I used to write Ki, ionization constant. In case of hydrolysis reaction, I won't be using the term Ki. I'll be using KH. KH is what I call as hydrolysis constant. KH, I'll be calling as hydrolysis constant. How do you write its expression? It is going to be concentration of CH3COH multiplied by concentration of OH negative divided by divided by concentration of CH3CO negative. This is how you are going to write its expression. What is KH here? Again, I'm telling you same thing. KH is what you call as hydrolysis constant. It is basically your Ki, hydrolysis constant, but over here you are calling it as KH. And this H over here, as I told you, this is what you call as degree of hydrolysis. This is what you call as degree of hydrolysis. Now, my dear students, one more thing. When this ion has interacted with water, it has led to the formation of CH3COH, which is a weak acid. Now, this weak acid in the solution, it will further undergo dissociation. This CH3COH in water, it is further going to undergo dissociation. It is further going to undergo dissociation, or let me write it generally like this. CH3COH in water, it is further going to undergo dissociation as CH3CO negative and H positive. Right? In the hydrolysis reaction, the product which we get, this product further undergoes dissociation in water, CH3CO negative, H positive. Correct? Now, guys, it's a weak acid. In the hydrolysis reaction, we got a weak acid here. If you see, it's a weak acid. This weak acid has interacted with, this weak acid has undergone dissociation, right? So, what is the dissociation constant of the weak acid? I'll be representing that with Ka. So, Ka here is going to be concentration of CH3CO negative multiplied by concentration of H positive divided by concentration of CH3COOH. Correct? Now comes the things. First of all, if I multiply Ka with Kh, let's see what do we get. If I multiply Ka with Kh, if I multiply these two things, what all things will get cancelled out? CH3COH cancels out. CH3CO negative cancels out. So I'll be left with H positive concentration multiplied by OH negative concentration. Now you tell me in the chats, what do we call this particular term as? H positive concentration, OH negative concentration. What do you call this as? What do you call this as? You call this as Kw, which is 10 raised power minus 14 at 25 degrees centigrade. So from here, my first question is done. That is Kh, that is Kw divided by Ka. This is the first question which will be asked here. Calculate the hydrolysis constant. Calculate the hydrolysis constant in case of the salt of weak acid and strong base. This will be our first question. Okay. Calculate the hydrolysis constant. Number one. This will be the first question. Kw, you know, Ka will be given to us in the question. Kh we can calculate. Number one. Number two. Second question that will be asked. What is that? Since if you look at Kh is nothing but concentration of CH3COH, which is Ch, concentration of OH negative, Ch, divided by concentration of CH3CO negative, which can be finally written as CH square. Divided by 1 minus H. It used to be C alpha square by 1 minus alpha. And instead of alpha, I'm using H. Now, guys, if H is less than 0.05, at that point, instead of 1 minus H, I can just write 1. So, I can say your Kh gets reduced to what? Kh gets reduced to CH square. Or I can say H is nothing but under root of Kh divided by C. And this Kh we have already calculated. Kh is nothing but, it is Kw divided by Ka, and in the denominator you have got C. This is one more question which is asked. My dear students. What is the question? Calculate the degree of hydrolysis H in case of the salt of weak acid and strong base. This is the second question. Okay? This is the second question. I hope you are getting all this stuff. First question will be calculate the hydrolysis constant. Second question will be calculate the degree of hydrolysis. Okay. Since when salt is introduced in water, the ions of salt are going to interact with water to produce either alkaline or acidic solution. How do we calculate the pH of that alkaline or acidic solution? Now, what do we have to calculate? pH. Right? What do we have to calculate? pH. Okay. Now, over here, if you see, OH negative concentration is how much? CH. OH negative concentration is what? It is CH. If OH negative concentration here is CH and H value already you got under root of what? Under root of Kw divided by K into C, right? If you put this C in the root, it's going to come as under root of Kw multiplied by C. divided by Ka. Or you can write it as Kw multiplied by C divided by Ka whole raised power 1 by 2. This is the concentration of OH negative which is there in the solution. If it is the concentration of OH negative in the solution, we can easily calculate POH. P stands for minus log of OH negative concentration. So minus log of what is OH negative concentration? It is Kw multiplied by C divided by Ka whole raised power 1 by 2. Or 1 by 2 comes out. This is going to be, it will come out to be what? It will come out to be log of Kw plus log of C plus log of C minus log of Ka. Minus log of Ka, right? Minus log of Ka. So POH here comes out to be. Take the minus inside. So it's 1 by 2. 1 by 2. It is minus log of Kw. Minus log of Kw plus, sorry, it's minus now, log of C. And then we have got plus log of Ka. Plus log of Ka. Okay. Now guys, try to understand. POH will be equal. Half I'm writing as such. What is minus log Kw? Minus log Kw means P of Kw. Minus log Kw is P of Kw, right? Minus log Kw means P of Kw. Plus log of Ka minus log of C. This is how I've written it till now. Now at 25 degrees centigrade, Kw is equal to 10 raised power minus 14. At 25 degrees centigrade, Kw is equal to 10 raised power minus 14. So minus log of 10 raised power minus 14 comes out to be what? Minus log of 10 raised power minus 14 comes out to be 14. Minus log of 10 raised power minus 14 comes out to be 14, right? So POH value here comes out to be 7 plus, I'll be writing it half log of Ka minus log of C. Perfect. So this is POH, but what am I supposed to calculate? I'm supposed to calculate POH. Sorry, I'm supposed to calculate pH. pH is equal to 14 minus POH, right? So 14, POH is this term. I'll be writing the final expression here. pH is going to be equal to, since we have taken the salt of what? This is the salt of weak acid and strong base. It is the salt of weak acid and strong base. So 7 plus half of P of Ka plus log of C. This is going to be the final expression of calculation of pH when the salt of weak acid and strong base undergoes hydrolysis. Right? Okay. Is it clear, guys? Is it clear? Is it clear? Is it clear? Quick. Sir, log Kw minus kaise hua? Log Kw where? Oh, this one. So it was minus log of this. So minus log of this. So minus as such outside. So it will be half of log of Kw plus log C divided by log K. Now minus I've taken inside. So it is half of minus log K. Now this plus becomes minus and this minus becomes plus. Okay. So my dear students, 3 questions will be asked here. 3 questions. First question is going to be calculate the hydrolysis constant, calculate the degree of hydrolysis, and calculate the pH of the solution, and calculate the pH of the final solution. Now, I just derived the results for one of the salts, which was the salt of weak acid and strong base. Other results I'm not going to derive. Other results I'm going to give you directly, and you are going to remember them, and I'll show you how do we apply them. Okay? I'll show you how do we apply them. See guys, here I'm going to make a table, and please remember this particular table. So here I'm writing type of the salt. Okay? Here I'm writing hydrolysis constant. Here I'm writing degree of hydrolysis, and here I'm writing formula to calculate pH. Formula to calculate pH. Okay? Just try to understand what exactly I'm going to do. Remember this particular table, guys. This is important. This table is important. Okay. Now, the first salt which I'm taking into consideration, that is the salt of weak acid and strong base, which all its results I derived 5 minutes back only. All its results I derived 5 minutes back only. Salt of weak acid and strong base, its KH has to be equal. its KH has to be equal. First you write KW divided by, which one is weak? Acid. I'll be writing Ka. Degree of hydrolysis, H. H is equal to what? Under root of KH by C. Under root of KH. KH is KW divided by Ka multiplied by C, where C is the concentration of the salt. How do we calculate its pH? Since it is a salt of weak acid and strong base, so pH has to be 7 plus, strong base, 7 plus. 7 plus half of, which one is the weak acid? So P of Ka plus log of C, where C is the concentration of salt. These are the three results which I have derived. No need to go for the derivations and stuff. Just remember these three results directly, right? Let's say I have got the salt of strong acid and weak base. Let's say the salt of strong acid and weak base undergoes hydrolysis. How do we get all these things again? First of all, KH. KH here will be KW divided by, instead of Ka, I'll be writing KB, right? H will be equal to under root of KH by C. KH here is KW divided by KB multiplied by C. If I ask you what would be pH, it is strong acid and weak base. Strong acid means 7 minus. pH has to be 7 minus. So 7 minus half of, this will be P of KB here, because base is weak, plus log of C. C is the concentration of salt. Similarly, I've got third type of the salt as well, the salt of weak acid and weak base, right? Its KH is nothing but, KH will be KW divided by, since both are weak, so write Ka as well as Kb. And when you do its degree of hydrolysis calculations, it comes out to be under root of KH, and KH is nothing, that is KW divided by Ka multiplied by Kb, and its pH formula will be equal to 7 plus half of P of Ka minus P of Kb. These are the results which you will have to remember directly. These are the results which you will have to remember directly. Okay? All clear? All clear? Whosoever wants a break for 5 minutes, please, you can take the break and watch the session. Come back after 5 minutes, right? In the recorded format, you can watch. Perfect? Do not disturb the class, please. All right, so we have got these three types of salts, guys. Okay, if you have got the salt of strong acid and strong base, if you have got the salt of strong acid and strong base, like NaCl, tell me, will it undergo hydrolysis? Will it undergo hydrolysis? Will it undergo hydrolysis? Will it undergo hydrolysis? Quickly, salt of strong acid and strong base, will it undergo hydrolysis? Why is that? Why it does not undergo hydrolysis? Because over here we have got Na positive, Cl negative. Na positive has come from NaOH, strong base. Cl negative has come from HCl, strong acid, right? So no component here is weak. And with water, which ion interacts? That ion of salt interacts with water, which comes from either weak acid or weak base. But both are strong components here. So it does not undergo hydrolysis. It does not undergo hydrolysis. Okay? And remember, if you look at all these three expressions, over here H is inversely proportional to concentration of salt. Inversely proportional. H is independent. Degree of hydrolysis is independent of the concentration of salt. In case of what? In case of the hydrolysis of the salt of weak acid and weak base. Weak acid and weak base. Okay? Got it? So you have to remember this particular table, guys. Now, let's see what kind of questions can be asked from here. One thing I'll tell you. You just have to do one thing. You just have to identify the salt and we are done. Identify the salt, use the formulas, we are done. For example, calculate KH, hydrolysis constant, degree of hydrolysis and pH of a centimolar. Centimolar means 10 raised power minus 2 molar. Right? Centimolar solution of NH4Cl. So first of all, the salt is NH4Cl. If the salt is NH4Cl, just identify the salt. NH4 positive, Cl negative. NH4 positive has come from NH4OH. Cl negative has come from HCl. This is a weak base. This is a strong acid. That means the salt that is given to us, it is a salt of strong acid and weak base. It is a salt of strong acid and weak base. My first question, calculate KH. KH here will be equal to KW divided by weak is base, so KB, right? KW at 25 degrees centigrade is 10 raised power minus 14, and KB must be given to me in the question, that's 10 raised power minus 6. The value comes out to be 10 raised power minus 8. So this is our first question. The hydrolysis constant, calculated. Hydrolysis constant, calculated. Second, degree of hydrolysis H. That's equal to under root of Kh by C. Kh is Kw divided by Kb multiplied by C. So it's going to be under root of Kw is 10 raised power minus 14 divided by Kb is given to me as 10 raised power minus 6. C is the concentration of the salt, which is centimolar. Concentration is 10 raised power minus 2. Now, this will be 10 raised power minus 8, goes up. It will be 10 raised power minus 6. The value finally will be 10 raised power minus 3. So H is 10 raised power minus 3. The third question, calculate the pH of the solution. pH will be equal to, the formula you already know. Since it's a strong acid weak base, so 7 minus half of P of Kb plus log of C. Plus log of C. So it's going to be 7 minus half of. What is P of Kb? P of Kb means minus log of Kb. Minus log of 10 raised power minus 6. Minus log of 10 raised power minus 6 comes out to be 6 plus log of C. C is the concentration of salt, 10 raised power minus 2. Log of m raised power n is n log n, right? So minus 2 comes to the front. So 6, this will be minus 2, right? Now just the matter of calculation. 7 minus 6 minus 2 is 4. 4 by 2 is 2. So 7 minus 2 comes out to be 5. So this is the pH of the final solution, right? Am I clear with this? Am I clear with this? Tell me in the chats quick. Am I clear with this? You just have to identify the salt, which category of salt it is. Then use the formulas. All the formulas I have given you already in the table. All the formulas I have already given you in the table. Okay, try to solve this question. Try to solve this particular question. Calculate KH, H and pH of a millimolar solution. Millimolar means concentration 10 raised power minus 3 molar, right? Of KCN. Salt is KCN. Ka is given. So first of all, if you look at KCN, let's try to identify the salt. K positive, Cn negative. K positive has come from KOH. Cn negative has come from HCN. KOH is a strong base. HCN is a weak acid. One more thing. Since Ka is given, that means the acid which we have taken, that's weak. So I identified the salt. The salt is of the type weak acid and strong base, right? Salt is it is a salt of weak acid and strong base. If it is the salt of weak acid and strong base, first of all, calculate its hydrolysis constant, KH. KH has to be equal. Formula you know, Kw divided by Ka. Kw at 25 degrees centigrade, you know that's 10 raised power minus 14. Ka is given to me as 10 raised power minus 7. The value comes out to be 10 raised power minus 7. So first question is done, KH, right? Second, degree of hydrolysis H. H is nothing but, it will be under root of KH by C. KH is equal to Kw divided by Ka multiplied by C. So Kw we know, that's 10 raised power minus 14. Ka is given to me as per the question, that's 10 raised power minus 7. C is the concentration of the salt, that's 10 raised power minus 3. So this will be 10 raised power minus 10, comes up. So root of 10 raised power minus 4, which will be 10 raised power minus 2. So this is your degree of hydrolysis as well. Now, if this is the degree of hydrolysis, calculate the pH now. pH has to be equal. There's a formula. Since it's a salt of weak acid, strong base. Strong base means it's 7 plus. Strong base means 7 plus, half of. P of, which is weak. Weak is acid. So P of Ka plus log of C, where C is the concentration of salt. So 7 plus half of. P stands for minus log of Ka. So minus log of this value. Minus log of this value comes out to be 7 plus log of C. C is the concentration, 10 raised power minus 3. So log of 10 raised power minus 3 comes out to be minus 3 only. So 7 minus 3 is 4. 4 by 2 is 2. So 7 plus 2 here is 9. So this is the pH of the solution which we were supposed to calculate. Is it clear? Is it clear, guys? Is it clear to everyone? So these are the 3 types of the questions that can be asked. All right. Even this question you can solve, I believe. Even this question you can solve, I believe. A lot of spammers have come. Yeah? A lot of spammers have come. Welcome, spammers. Welcome, welcome. You should have taken the subject arts because this is not your business. Okay? You can still change the subject. or take the commerce, learn accountancy. That will be still tough for you. Okay. What do you think is the answer of this particular question? What do you think is going to be the answer of this particular question? What do you think is going to be the answer of this particular question? Let me not block them today. Yeah, let me not block them today. What do you think is going to be the answer of this question? Quick. Quickly, people. This is something which you should be able to solve. First of all, just look at the salt. NH4 positive, Cl negative. It has come from NH4OH, so weak base. This has come from HCl, strong acid. So it is a salt of weak base and strong acid. The salt of weak base and strong acid, its degree of hydrolysis is equal to under root of Kw divided by Kb multiplied by C. So degree of hydrolysis and C, they are inversely proportional. Degree of hydrolysis and C, they are inversely proportional. Degree of hydrolysis and C, they are inversely proportional. C is the concentration of the salt. So more the concentration of the salt, less the degree of hydrolysis. What do we have to calculate? In which of the following degree of hydrolysis is maximum? Degree of hydrolysis will be maximum where the concentration of salt will be minimum. So where do you think is the concentration of salt minimum? Where is the concentration of salt minimum? Here. So degree of hydrolysis here is going to be maximum. Yeah? Right? If the salt was of the type weak acid, weak base, if the salt was weak acid, weak base type, what would have been the answer? In case of the salt of weak acid and weak base, degree of hydrolysis is independent of the concentration. Right? Degree of hydrolysis there is independent of the concentration. Do remember that. Do remember that. Okay? Just a second. This is not the question from the salt hydrolysis. This is the question from buffer. So it has to be here. I hope all the things are clear till here. So guys, this was all about your salt hydrolysis, and I have kept few questions here. I have kept few questions here for you so that you can try them out. See, for example, this is the question. You can give it a try afterwards. You just have to check the type of the salt. Salt is NH4Cl. Then you have to calculate hydrolysis constant, degree of hydrolysis, and pH. You can do it. You know the formulas. It's a homework question, number 1. Second homework question I've kept. See, this is one more salt, pyridinium chloride. You just have to identify the type of the salt, and accordingly, you have to use the formula and do the question. Since one hint, Kb is given, that means the base used has to be a weak base, right? So it would be the salt, probably salt of your strong acid and weak base. Okay? I hope this is clear. Similarly, calculate the pH of this particular salt, sodium phenolate. Ka is given. If Ka is given, that means acid is weak. So this is the salt of weak acid and strong base here. It is the salt of weak acid and strong base. It's again a homework question because these are formula based ones. These are formula based ones. Okay? These are formula-based questions. Now, let's go into one more important topic, that is your buffer. But before starting the buffer, tell me in the chats whether all the things are super clear to you or not. Tell me in the chats whether all the stuff is super clear till here or not. Guys, just 2 topics are left. Just wait. 2 more hours. That's it. Let me know in the chats whether all the stuff till here is clear or not. Everybody in the chats. Perfect, guys. Wonderful. So let's move on to something called as buffer. How do we exactly define a buffer? My dear students, there are some solutions. There are some solutions in which upon the addition of small acid or small base, there are some solutions in which upon addition of small amount or small base, their pH does not significantly change. You will see some type of solutions in which if you add small amount of acid or small amount of base, their pH does not significantly change. Their pH does not significantly change. Why is that? You'll get the answer in some time. Why that happens? You'll get the answer in some time. First of all, I want you guys to remember the definition of a buffer. Buffer is nothing. Buffer is a special type of solution whose pH does not significantly change on adding small amount of acid or base into it. On adding small amount of acid or base into it. What's the reason for that? You'll get the idea in some time when I'll teach you buffer action, how buffer works. Okay? So, those solutions in which if you add small amount of acid or base into them, their pH does not significantly change. Their pH does not significantly change to our expectations, right? Those solutions are called as buffer solutions. And these buffer solutions, I would say, they show resistance. They show resistance towards what? Towards the change in pH. They show resistance towards the change in pH. So these are the solutions whose pH does not significantly change on addition of small amount of acid or base into them. They technically show resistance towards the change in their pH. Why it happens? You'll get the idea in some time, but before that, we have got 2 types of buffers. We have got 2 types of buffers. Simple buffer and mixed buffer. Simple buffer consists of, it is made up of only a single substance. For example, let's say you have got a container. In this container, if you are, for example, taking salt of weak acid and weak base. Example is, let's say, CH3COONH4. This is the salt of weak acid and weak base, right? A salt of weak acid and weak base, it behaves like a buffer. It acts like a buffer. So, when you add small amount of acid or small amount of base into this particular container, if you are expecting its pH to change by, let's say, 4 units, in reality, it won't be changing by 4 units. It will be changing very, very, very less than that, right? So, pH does not change as per your expectation. So, first of all, this is the salt of weak acid and weak base. It behaves like a buffer. So, when you add small amount of acid or base into it, its pH does not significantly change. It will show resistance towards the change in pH. And if you look at this particular buffer consists of what? Just a single substance. So, you'll be calling this particular buffer as the simple buffer. So, your simple buffers, if I talk about, your simple buffers are made up of what? Your simple buffers are made up of what? Your simple buffers are made up of, they consist of single substance, right? If you talk about the mixed buffers, mixed buffers, they consist of, they are the mixture of what? They are the mixture of 2 substances. That means in the container, you do not have only one substance. In the container, you have got 2 substances. in case of the mixed buffers. And they are further classified into two types: acidic buffer, basic buffer. Have a look. Have a look, guys. Acidic buffer and basic buffer. Acidic buffer and basic buffer. So first of all, acidic and basic buffer, they are the examples of what? They are the examples of mixed buffers. They are the examples of mixed buffers. That means in these buffers, you will have two components basically, not just one component. Now, acidic buffer consists of weak acid and the salt of same weak acid with a strong base. For example, imagine you have got the container. In the container, you have taken CH3COH, which is the example of a weak acid, and this is the salt of same weak acid with a strong base. It is the salt of same weak acid with a strong base. Whenever you see these two things present in the container, whenever you see these two things present in the container, weak acid and salt of same weak acid with a strong base, you'll be calling this mixture as the acidic buffer. This is what you call as acidic buffer. This is what you call as acidic buffer, right? Similarly, in case of the basic buffer, what do we have? Basic buffer consists of weak base. It consists of weak base and the salt of same weak base with a strong acid. The salt of same weak base with a strong acid. Like you have taken a container. In this container, we have taken a weak base. And this is the salt of same weak base with a strong acid. I'll be calling this particular buffer as what? I'll be calling this particular buffer as basic buffer. So this is my acidic buffer. This is my basic buffer. Number one. Number two. Look at this acidic buffer. In the container, do you see only one component or two components? I can see two components here. So it is the example of which buffer? Mixed buffer. Look at the basic buffer. Again, you have got two components in the container. So this is the example of simple or mixed. It's the example of mixed buffer, right? Now, what these buffers do, when you'll be adding some small amount of acid or base into it, its pH won't significantly change. It will show resistance towards the change in pH. Similarly, over here, if you add some small amount of acid or base into it, its pH won't significantly change, right? This is again going to show resistance towards the change in pH. Now, why do they show resistance towards the change in pH? Let's get to know about that in detail. Let's get to know about that in detail. Understand, guys, what exactly I'm going to say. I hope you remember the common ion effect that I've taught you long back. I hope you remember that. So before showing you how buffer works, what is a buffer? Buffer is basically a solution that what that solution does, when a small amount of acid or base is added into that, its pH does not significantly change. It will show resistance towards the change in pH. Number one. These buffers are of two types. You saw it recently. One was your simple buffer, one was your mixed buffer. Simple buffer consists of only one substance, like we have got salt of weak acid and weak base. It behaves like a simple buffer. In case of mixed buffer, you'll find two components. Mixed buffer is of two types, acidic and basic, which is in our syllabus actually. Acidic buffer, basic buffer. When you talk about the acidic buffer, acidic buffer consists of weak acid and the salt of same weak acid with a strong base. Basic buffer consists of weak base and the salt of same weak base with a strong acid, right? Now, how these buffers work, why they show resistance towards the change in pH when a small amount of acid or base is added into them, we need to talk about that now. See, guys, first of all, what do you think this is? It's a weak acid. What do you think this is? This is the salt of same weak acid with a strong base. This is the salt of same weak acid with a strong base. So what do I call these two as? What do I call this mixture as? This is something which I call as acidic buffer. This is something which I call as acidic buffer. Now try to understand what exactly I'm going to say. For example, this is the container which I have. Let's say this is the container which I have. Understand properly. I'm assuming that this entire container is filled with water. I'm assuming that this entire container is filled with what? It's, for example, filled with water. Now, my dear students, in this container, for example, I'm keeping a weak acid, CH3COH. It's a weak acid. If it is a weak acid, definitely it's going to remain in equilibrium with its ions. Ions are CH3CO negative and H positive. So I'll say right now, this weak acid, it is in equilibrium with its ions. Let's say its concentration in the beginning is C, this is 0, this is 0. Let's assume its degree of ionization is alpha. So at equilibrium, this is C minus C alpha, this is C alpha, and this is C alpha. Okay, this is C alpha. Correct? Now, my dear students, this weak electrolyte right now, it is in equilibrium with its ions. So the system is at equilibrium. And as per thermodynamics, when the system is at equilibrium, system is considered to be at maximum stable state. I would say the system is right now present at its maximum stable state. Okay. So if I do any change to any of the ion, the system is going to oppose that. Whatever things I am going to do towards this system at equilibrium, system is exactly going to do opposite of that. Whatever things I'll be doing, system will be doing opposite of that, as per your Le-Chatelier principle, right? Now, let's say in the same container, I'm introducing CH3CONA. In the same container, I'm introducing CH3CONA, right? This CH3CONA will dissociate as CH3CO negative and Na positive. Right? Let's say its concentration is C1, 0, 0. Now this is 0. This will be C1 and this will be C1, right? My dear students, do you see one thing? In the same container, we have got a weak electrolyte and a strong electrolyte. In the same container, we have got a weak electrolyte and a strong electrolyte. Both are having one ion in common. What is that common ion? CH3CO negative. So what will be the total concentration, net concentration of this CH3CO negative? It has to be C1 plus C alpha, right? So in the same container, we have got weak electrolyte, strong electrolyte, both having one ion in common. Can I say over here common ion effect is going to operate? Yes. And due to common ion effect, will the degree of ionization of alpha increase or decrease? It will decrease. It will decrease. Due to which this reaction will go backwards. This reaction will go backwards due to common ion effect, right? This reaction will go backward due to common ion effect. And if the reaction goes backwards, that means alpha of the weak electrolyte decreases. So wherever you would want to neglect alpha, you can do that. So instead of C1 plus C alpha, I can just write C1. Now, my dear students, understand one simple thing. We have got weak acid, salt of same weak acid with a strong base in the same container. So basically, I have got an acidic buffer in the container. Right? Weak acid, salt of same weak acid with a strong base. So I've got the acidic buffer in the container. Now, what is the function of the buffer? What does the buffer do? When you will be adding some small amount of acid or base in the same container, its pH, it will show resistance towards the change in pH. Its pH won't change as expected, right? Why is that? Have a look. For example, in this particular container, wherein we have got acidic buffer, let's say in this container, I'm adding some 10H positive ions. Let's say, just to make you understand, I'm adding some 10H positive ions. I'm expecting that if I'll be adding some 10H positive ions, I'm expecting the pH of the solution should reduce by 2 units. Because when you add H positives, that means pH should reduce. So I'm expecting over here, if I add some 10H positives in the container, pH should reduce by 2 units. This is my expectation. But what happens in reality? When you add H positives here in the container, what is going to happen? When you add H positives in the container, what is going to happen? Since you are adding H positives in the container, that means you are increasing the concentration of H positive here. You are trying to increase the concentration of H positive here. This reaction was at equilibrium. Now at equilibrium, you are trying to increase the concentration of H positive. So equilibrium will try to decrease it. How? It will again send the reaction backwards. Since you are trying to add the concentration of H positive, you are trying to increase the concentration of H positive, right? Equilibrium will try to decrease it. It will shift the reaction backwards. Due to which, I'll say, since the reaction is shifting backwards, equilibrium is shifting backwards, so H positive and CH3CO negative, they are reacting and forming CH3COH back. Due to which, since due to this backward reaction, are H positives increasing or decreasing? No doubt, I am adding 10 H positives, but at the same time, some H positives are getting converted into what? This acid back, right? So on one side, you're increasing H positives, on another side, H positives are decreasing. I was expecting that pH should decrease by 2 units because I was expecting that I was adding 10 H positives. But in reality, due to backward reaction, some of the H positives interacted with CH3CO negative and formed CH3COH back, right? So what does that mean? Does that mean effectively 10 H positives are increasing in the container? Or let's say only 2 H positives are increasing in the container. I'm just giving you the numbers just to make you understand. So whatever our expectation was, we were expecting that we are increasing 10 H positives in the container. But due to the backward reaction, some of the H positives are decreased. So effectively, are we adding 10 H positives? Or in the solution, the increase in the H positives are less than that. The increase in the H positives are less than that. So I was expecting pH should reduce by 2 units due to the addition of 10 H positives. But in reality, are 10 H positives being increased? No, less than that. Maybe some 2 H positives are effectively increased. Due to the increase in the 10 H positives, I was expecting pH should decrease by 2 units. But in reality, 10 H positives effectively are not increasing in the solution. Only, just to make you clear, only let's say 2 H positives are effectively increased in the solution. Due to which, should pH decrease by 2 units or less than that? pH will decrease less than that, not exactly by 2 units. So what this solution is doing? Is it showing a resistance towards the change in pH? I had expected that the pH of the solution will decrease by 2 units, but in reality, it did not decrease by 2 units. 2 units would have decreased if effectively 10 H positives were being increased in the container. But are 10 H positives effectively increased in the container? No. You are adding 10 H positives. Due to the shift in backward direction, some of the H positives react with CH3CO negative, get back into CH3COH. Due to which, effectively 10 H positives are not increased in the container. Maybe some 2-3 H positives are increased. So whatever our expectation was pH will get decreased by 2 units if you add 10 H positives. If there will be increase of 10 H positives in the container. But in reality, there is not the increase in the H positives is not 10 exactly. It will be less than that. Due to which, what are you had expected? In reality, it won't be same. It will be less than that. Let me know once in the chats if it's clear. So I would say this particular solution right now, what is it doing? This particular solution right now, it is showing resistance towards what? It's showing resistance towards the change in pH. Okay? It is showing resistance towards the change in pH, guys. Correct? Am I clear with this? Say it in the chats once. Say it in the chats once quick, if this is clear. I would want everyone to let me know in the chats if it is clear. Everyone means everyone. Everyone means everyone. Yeah? Now guys, one more thing. If I would want to write Ka expression for this weak acid, or let me write somewhere here. If I want to write Ka expression for this acid over here, it will be concentration of CH3CO negative, that is C1, multiplied by concentration of H positive, that is your C alpha, divided by concentration of CH3COH, that is C minus C alpha. Take C as common, 1 minus alpha. C and C gets cancelled. Instead of 1 minus alpha, I can write 1. So your alpha comes out to be Ka divided by C1. This is something which we already discussed in common ion effect also. Okay? So this is your alpha. If you got alpha, what do you think will be the concentration of H positive in the solution? Concentration of H positive in the solution is C alpha, right? C I'm writing as such. Alpha is your Ka divided by C1. If I want to calculate pH of the solution, pH of the final solution, it will be minus log of H positive concentration, minus log of C into Ka divided by C1. Or I can write minus as such. It is going to be log of C plus log of Ka minus log of C1 minus log of C1. So I would be getting a formula here. The formula is going to be of what nature? See, it will be minus log Ka minus log Ka minus minus plus log of C1 plus log of C1 and minus log of C. Minus log of C. Now guys, tell me one thing. pH is equal. Minus log means P. So it's P of Ka. P of Ka plus log of M minus log of N is log of M divided by N. Right? Or you can write it as P of Ka plus log of, what is C1? C1 is basically the concentration of the common ion. Or I can call this ion as conjugate base of this particular acid. This CH3CO negative, I'll be calling it as conjugate base of this particular acid. So it is the log of concentration of conjugate base divided by, what was C? C was the concentration of acid. So conjugate base divided by acid. So this becomes one of my important formulas to calculate pH of the acidic buffer. This is one of the formula. By means of which you can calculate pH of the acidic buffer. What? It is P of Ka plus log of concentration of conjugate base divided by the concentration of acid. So let me write it over here. pH of the acidic buffer is equal to P of Ka plus log of concentration of conjugate base divided by concentration of acid. Or you can write it like this over here as well. pH is equal to P of Ka plus log of concentration of, if you look at concentration of conjugate base is C1, right? This C1 was basically the concentration of salt, right? So you can write the concentration of salt divided by concentration of acid. Perfect. You can remember these two expressions for now. Correct? This is how you calculate pH of the acidic buffer. Similarly, guys, if you'll be having a basic buffer, in case of the basic buffer, what will be the formula? Let me just write that formula directly. Let me not derive that. In case of the basic buffer, what would be the formula? The formula is going to be POH is equal to P of Kb plus log of concentration of conjugate acid divided by concentration of base. This is the formula to calculate POH in case of the basic buffer, or you can remember it like this. POH is equal to PKB plus log of concentration of salt divided by concentration of base. This is how you calculate POH of a basic buffer. Remember these two results directly, guys. Remember these two results directly from now on. Okay? Right? Am I clear? Am I clear? Am I clear? Am I clear? Clear, guys? Take a note of one more thing. If you have got the acidic buffer, remember, a solution can act as a buffer. Remember this directly. A solution can act as a buffer only if the ratio of concentration of salt and acid is between 0.1 to 10. Remember this particular point as well. Okay, this can be directly asked. It has got mathematics behind it as well. Okay, so do remember it directly. Perfect. Now let's see what kind of questions can be asked from the buffer. Okay, so if I ask you again, what does a buffer do? What does a buffer do? It shows resistance towards the change in pH. Okay, right? It's on adding small amount of acid or base into it, its pH does not significantly change. its pH does not change as expected. Right? Now, look at this simple question. It's one basic question here, and I believe you can easily solve this. Calculate the pH of 1 liter solution containing 0.01 molar CH3COH and 0.02 molar CH3CON. So basically, imagine that in the container we have got CH3COOH and we have got CH3COONA. So what all things are there in the container? This is your weak acid. This is the salt of same weak acid with a strong base. So weak acid and the salt of same weak acid with a strong base. What do I call this as? Acidic buffer, right? It is the acidic buffer. And how do you calculate pH of the acidic buffer? How do you calculate pH of the acidic buffer? pH of the acidic buffer is calculated as P of Ka plus log of, you can write concentration of salt divided by acid. Okay, P of Ka. Ka is this much, Ka is this, and P of K, P stands for minus log. So minus log of this value, you already know that's 4.74 plus log of, what is the concentration of salt? Concentration of salt is 0.02 molar divided by concentration of acid is how much? 0.01 molar. So it is 4.74 plus log of 2 is 0.3. The value comes out to be 5.04. So this is basically the pH of the solution. Done? Done, people? This was the first and the basic type of the question. Now, let's see some more questions, some good ones. See, guys, look at this particular question. Understand it properly. Before showing you this question, let me tell you one important thing. Whenever you are given with a solution consists of solute and solvent, right? If the molarity of the solution is given to you, if the volume of the same solution is given to you as well, if molarity is given, if molarity of the solution is given, volume of the same solution is given to us as well, then remember molarity of the solution multiplied by volume of solution in liters, it gives us number of moles of solute in the solution. It gives us number of moles of solute in the solution. Similarly, molarity of the solution multiplied by volume of solution in ml, it gives us number of millimoles of solute. It gives us number of millimoles of solute in the solution. Remember these two things. Molarity of the solution multiplied by volume of solution in liters gives us moles of solute in the solution. Molarity of solution multiplied by volume of solution in ml, that gives us number of millimoles of solute in the solution. Why am I telling you all this stuff? Have a look. See, guys. As far as the question is concerned, calculate the pH of the solution obtained on mixing 100 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. So as per the question, we are mixing two solutions. One is your CH3COOH solution. You are mixing with NaOH solution, right? CH3COH, acid, base. And if you are mixing these two solutions, it will lead to the formation of salt. Salt is going to be CH3CONA, and with that, you'll be getting water, correct? Since you are mixing these two, you are mixing acid and base, acidic solution and basic solution. What is going to happen? In the acidic solution, acid, in the basic solution, base, they are going to react. They will lead to the formation of salt and water. Now, initially at time t is equal to 0, CH3COH, we have got CH3COH solution. Molarity of the solution is given. Volume of the solution is given to us in ml. Molarity of the solution multiplied by volume of solution. Molarity multiplied by volume in ml. That gives us what? Number of millimoles. So if I ask you, how many millimoles of CH3COH do we have? 0.1 into 100 comes out to be 10. So in the beginning, we have got 10 millimoles of CH3COH. Similarly, how many millimoles of NaOH do we have? Molarity multiplied by volume in ml. This multiplied by this will be also 10. So we have got 10 millimoles of NaOH in the beginning as well. In the beginning, we have got 10 millimoles of this, 10 millimoles of this, right? Now, my dear students, if you have studied mole concept, I have taught you in detail, whenever in a chemical reaction, amounts of all the reactants are given. Whenever in a chemical reaction, amounts of all the reactants are given, at that point of time, we use the concept of limiting reagent. And in the limiting reagent concept, what do? We are supposed to balance the reaction first. The reaction is already balanced, right? Now, identify the limiting reagent. How do you identify the limiting reagent? Given moles, divide by stoichiometric coefficient. Given moles, divide by stoichiometric coefficient. The one that gets the lesser value, that's always the limiting reagent. But here, we are not given with moles. We are given with millimoles. So, divide the given millimoles by the respective stoichiometric coefficients. 10 by 1, that's 10. 10 by 1, that's 10. You are getting the same value. If you are getting the same value, that means both would have got completely consumed. You would be left with nothing at the end. This is the case of complete neutralization, where entire acid has reacted with entire base to form salt and water. So take one of them as reference. 1 mole gives 1 mole. So 10 millimole is going to give us 10 millimoles of salt, and there'll be 10 millimoles of water as well. So now if I ask you, in the final solution, when the reaction is stopped, in the final solution, what all things are we left with? Are we left with any acid? No, it's over. Are we left with any base? No, it's over. We are left with salt and we are left with water. And you know, salt plus water. Salt plus water. What are they going to do? They are going to do the salt hydrolysis now. Salt plus water. They are going to do the salt hydrolysis. So, the final solution which I got, the final mixture I got, in the mixture, we have got salt and water present only. Rest, everything is over. Right? Initially, we started with acid and base. Acid and base completely has got over. Now, we are left with only salt and water. So, salt and water will undergo salt hydrolysis. Right? And in salt hydrolysis, either you get alkaline solution or you get acidic solution. How do we calculate pH of that solution? You know it. You know it. So, over here, which salt we have? We have got the salt of weak acid and strong base. When the salt of weak acid and strong base undergoes hydrolysis, how do we calculate its pH? Remember the formula, I have given you the table. Salt of weak acid and strong base. Weak acid, strong base. That means 7 plus half of P of Ka plus log of C. This is how you are going to calculate the pH of the final solution. Okay. So this is going to be 7 plus half of P of Ka. Ka value is given as this much. Minus log of this is going to be 4.74 plus log of C. What is C? C is the concentration of salt. Concentration of salt means molarity of the salt. I would say molarity of the salt will be millimoles of the salt divided by total volume in ml. Right? Concentration of salt will be millimoles of the salt divided by total volume in ml. Total volume is how much? 100 plus 100, that's 200. So, this particular equation, you'll have to solve here. So, it's going to be 7 plus half of 4.74 log of m by n is log m minus log n. So, it's going to be log 1 is 0. So, it's directly going to be log 20. Log 20 is how much? 1.3. Now, solve this and you are going to get the pH of the final solution. Okay? Understand and remember these sort of questions. They're important. They're very important. These questions are what you call as acid-base titration. Acid-base titration questions. Okay? Let me show you more. Let me show you more such type of the questions. Wherein you need to use your brain basically. Wherein you need to use your brain basically. But before showing the questions further, let me tell you one more thing so that you can solve these questions. Dear students, like in this particular question, we started with acid and base. So finally, what were we left with? We were left with salt and water. And how did we calculate pH of the final solution? With the help of salt hydrolysis formula, right? Remember, whenever there's a question wherein you are confused whether to use salt hydrolysis formula for the calculation of pH or whether to use buffer formula for the calculation of pH. Okay, whenever you'll find a question wherein you'll get confused whether to use salt hydrolysis formula or buffer formula for the calculation of pH, you'll prioritize your buffer at that time. Okay, whenever you'll find a question wherein there is a possibility of salt hydrolysis or salt hydrolysis is one of the possibility, and in the final solution, let's say there is some strong acid left. Now, should we use the salt hydrolysis formula to calculate pH or should we consider strong acid for the calculation of pH? Here you will be considering strong acid for the calculation of pH. I'll let you know in some time what it means. First of all, write them down. Whenever there's a possibility of salt hydrolysis and there is a strong base present in the container, which one should I prioritize? How do I calculate pH? With the help of salt hydrolysis or strong base? I'll be prioritizing strong base. Okay? Remember just these three things. Remember just these three things. They are going to help you out in order to solve the questions in effective way. Remember these three things. Now, why am I giving you these three things? What is meant by them? For that, I'll be showing you one more question. Say guys, as per this particular question is concerned, we are going to mix CH3COH with NaOH. We are mixing CH3COOH with what? With NaOH. Acid and base you are reacting. And you know acid and base reacts and leads to the formation of salt. Salt is CH3CONa, and with that you'll be getting water. The reaction is balanced, right? Initially tell me, time t is equal to 0. How many millimoles of CH3COH do we have? Molarity multiplied by volume in ml. 0.1 multiplied by 100, that's 10. So we have got 10 millimoles of CH3COH in the beginning. How many millimoles of NaOH do we have? Molarity multiplied by volume in ml. 50 into 0.5 is 5. So we have got 5 millimoles of NaOH in the beginning. So this would be 0, this would be 0. Now, among these two reactants, which one is the limiting reagent? 10 divided by 1 is 10. 5 by 1 is 5. The one that gets the lesser value, that is the limiting reagent. So this is the limiting reagent. If this is the limiting reagent, it would have got completely consumed and I'll be left with nothing, right? Now, you know in the reaction, how much is the product formed? How much is the excess reagent left? All that stuff is decided by what? All that stuff is decided by the limiting reagent. Now have a look. 1 mole gives 1 mole. So from 5 millimoles, you would have got 5 millimoles of this salt. 1 gives 1, 5 millimoles would have given 5 millimoles of water. Now at the same time, 1 mole of NaOH reacts with 1 mole of CH3COH. So 5 millimoles of NaOH would have reacted with 5 millimoles of CH3COH. I had taken 10. Out of 10, 5 are reacting. So I'll be still left with 5 millimoles of CH3COH. And then the reaction would have stopped. Reaction would have stopped. Now guys, if you look carefully, when the reaction has stopped, what all things are present in the container? Base is completely over. It's over. Nothing is left. Salt is present. Water is present. Weak acid is present. Now tell me, what all possibilities do you see? Salt plus water can do salt hydrolysis, right? Weak acid and the salt of same weak acid with a strong base, right? They can form acidic buffer. Now, which one should we prioritize? Salt hydrolysis or buffer? We're prioritizing buffer. So, how do I calculate pH? With the help of salt hydrolysis formula or buffer formula? I'll use the buffer formula. That is going to be acidic buffer P of Ka plus log of concentration of salt here divided by concentration of acid. Okay, so P of Ka, P of this particular value minus log of this particular value, you know, that's 4.74 plus log of, what is the concentration of salt? Concentration of salt means millimoles of salt divided by total volume. Total volume is 100 plus 50, that's 150, whole divided by. Concentration of acid means millimoles of acid in the final solution divided by total volume. So again 5 divided by 150. So this term is 1, log of 1 is 0. The final answer of the question will be 4.74. Got it? Is it clear, guys? Is it clear? Is it clear? Let me know once in the chats. Now you must be understanding why did I give you this particular table. You must be understanding why did I give you this particular table, because the question which we solved, it was based on this particular one, right? It was based on this particular one. Yeah. I hope you're understanding the things properly. All right, let's solve a similar sort of question. Similar sort of question, but slightly different. Slightly different. This will make your one more concept clear. Calculate the pH of the solution obtained on mixing 50 ml of 0.1 molar CH3COH with 100 ml of 0.1 molar NaOH. So again, you are mixing what? Again, you are mixing CH3COH solution with NaOH. And acid and base are going to react, will lead to the formation of salt. Salt here is going to be CH3CONa, and with this you'll be writing water. With this you'll be writing water. Now initially at time t is equal to 0, how many millimoles of acid we have? Molarity multiplied by volume in ml. 0.1 into 50, that's 5. So we have got 5 millimoles of this acid in the beginning. How many millimoles of NaOH? This multiplied by this, 100 into 0.1, that's 10 millimoles. This would be 0 in the beginning. This would be 0 in the beginning. Now, which one is limiting? Which one is limiting reagent? Divide the millimoles by the respective stoichiometric coefficients. 5 by 1 is 5. 10 by 1 is 10. Which one is getting the lesser value? This is getting the lesser value. So it is my limiting reagent. Completely consumed. Now, entire product formation is decided by the limiting reagent. 1 mole gives 1 mole. 5 millimoles would have given 5 millimoles of this. Similarly, there would be 5 millimoles of this as well, right? Now, this is excess reagent. 1 mole reacts with 1 mole. So 5 millimoles would have reacted with its 5 millimoles. I had taken 10 out of 10, 5 are reacting. So I'm left with 5 millimoles of NaOH as well, right? And now I would say the reaction would have stopped. Now understand and remember, see what all things are left in the container. Weak acid, completely over. There is no weak acid left in the container. Salt and water, possibility of salt hydrolysis, right? What is left? A strong base is left here. Now this base and salt, can they form a buffer? No. Because of the base, for the buffer to be formed, there should be weak base and the salt of same weak base with a strong acid. It is not a weak base, it's a strong base. So they cannot form buffer or something here, right? Be careful with that. So what do we have in the container finally? Salt hydrolysis and strong base. Which one to prioritize? Strong base. So strong base is going to decide the pH of the solution here. Strong base is going to decide the pH of the solution. So the strong base which is left in the container, that's NaOH. Since it's a strong base, how many millimoles of it are left in the container? 5 millimoles of it are left in the container. I would say these 5 millimoles of NaOH which are left in the container, they would have dissociated completely into their ions. Ions are Na positives and OH negatives. 0, 0. Now this is 0. This would be 5. This would be 5. So basically, in the final solution, how many millimoles of OH negative are present? In the final solution, how many millimoles of OH negative are present? 5. So what would be the concentration of OH negative in the final solution? Millimoles of OH negative divided by total volume. Total volume is how much? 50 plus 100, 150. The value comes out to be 1 by 30. So this is the concentration of OH negative in the final solution. If you got the concentration of OH negative in the final solution, you can calculate POH. So minus log of 1 by 30, right? Minus as such, it's going to be log 1 minus log 30. Log 1 is 0. What is log 30? That will be log 3 into 10. So log 3 is 0.47. So it's going to be 1.47. So this is POH of the solution. If you got the POH of the solution, pH is going to be 14 minus 1.47. So 12.53 is going to be the pH of the final solution. If this sort of a question is clear, you can let me know it in the chats. You can let me know this in the chat. Okay? These sort of questions can be asked, guys. They can be asked. Let me know once in the chats if all the things are clear. Now there comes one more topic. What is that? That is your buffer capacity. Buffer capacity. What does the buffer do? It shows resistance towards the change in pH. It shows resistance towards the change in pH, right? Now buffer capacity is defined as number of moles of H positive or OH negatives. Number of moles of H positives or OH negatives added to 1 liter of buffer. Number of moles of H positives or OH negatives added to 1 liter of buffer divided by change in pH. How many moles of OH negative or H positive we have added to 1 liter of buffer divided by how much was the change in pH due to that, right? Okay. Thank you, sir. Because of you, I got my dream, Government Medical College, thanks to Game of NEET 1.0, NEET 2020. Amazing. Congratulations. 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 All right, guys. Buffer capacity. Buffer capacity. Number of moles of H positives or OH negatives, which are added to 1 liter of buffer divided by change in pH. This is how you calculate buffer capacity. First of all, what kind of information buffer capacity gives us? What kind of information buffer capacity gives us? My dear students, if I say that a buffer has got more buffer capacity, buffer has got more buffer capacity, what does that mean? That means buffer has got more tendency to show resistance towards change in pH. That means buffer has got more capability to show resistance. To show resistance towards towards a change in pH. That means buffer has got more tendency, more capability to show resistance towards the change in pH. If buffer has got more tendency to show resistance towards change in pH, that means will the change in pH be less or more? Change in pH is going to be less, right? So more the buffer capacity, more the tendency of the buffer to show resistance towards the change in pH. Or I would say more is going to be the efficiency of the buffer. More is going to be the buffer efficiency. More is going to be the buffer efficiency. So remember this particular stuff as well. Okay? Remember this particular stuff as well. Perfect? Remember this particular stuff as well. For example, let me give you one question so that you'll understand it properly. Look at this question, guys. It's simple. Look at this question. 0.4 grams of NaOH when added to 200 ml of buffer. We are adding 0.4 grams of NaOH to 200 ml of buffer, due to which pH changes by 0.01. Calculate buffer capacity. Calculate buffer capacity. So we are supposed to calculate phi. Phi is defined as number of moles of H positives or the number of moles of OH negatives added to what? Added to 1 liter of buffer. Added to 1 liter of buffer divided by change in pH. Divided by change in pH, right? Now understand. As per the question, what are we adding to a buffer? 0.4 grams of NaOH. So if I ask you how many moles of NaOH are we adding to a buffer? How many moles of NaOH are we adding to a buffer? Mass of buffer divided, mass of NaOH divided by molar mass of NaOH, right? So it will be 4 by 400 or 1 by 100, so 10 raised power minus 2. So as per the question, we are adding these many moles to 200 ml of buffer. These many moles of NaOH we are adding to 200 ml of buffer. Okay? Now guys, understand properly. Understand properly. The NaOH which we are adding to a buffer, how will it undergo dissociation? It will undergo dissociation as Na positive plus OH negative. So how many moles of NaOH we are adding? 10 raised power minus 2. 0, 0. Now this will be 0. This will be 10 raised power minus 2. This will be 10 raised power minus 2. So that means how many moles of OH negative are we adding to 200 ml of buffer? We are adding these many moles of OH negative to 200 ml of buffer. So I would say, dear students, I would say, as per the question, towards 200 ml of buffer, we are adding 10 raised power minus 2 moles of OH negative. To 200 ml of buffer, we are adding 10 raised power minus 2 moles of OH negative. Therefore, to 1 ml of buffer, how many moles of OH negative are we adding? 10 raised power minus 2 divided by 200 moles of OH negative. We are adding to 1 ml of buffer. Therefore, towards 1000 ml, 1000 ml means 1 liter. Towards 1000 ml of buffer, how many moles of OH negative are we adding? 10 raised power minus 2 divided by 200 multiplied by 1000. The value comes out to be 5 into 10 raised power minus 2. Moles of what? Moles of OH negative. So I would say these many moles of OH negative I'm adding to 1 liter of buffer. Okay? This is something which I needed. Number of moles of H positive or OH negative. Here I'll be calling it as OH negative. So how many moles of OH negatives are we adding to 1 liter of buffer? These many moles of OH negative we are adding to 1 liter of buffer. 5 into 10 raised power minus 2 divided by, what is the change in pH? 0.01. 10 raised power minus 2. So the value comes out to be 5. So I would say the buffer has got the buffer capacity of 5 exactly. The buffer has got the buffer capacity of 5 exactly. Okay? Am I clear with this, people? Is this question clear? Is this question clear to everybody? Right? All right. One similar sort of question we can do. And then we are left with only one topic, which we are going to do after the break. Okay? See guys, 100 ml of 0.1 molar solution of KOH is added to 200 ml of buffer. Changes the pH from this to this, calculate phi. We are again supposed to calculate buffer capacity. We are again supposed to calculate buffer capacity. We are again supposed to calculate buffer capacity. See, first of all, what are we adding right now? We are adding KOH. We are adding KOH solution in a buffer. Well, molarity of the solution is given. Volume of the solution in ml is given. You know, molarity multiplied by volume in ml. That gives me number of millimoles. So if I want to calculate moles of KOH, which we are adding to a buffer, that will be equal to molarity multiplied by volume of solution in liters. Molarity is how much? 0.1. Volume of solution in liters, 100 divided by 1000. That's again 0.1. Right? So it will be 10 raised per minus 2. So these many moles of KOH we are adding to a buffer. So that means how many moles of OH negative we are adding? Since KOH dissociates as K positive plus OH negative. Right? Right, people? KOH dissociates as K positive plus OH negative. 1 mole of KOH gives 1 mole of OH negative. Therefore, 10 raised per minus 2 moles of KOH will give us 10 raised per minus 2 moles of OH negative. So I would say these many moles of OH negative we are adding to 200 ml of buffer. So towards 200 ml of buffer, how many moles of OH negative are we adding? These many moles of OH negative we are adding. So towards 1 ml of buffer, how many moles we are adding? Divided by 200. Therefore, towards 1000 ml of buffer, 1000 ml means 1 liter of buffer. How many moles of OH negative we are adding? 5 into 10 raised per minus 2. So these many moles of OH negative we are adding to 1 liter of buffer actually. These many moles of OH negative we are adding to 1000 ml of buffer. That means 1 liter of buffer. So if you want to calculate buffer capacity is equal to number of moles of OH negative added to 1 liter of buffer. That is 5 into 10 raised per minus 2 divided by change in pH 4.2 to 4.4. So change in pH will be 0.2. Right? 0.2. So 0.2 means 2 into 10 raised per minus 1. Perfect. So 0.5 divided by 2, the value comes out to be 0.25. The buffer capacity of the buffer over here is going to be 0.25. Am I clear with this? Am I clear with this, people? So since buffer capacity is equal to number of moles of H positive or OH negative added to 1 liter of buffer. These were the moles of OH negative added to 200 ml of buffer as per the question. So I had to use the unitary method and check how many moles of OH negative are added to 1 liter of buffer. Then divide that with change in pH. I got the buffer capacity. I hope I'm clear with this particular stuff. Yeah. Now, one topic is left, that is solubility and solubility product. Let's take a break here for some time. And the time is 12:20. So, what time are we going to start again? Tell me in the chats. Tell me in the chats. Let's take a break for 20 minutes. Break till 12:40. But I would want every one of you to be back, okay? I would want every one of you to be back. I would want every one of you to be back on time. Okay? Because there is only one topic left, that's all. And we are done with this chapter in detail, that too. Naresh, that's not needed. That's not needed. Okay? Chalo, I'll see you all after the break. Be back exactly on time, guys. See you. Are you guys back? I think, yeah, back on time. Right? Back on time. All right, guys. So let me know in the chats if all the things are cleared properly. Whatever things we have discussed till now, is every single thing clear? You guys can let me know quickly in the chats. Then I can start the last topic of the session, that is solubility and solubility product. Yes, Devyansh, it will be completed. Don't worry. It will be completed. So let me know quickly in the chats, people, if all the things, whatever things we have discussed till now, are all the things clear? Yeah? Perfect. Perfect. So let's get to know and let's start with the topic, that is solubility, right? So how do we exactly define the term solubility? Let me quickly read the definition and then I'll make you understand what the solubility exactly is all about. My dear students, solubility is defined as maximum number of moles per liter which can be dissolved in a solution. Maximum moles per liter which can be dissolved in a solution. It is expressed in moles per liter. What does exactly it mean? Let's try to understand this. Say, guys, for example, imagine that you have got a container. Let's say this is the container which we have. In this particular container, for example, the solvent which you have kept here, that is water. Okay. Let's say we have got 1 liter of water in this particular container. Let's say you have got 1 liter of water in this particular container. Try to understand what exactly I'll be saying. For example, you are going to put a solute AB. For example, you are going to put a solute AB in this particular water, right? Let's say you are going to put this solute AB in this water, which I have taken in the container. This solute can be anything. For example, just to make you understand, let's say you are taking NaCl solid over here, and you want to introduce this NaCl solid in this water which I have taken in the container. Now, my dear students, you know, when you put salt in water, it dissolves. When you put salt in water, salt dissolves in water. Why is that? Because in between the water molecules, if you know, in between the water molecules, there are some vacant spaces, and the salt, it goes into those vacant spaces only. Salt fills those vacant spaces which are present between the water molecule, right? The salt which you are introducing here in this liquid, the salt occupies the spaces in between the water molecules, right? And that's the reason why the salt dissolves in water. Perfect. Now, my dear students, just try to understand. Just try to understand. For example, you are continuously introducing NaCl in this water. You are continuously introducing NaCl into this water. Now, this NaCl particle which you are introducing in water, as soon as NaCl goes into water, it breaks down into Na positives and Cl negatives. And these Na positives and Cl negatives, they try to occupy the spaces which are in between the water molecule. Okay? They try to occupy the spaces which are in between the water molecule. If you keep on continuing, putting this NaCl into water, continuously you are introducing NaCl into water, NaCl into water, NaCl into water. Can I say there will be a time when all the spaces between the water molecules will be occupied by NaCl particles, right? Okay, there will be a time when all the spaces between the water molecules will be filled by what? By NaCl particles. Perfect. I will be calling that particular solution in which all the spaces between these water molecules are filled by the solute particles. I'll be calling this solution as saturated. This solution now I'll be calling as saturated solution, in which all the spaces between the solvent molecules have been filled by the solute particles. Okay. Now guys, try to understand. Maximum moles of solute that can be dissolved in 1 liter of solution to make the solution saturated. That's something which we call as solubility of the salt. Maximum moles of solute that can be dissolved here to make this solution saturated. That's something which you call as solubility of the salt. For example, if I say solubility of, for example, this NaCl, let's say this is 5 moles per liter. What does that mean? That means in order to make 1 liter solution saturated, in order to saturate this 1 liter of solution, how many maximum moles of NaCl are used? In order to make this 1 liter solution saturated, 5 moles of NaCl has been used over here. Okay, right? Now, my dear students, if you look at this saturated solution, we have got 1 liter of the saturated solution now. This 1 liter of solution contains what? It contains water, and with this water there is NaCl as well. This water is the solvent, and I would say this NaCl is the solute. Perfect. Now guys, if you think logically, I told you, for example, in order to make 1 liter solution saturated, how many moles of solute have been introduced? 5 moles. So can I say in this saturated solution, 5 moles of solute are present in 1 liter of solution? I would say right now in this saturated solution, 5 moles of solute are present in 1 liter of solution, right? Number of moles of solute present in 1 liter of solution, that's something which you call as molarity. That's something which you call as molarity. If I ask you what is the molarity of this saturated solution, you will say molarity of this saturated solution is 5 moles per liter, or you can write it like this, 5 molar. This is the molarity. This is the molarity of the saturated solution. What was the solubility of the salt? Solubility of the salt was 5 moles per liter. What is the molarity of the saturated solution? It's also 5 moles per liter. Can I say in the saturated solution, and I say whenever you see a saturated solution, for a saturated solution, remember that solubility of the salt is equal to the molarity of the solution. In case of the saturated solution, solubility of the salt is nothing but, it is just the molarity of the solution in case of the saturated solution. I believe I'm clear with this. So in case of this saturated solution here, solubility of the salt was 5 moles per liter. It was 5 moles per liter. That means to make 1 liter of solution saturated, 5 moles of salt were introduced. So in this saturated solution, in 1 liter of this saturated solution, 5 moles of salt are there, right? So I would say molarity of this saturated solution right now is 5 molar. So in the saturated solution, I must say solubility is nothing. Solubility of the salt is nothing. It is just the molarity of the solution. This is one important point which I would want you guys to take a note of. Remember this. I'll write this point over here. Whenever you see a saturated solution, in the saturated solution, solubility of the salt is nothing but concentration or molarity of the solution. Molarity of the solution, right? Now guys, try to understand one more thing. These are some very, very small points which I'm trying to make you clear. Okay, try to understand one more thing. See, the 1 liter of water which is over here, let's assume that 1 liter of water can accommodate maximum 5 moles of solute. Let's say 1 liter of this water, it can accommodate maximum 5 moles of NaCl. Okay. Now, for example, I told you this 1 liter of water, it can accommodate maximum what? It can accommodate maximum of 5 moles of NaCl, for example. Okay. For example, I'm introducing, instead of 5 moles, I'm introducing 10 moles of NaCl. For example, I'm introducing 10 moles of NaCl. I would say out of 10 moles of NaCl, 5 moles will fill the spaces between the water molecules. The remaining 5 moles of NaCl will settle down at the bottom. The remaining 5 moles of NaCl will settle down at the bottom, and the other 5 moles, they will go into the solution. And that NaCl which is present in the solution, that is not basically present in the form of NaCl, that is present in the form of ions. That is present in the form of ions, right? So I took NaCl, for example. I took NaCl solid. Perfect. Right? How many moles of NaCl I took? 10 moles. Out of 10 moles, 5 moles are directly settling into the bottom. 5 moles are there in the solution. And those moles which are present in the solution, I would say, out of 10 moles, 5 moles go into the solution. And those moles of NaCl which go into the solution, they dissociate into their ions, right? So, if I ask you one thing, what is the solubility of NaCl here? You are no doubt introducing 10 moles, but solubility of NaCl in water is 5 moles, right? So, solubility of NaCl here is 5 moles. Perfect, it is 5 moles. And these 5 moles of NaCl are present in the solution in the form of its ions. So, I would say if 1 mole has given 1 mole, so 5 moles would have given 5 moles of Na positive and 5 moles of Cl negative. So, in this particular solution, what you will find? You will find 5 moles of Na positive. And at the same time, in this solution, you will find 5 moles of Cl negative. 5 moles of NaCl are present over here at the bottom. Is this particular point clear? Is this particular point clear? Let's say you have got the solute AB. You have got the solute AB, right? Let's say this 1 liter of water can accommodate 5 moles of AB. It can maximum accommodate 5 moles of AB. Now, for example, you are introducing 10 moles. If you are introducing 10 moles, out of those 10 moles, 5 moles will go into the solution, will fill the spaces. And out of 10 moles, 5 moles are filling the spaces, right? And remaining 5 moles are settling down at the bottom. Those 5 moles which go into the solution, they will be present in the solution in the form of its ions. They will be present in the solution in the form of its ions. Okay? Try to understand one more thing, guys. Try to understand one more thing. Try to understand one more thing. Okay. For example, this is the container which again contains, let's say, 1 liter of water. There is 1 liter of water here in this particular container. Let's assume that. Okay, 1 liter. Now, guys, this 1 liter of water, for example, it can accommodate maximum 5 moles of solute AB. It can, let's say, accommodate 5 moles of solute AB, maximum. Right? Let's say you have introduced, let's say you are introducing 5 moles of AB here in this particular container. You are introducing 5 moles. When you introduce all the 5 moles in this water, I would say the solution would become saturated. The solution would become saturated. And all these 5 moles of AB, they would be present in the solution in the form of its ions. All these 5 moles of AB, they would be present in the solution in the form of ions. That means all the 5 moles of AB would be present in the solution, right? In the form of its ions. So all those ions, they have occupied the spaces in between water molecules. Now try to understand. Since the solution is saturated, there is no more space left for further solute to be dissolved. There is no more space left for the further solute to be dissolved because all the space have been occupied. Now, for example, since the solution is saturated, in the saturated solution, if you try to introduce one more AB particle, if you are trying to introduce one more AB particle in this particular solution, what is going to happen? See, in the solution already there are A positives and B negatives. Okay. Now, you are introducing in this is a saturated solution right now. There is no space left for the solute to be dissolved. Now still you are introducing one more particle of AB. When you are introducing one more particle of AB, no doubt when this particle goes into the solution, when this extra particle of AB goes into the solution, no doubt it will dissociate into A positive and B negative. But at the same time, the other A positive and B negative in the solution, they will, attract each other and they will form AB, and that AB gets settled at the bottom. That AB gets settled at the bottom. The solution was saturated already. There was no space left. Now still you are introducing one more AB particle. When you introduce one more AB particle, no doubt this AB gets broken down into A positive and B negative, right? But at the same time, in the solution, there were already A positives and B negatives. Now those A positives and B negatives will interact, will form AB, and that AB gets settled at the bottom. So can I say in the saturated solution, AB and its ions, they are in equilibrium? In the saturated solution, if you have got the saturated solution of AB, I would say at that point of time, your AB and its ions, they are present in equilibrium. So if an extra particle of AB goes into the solution, it breaks down into A positive and B negative. If an extra particle of AB goes into the solution, it breaks down into A positive and B negative. But at the same time, other A positive and B negatives in the solution, they react back and they form AB, and that AB gets settled down at the bottom. So remember, in the saturated solution of the solute, in the saturated solution of AB, your AB and its ions, they are present at equilibrium. Is this clear? Is this clear, people? Is this clear? In the saturated solution of the salt, what happens? You can say the salt and its ions, you will always find in equilibrium with each other. Perfect. I believe this is clear. In the saturated solution of salt, what you will find? You will find salt and its ions. They are perfectly in equilibrium with each other. Okay. Now, my dear students, remember one simple thing. Remember one simple thing. What is that? That particular salt whose solubility will be greater than 0.1 molar. That salt whose solubility is greater than 0.1 molar. You'll be calling that salt as the soluble salt. That particular salt whose solubility lies between 0.01 moles per liter to 0.1 mole per liter. You'll be calling that salt as slightly soluble salt. You'll be calling that salt as slightly soluble salt. Similarly, if you will be having a salt whose solubility is less than 0.01 molar, you call that particular salt as sparingly soluble salt. That particular salt whose solubility is less than 0.01 molar, you'll be calling that particular salt as the sparingly soluble salt. And sparingly soluble salts, they are treated as weak electrolytes. They are treated as weak electrolyte. That means a sparingly soluble salt will be in equilibrium with its ions. Sparingly soluble salt will be in equilibrium with its ions. So first of all, we have got, if the solubility of the salt is greater than 0.1 mole per liter, we call the salt as soluble salt. If the solubility of the salt is greater than 0.01 molar, less than 0.1 molar, you call the salt as a slightly soluble salt. If the solubility of the salt is less than 0.1 mole, less than 0.01 molar, the salt is called as the sparingly soluble salt, right? Sparingly soluble salt, and it is treated as the weak electrolyte. And you know, your weak electrolyte, it remains in equilibrium with its ions. Now, let's try to understand few more important things. Say guys, I'm marking the heading here as solubility product. I'm marking the heading here as solubility product. Solubility product, which I'm representing with KSP. Solubility product. This is important. Understand. For example, let's say you have got a saturated solution of a salt AB. Let's say you have got a saturated solution of a salt AB. Okay, saturated solution of the salt AB. So I would say it is going to be in equilibrium with its ions, A positive and B negatives. Okay. Now, my dear students, for example, if I say solubility of this salt is S moles per liter, what does it mean? It means that to make 1 liter of solution saturated, how many moles of salt have been added? 5 moles of AB have been added, right? And when 5 moles of AB are added, that means after that, there'll be no space for further salt to be dissolved. And all these S moles of salt, they would have dissociated into their ions, A positives and B negatives, right? Now have a look. 1 mole gives 1 mole. So from S moles, I would say S moles of A positives would have been generated into the solution. Similarly, S moles of B negatives would have generated into the solution. Okay. Now guys, let's do one thing. Since I've taken the saturated solution of salt AB, right, which is in equilibrium with its ions. Since if I want to write the expression for Ki, ionization constant, since you can see the symbol here, equilibrium sign, right? So I'm writing Ki expression. Ki, ionization constant, is going to be concentration of A positive in the solution at equilibrium raised power 1, concentration of B negative in the solution at equilibrium raised power 1 divided by concentration of AB. Okay? This is, I can write Ki multiplied by concentration of AB is equal to concentration of A positive in the solution at equilibrium multiplied by concentration of B negative in the solution at equilibrium, right? Now guys, AB, it's solid. Active mass of solid is constant. Since this is constant. In place of these two constants, I'm writing one more constant. That is something which you call as KSP. KSP is nothing. Concentration of A positive in the solution at equilibrium raised power stoichiometric coefficient. Concentration of B negative in the solution at equilibrium raised power stoichiometric coefficient, right? And this particular expression, I'll be calling as solubility product expression. I'm calling this as solubility product expression for the salt AB. Okay. Now guys, one more thing. What is the concentration of A positive in the solution? S molar. What is the concentration of B negative in the solution? S molar. S into S makes it S square. So KSP expression here came out to be what? It came out to be S square. It came out to be S square. For example, let's say you have got the salt of the type AB2. Let's say you have got the salt of the type AB2. You have got the saturated solution of the salt AB2. First of all, it is going to remain in equilibrium with its ions. Ions are going to be A di positive aqueous plus 2 times B negative aqueous. Okay, now tell me one thing. If, for example, solubility of this salt is S, right? S moles per liter. S moles per liter. So 1 mole gives 1, S gives S. So concentration of A di positive in the solution will be S moles per liter. 1 gives 2. So from S, I would say 2 S moles per liter of B negative will be there, right? So you got the concentration of ions in the saturated solution. Now, if I want you to write the KSP expression, how do you write the KSP expression? Concentration of ions at equilibrium raised by their stoichiometric coefficients. So I'll write concentration of A di positive. Concentration of A di positive in the solution at equilibrium raised by stoichiometric coefficient. Concentration of B negative in the solution at equilibrium raised by stoichiometric coefficient. So KSP here is going to be equal. What is the concentration of A di positive? S raised by 1 multiplied by. What is the concentration of B negative? 2S raised by stoichiometric coefficient, that's 2. So the expression comes out to be simply 4S cubed. So this is the expression of KSP of the salt which is of the type AB2. AB2. Right? Similarly, guys, let's say you have got the salt of the type, for example, A2B3. Right? So if you have got the saturated solution of this particular salt, so the ions are going to be 2 times A tri positive and 3 times B di negative. First of all, I hope you know how to dissociate the salt. If not, let me show it to you first of all. See guys, first of all, crisscross them. This 3, you can make charge here. This 2, you can make charge here. Number 1. How many A particles are here? 2. Write 2 first. A is present in tri-positive state. Similarly, how many B we have here? 3. And B is present in di-negative state. Perfect. Now, if its solubility is S moles per liter, I'll say concentration of A tri-positive will be 2S moles per liter. And similarly, this will be 3S moles per liter. If you want to write the expression for KSP, you can do that. It's going to be concentration of A tri-positive, raised power stoichiometric coefficient, concentration of B di-negative, raised power stoichiometric coefficient. So KSP has to be equal. What is the concentration of A tri-positive? 2s raised power 2. And this is going to be 3s raised power 3. 3, 3, 9, 3, 27. 27 into 4 is 108. And s raised power 5. This is the expression of KSP for the salt of the type A2B3. Right? Right? Roshan, if you are starting your preparation now, see, first of all, I don't know at which level you are right now. Okay? I don't know at which level you are right now. So I cannot correctly answer this question till you tell me what is the score which you are getting nowadays in the mock test. Okay? Just watch the video that I posted like 2 days back. There I have mentioned every single thing. Okay? Now guys, understand. For example, you have got the salt of the type AXBY, a general salt. Perfect. Now, first of all, what are going to be its ions? In order to draw its ions, this Y will be the charge here. This X is basically the charge here, right? So, how many A particles here? X. X. A is present in which form? Plus Y form. Similarly, how many B here? Y. This B is present in -6 form. Okay. Now, people, if the solubility of this salt is S, concentration of AY positive, if 1 mole gives X moles, so S moles are going to give us X times S moles, right? And this is going to be Y times S. Just using the stoichiometry. Perfect. Now, KSP expression will be equal. Concentration of AY positive, that's X times S, raised power stoichiometric coefficient, that's X. This is Y times S, raised power stoichiometric coefficient, that's Y. I would say KSP value will be equal to X times X multiplied by Y times Y. This is going to be S raised power X plus Y. This is how you write the KSP expression generally for the salt of the type AXBY. Okay? Right? Number 1. This is the first point, guys. This is the first point. Second point. Second point. Try to understand what exactly I'll be saying. Try to understand what exactly I'll be saying. For example, you have got the saturated solution of the salt AB. Okay? So its ions in the solution would be A positive and B negative. How do I make its KSP expression? KSP expression is simply going to be concentration of A positive at equilibrium raised power stoichiometric coefficient 1, concentration of B negative at equilibrium raised power stoichiometric coefficient 1. This is the expression for KSP. This is the expression for KSP. Sir, if a common ion is there, just wait, I'll show that too. Wait. I'm just teaching you the basics right now. See guys, this is how you make the KSP expression. I hope you remember, in chemical equilibrium, I have taught you reaction quotient and equilibrium constant. What was the difference between reaction quotient and equilibrium constant? Reaction quotient expression, that was basically the same type of expression as that of equilibrium constant, which was written at any stage apart from equilibrium. Here, in this expression, I'm taking the concentration of these ions at equilibrium. But if I write the same expression like this, concentration of A positive multiplied by concentration of B negative, not at equilibrium, then I won't be calling it as KSP. I would be calling it as KIP. I would be calling it as KIP. I would be calling it as KIP for the salt. What is the difference between KSP and KIP? Here, the concentrations of ions are taken at equilibrium, right? At equilibrium. Perfect. Here, concentrations of ions are taken at any stage apart from equilibrium. At any stage apart from equilibrium. Now, my dear students, tell me one thing. Can I say if KSP, if KIP of the salt, if KIP of the salt is equal to KSP, if KIP of the salt is equal to KSP, what does that mean? If KIP of the salt is equal to KSP, if KIP of the salt is equal to KSP, do remember, if you remember, when Q is equal to K, when reaction quotient is equal to equilibrium constant, we say reaction is at equilibrium. So, if KIP is equal to KSP, that means this reaction is at equilibrium. If it is at equilibrium, what does that mean? Solution is saturated. But at that time, the solution which we have we call that as the saturated solution. Okay. Similarly, guys, if for example KIP is less than KSP, if KIP is less than KSP, that means solution is unsaturated. It is not saturated yet. If KIP is less than KSP, I would say KIP would want to increase its value to get equal to KSP, right? Like we had Q and K, in chemical equilibrium. If Q is less than K, Q tries to increase its value so that it becomes equal to K, right? If reaction quotient is less than equilibrium constant, reaction quotient tries to increase its value so that it becomes equal to K, so that equilibrium is attained, right? In the similar way, you can remember it over here. If KIP of the salt is less than KSP, that means solution right now is not saturated, it's unsaturated. So in the solution, I would say more salt can be dissolved right now. More salt can be dissolved. More salt can be dissolved because the solution is not saturated yet. Okay? The solution is not saturated yet. Perfect? And similarly, if KIP value is greater than KSP, guys, you can remember it like this. You can remember it like this. KIP always wants to get equal to KSP. KIP always wants to get equal to KSP. Now, if KIP is less than KSP, that means KIP has to increase its value so that it becomes equal to KSP. How will KIP increase its value? KIP can increase only its value if concentration of A positive and B negative will increase. How will concentration of A positive and B negative will increase? How will concentration of A positive and B negative increases? Concentration of A positive, B negative increases if this reaction shifts forward, right? This reaction shifts forward means more salt will get dissolved. More salt is getting dissolved. Now, similarly, if KIP is greater than KSP, KIP would want to decrease its value so that it becomes equal to KSP. How would KIP decrease its value? KIP would decrease its value when these particular terms will decrease. How will these particular terms decrease? These particular terms, that means concentration of A positive, B negative will decrease only if the reaction shifts backward. And when the reaction shifts backward, that means in the solution A positives and B negatives are interacting, forming AB, and that AB is settling down at the bottom. So can I say this is the case of precipitate formation? Over here, precipitate formation takes place. And you will be calling this particular solution as the supersaturated solution. Sometimes a question is asked from this particular part as well, whether precipitate formation takes place or not, right? Whether the solution is supersaturated or not. You just have to check the value of KIP. If KIP is greater than KSP, that means precipitate formation will take place. Okay? In short, remember it like this. KIP always wants to become equal to KSP. If KIP is less than KSP, so KIP has to increase its value. If KIP is more than KSP, then KIP has to decrease its value, right? Perfect. Now, let's try to solve some questions so that you'll understand what all types of questions are asked here. See guys, this is the first and the basic question which we have. KSP for MgOH hold twice. We are given with MgOH hold twice. First of all, how would this MgOH hold twice have undergone dissociation? It would have undergone dissociation as Mg di positive aqueous plus 2 times OH negative aqueous. As per the question, solubility product of MgOH hold twice is given. We need to calculate its solubility in water. We need to calculate solubility of MgOH hold twice in water. Let's say its solubility is S. So this has to be S. This has to be 2S moles per liter. If you want to write the expression for KSP expression for MgOH hold twice will be concentration of Mg di positive, that's S raised power 1. Concentration of OH negative, 2S raised power 2. 2S raised power 2. The value comes out to be 4S cube. So I can say, since your KSP is equal to 4S cube, therefore S will be equal to KSP divided by 4 whole raised power what? Whole raised power 1 by 3. Now KSP value is given to me as per the question. That is 3.2 into 10 raised power. Guys, change it. It's not 14, it's 10 raised power minus 14. Okay? Just change it here. 10 raised power minus 14 divided by 4. Whole raised power what? 1 by 3. This is going to be 0.8 into 10 raised power minus 14 whole raised power 1 by 3, which can be written as 8 into 10 raised power minus 15 whole raised power 1 by 3. 8 raised power 1 by 3 means 2, right? 10 raised power minus 15 raised power 1 by 3. It's 10 raised power minus 5 moles per liter. So what is this particular term? This is the solubility of MgOH whole twice in water that we have calculated, right? Perfect. This is the solubility of MgOH whole twice in water that we have calculated. That means in order to make 1 liter of solution saturated, how many moles of magnesium hydroxide we have to add? 2 into 10 raised power minus 5 moles of magnesium hydroxide are to be added in order to make 1 liter of solution saturated. Okay? I hope this is clear. This was the first and the basic type of the question. Similarly, second. Remember guys, this mercurous chloride, Hg2Cl2. Okay, mercurous chloride. Remember this. This mercurous chloride, remember its dissociation. It does not dissociate normally like all the other electrolytes dissociate. It dissociates in this form. Hg2 di positive. Mercurous chloride dissociates in this form. Hg2 di positive plus 2 times Cl negative. Remember this particular case. Remember this particular case. Mercurous chloride, it does not undergo normal dissociation like all the other electrolytes do. It dissociates in the special way as Hg2 di positive with 2 times Cl negative. Now what are we supposed to calculate? Calculate the solubility of mercurous chloride in water, right? If it is Ksp, is this. Ksp is given. We need to calculate solubility of mercurous chloride in water. Let's say its solubility is S. If it is solubility is S moles per liter, or you can directly say S molar, right? So 1 gives 1, so S gives S. 1 gives 2, so S gives 2 times S. Perfect. Now you can just write the expression of Ksp over here. Ksp expression is concentration of this, that's S, raised power stoichiometric coefficient, that's 1, multiplied by concentration of Cl negative, that's 2 times S, raised power stoichiometric coefficient 2, so it comes out to be 4S cube. I would say S is again equal to Ksp divided by 4 whole raised power what? Whole raised power 1 by 3. Correct? What is Ksp value? It is 10.8 into 10 raised power. Change it guys, this is not 23, this minus 23, okay? Just change it. This is not 23 here, this 10 raised power minus 23 divided by 4 whole raised power 1 by 3. It comes out to be equal to. It comes out to be equal to. This is 27. Is this 27? 2.7, right? 2.7, which can be written as 27 into 10 raised power minus 24 whole raised power 1 by 3. So it comes out to be 3 into 10 raised power minus 8 moles per liter. So this is the solubility of mercurous chloride in water, which I was supposed to calculate. I hope I'm clear with this. And let's move on to one more question. Let's move on to one more question. Calculate the solubility of silver phosphate in mg per ml. Let's make the question a bit simple. Let's calculate all the stuff in moles per liter, okay? Okay. See guys, calculate the solubility of silver phosphate in moles per liter. Number 1, in pure water, we have to calculate solubility of silver phosphate in pure water first. Then we have to calculate solubility of same silver phosphate in a solution that contains 0.02 molar AgNO3. These are two different questions, guys. These are two different questions which we have to solve. And how exactly are we going to solve them? See, let's solve the first question. Ag3PO4 in water. How will it undergo dissociation? 3 times Ag positive aqueous. And with this, we'll be having PO4 tri-negative aqueous. First question is simple. Let's say its solubility is S molar. This will be 3 times S. This will be S molar, right? Okay. Now, if you want to write the expression of Ksp, or let me write it somewhere here. Expression for Ksp is equal to what? Expression for Ksp will be equal to concentration of Ag positive raised power 3. So 3S raised power 3 multiplied by S raised power 1. So Ksp value as per the question is 2.7 into 10 raised power minus 23 is equal. This is going to be 27 S raised power 4. S value here will be simply 2.7 into 10 raised power minus 23 divided by what? Divided by 27. And it's going to be now in moles per liter. This is basically the solubility of silver phosphate in water. This is the solubility of silver phosphate in water. So the question is done right now. The first question is done. Look at the second question. Look at the second question. Now we have to calculate the solubility of same silver phosphate in 0.02 molar AgNO3. This was solubility of Ag3PO4 in water. Now, solubility of same Ag3PO4 in what? Not in water now, in AgNO3. Now, for example, you have got a container which already had AgNO3 into it. And AgNO3, it is a salt of NO3 negative. And you know salts of NO3 negatives are water soluble. And they are considered to be what? All the water soluble salts are considered to be strong electrolytes. So this AgNO3 would have got dissociated completely into its ions, Ag positives and NO3 negatives, right? What is the concentration of AgNO3? It is 0.02 molar. So in the beginning, this would be 0, this would be 0. Now this would be 0, this would be 0.02, and this would be 0.02 molar. So basically, if you look carefully, now we have introduced Ag3PO4 in what? Not in water. We have introduced this in AgNO3 solution. Okay? We have introduced it in AgNO3 solution. Okay, we have introduced it in AgNO3 solution. Now, my dear students, do you see one thing? Do you see one thing? Equilibrium? Over here, no, right? So this is basically your weak electrolyte. This is a strong electrolyte. So do you see? You have got weak electrolyte and strong electrolyte present in the same container, and they have got one ion in common, Ag positive, right? So what should be the concentration of the common ion? 3s plus 0.02. So we have got weak electrolyte, strong electrolyte present in the same container, having one ion in common. So which effect is going to operate here? Common ion effect. Due to common ion effect, what happens? Due to common ion effect, what happens? This particular reaction shifts backward. If it is shifting backward, that means solubility of the salt is decreasing. Solubility of the salt is decreasing. Already the solubility of the salt was very low. Now solubility of salt would have further decreased. So you can neglect S wherever you want. So instead of all this, you can just write 0.02. Okay, you can just write 0.02. Now, my dear students, one thing. Since already we know the KSP value. Since already we know the KSP value, right? Since already we know the KSP value. Now, in this particular question, I would want you guys to write the expression of KSP again. Expression of KSP is going to be Ag positive raised power 3 multiplied by PO4 tri-negative raised power 1. What is the KSP value? 2.7 into 10 raised power minus 23. What is the concentration of Ag positive now? Now it is 0.02. 0.02 raised power 3. What is the concentration of PO4 tri-negative now? It is S raised power 1. So from here, you can easily get the value of S. And this S now I'll be calling as solubility of Ag3PO4, not in water. It is going to be the solubility of Ag3PO4 in what? In AgNO3, right? So which effect we have operated here? We have used the common ion effect here. Okay? Right, guys? KSP already we know. See, KSP of a salt, it has always a fixed value, right? It is already a fixed value. That's why KSP of Ag3PO4 in water and KSP of Ag3PO4 in AgNO3. In both the cases, I have taken the same value of KSP here. I believe I'm clear with this. Let's solve one more question so that it becomes like properly clear to you. If you look at this particular question, the solubility of Ag2CO3 in water. Solubility of Ag2CO3 in water is given. So from there you can calculate KSP of Ag2CO3. What is its solubility in 0.01 molar solution Ne2CO3? So first of all, if you talk about Ag2CO3 in water, it's going to dissociate as 2 times Ag positive aqueous. And with this you have got CO3 dinegative aqueous, right? CO3 dinegative aqueous. So as per the question right now, the solubility of Ag2CO3 in water, if this is S, this will be 2 times S, this will be S. Solubility of Ag2CO3 in water is given to me as 1 into 10 raised power minus 4. So right now only I can calculate its KSP value. KSP is going to be concentration of Ag positive, that is 2S raised power 2, which becomes 2S raised power square multiplied by S. So it's going to be 4S cube. So S you can calculate right now itself. Not S. You can calculate KSP over here as 4 into S. S is the solubility of Ag2CO3 in water, which is 10 raised power minus 4 ka square. 10 raised power minus 4 ka cube, sorry. So KSP of Ag2CO3 is equal to 4 into 10 raised power minus 12. This is the Ksp of Ag2CO3 everywhere. Be it in water, be it in some other solvent, Ksp is always fixed. Okay, it's always constant. Now, as per the question, what are we supposed to calculate? We are supposed to calculate the solubility of Ag2CO3, not in water. We are supposed to calculate it in Na2CO3. Now, tell me, Na2CO3 means this is 2 times Na positive plus CO3 dinegative. Its concentration we have kept as 0.01 molar. So in the beginning, this would be 0, this would be 0. Now this is 0. This would be 0.02 because 1 mole gives 2 moles. This would be 0.01 molar. Tell me one thing. Can I say in the same container, we have got a weak electrolyte and a strong electrolyte. Both are having one ion in common. Which is that? That is CO3 dinegative. So technically, the total concentration of CO3 dinegative has to be S plus 0.01. But since due to common ion effect, this reaction would shift backwards, due to which solubility of Ag2CO3 would decrease. So wherever you would want to neglect S, you can do that. So instead of S plus 0.01, you can just write 0.01 molar. Right? Now, do one thing. Write the expression of Ksp again. Expression of Ksp of Ag2CO3 is nothing but it is concentration of Ag positive raised power 2 multiplied by concentration of CO3 dinegative raised power 1. It is equal to 4 into 10 raised power minus 12. What is the concentration of Ag positive now? It is 2 times S raised power 2. What is the concentration of CO3 dinegative now? It is 0.01 means 10 raised power minus 2 is equal to 4 into 10 raised power minus 12, right? So it is 4S square is equal to 4 into 10 raised power. This will be minus 10, right? So 4 cancels out. S comes out to be 10 raised power minus 5, but it's now going to be moles per liter. So this is basically the solubility of Ag2CO3 in what? In Na2CO3, right? Perfect. You can see also, what was the solubility of Ag2CO3 in water? 10 raised power minus 4. What is the solubility of same Ag2CO3 in this particular Na2CO3? 10 raised power minus 5. Initially it was 10 raised power minus 4. Now it's 10 raised power minus 5. That means solubility has decreased. Due to what? Due to common ion effect. Due to common ion effect. Right? Due to common ion effect, alpha used to decrease. Instead of alpha, I'm using the term here as S, solubility. Right? I'm introducing a term S here. I hope this is clear. Similarly, guys, if you look at this particular question, I think you should be able to solve this one as well. Calculate the solubility of FeOH whole twice in a buffer solution. pH 6.5. Right? Ksp of FeOH whole twice is given. So first of all, if you talk about FeOH whole twice, can you let me know how it would have undergone dissociation? It would have undergone dissociation as Fe di positive aqueous plus what? Plus 2 times OH negative aqueous. Let's say its solubility was S molar. This would have been S molar. This would have been 2S molar. Correct? Right? Now we have to calculate solubility of FeOH whole twice. In what? In a buffer. Whose pH is given? In a buffer. Whose pH is given? pH is 6.5. That means pOH would be 7.5. If pOH is 7.5, that means in the buffer OH negative concentration would be 10 raised power minus 7.5 molar. Already in the solution, OH negative concentration was 10 raised power minus 7 moles, 10 raised power minus 7.5, right? Now we have introduced FeOH whole twice in that, right? So what will be the total OH negative concentration? Total OH negative concentration will be 2S plus 10 raised power minus 7.5, right? Now, due to the common ion effect, again, this would have gone back. Perfect. Or let me not use the term here. Let me directly do it like this. See, you got the OH negative concentration in the solution. Since you got the OH negative concentration in the solution, so if you want to write the Ksp expression now, Ksp expression is simply going to be Fe di positive raised power 1 and OH negative concentration raised power 2, right? Ksp is given to me as 8 into 10 raised power minus 16. Fe di positive concentration is S, right? OH negative concentration already I know. That's 10 raised power minus 7.5. Minus 7.5 because square is 10 raised power minus 15. So S value here would come out to be 8 into 10 raised power minus 1, which comes out to be 0.8 moles per liter. This is simply the solubility of what? FeOH whole twice in a buffer which has got the pH of 6.5, right? This sort of a question, again, you should be able to solve on your own from now on. And I hope this is clear to everyone. Perfect, guys. Is it clear? Is it clear? Can you let me know once in the chats? I just want to show you one more question. Or let me give you this question as the homework. This particular question, I'm mentioning it over here. Will there be PPT, precipitate formation? Will there be precipitate formation in a solution? In a solution that has 2.5 into 10 raised power minus 3 molar MgCl2 and has a pH of 10, given that Ksp of MgOH whole twice is equal to 1.8 into 10 raised power minus 11. Can you give this question a try on your own? Can you give this question a try on your own? Sorry. Will there be precipitate formation in a solution that has 2.5 into 10 raised power minus 3 molar MgCl2 and as the pH of 10, Ksp is given. So basically you have to calculate Kip value, right? If Kip comes out to be greater than Ksp, then there will be precipitate formation. So first of all, Ksp of MgOH whole twice is given. See guys. So how this MgOH whole twice would have undergone dissociation? Mg di positive plus 2 times OH negative. You know it, right? Perfect. Now, solution has got the pH of 10. That means pOH would be 4. So I would say OH negative concentration would be 10 raised power minus 4. This is the OH negative concentration. Okay, right? This MgOH whole twice is present in what? Will there be precipitate formation in a solution that has MgCl2? So already in the container there was MgCl2, which would have dissociated as Mg di positive plus 2 times Cl negative. Then its solubility was S, this was 2 times S, right? MgCl2, its concentration I have kept as 2.5 into 10 raised power minus 3. So initially 0, 0, now this is 0. This is 2.5 into 10 raised power minus 3. This will be 2 times. So it will be 5 into 10 raised power minus 3 molar, right? So in the same container, do you see, again common ion effect is going to operate? Weak, strong, both having 1 in common, right? So total will be 2.5 into 10 raised power minus 3 plus S. And instead of all this, I'll be just writing 2.5 into 10 raised power minus 3 only. Because S I can neglect here. S I can neglect here. Now, for this MgOH whole twice, I already know its Ksp value. Now, I want to calculate its Kip. Kip of MgOH whole twice in this particular solution. Its Kip is simply going to be concentration of Mg di positive raised power 1, concentration of OH negative raised power 2. Now, Kip will be, what is the concentration of Mg di positive? 2.5 into 10 raised power minus 3. OH negative concentration already we know, that's 10 raised power minus 4. So the value comes out to be 2.5 into 10 raised power minus 7. So look at Kip and look at Ksp. Just a second, this will be 10 raised power minus 4 ka square, 10 raised power minus 8. So it is coming out to be 10 raised power minus 11. So 2.5 into 10 raised power minus 11, that's Kip. 1.8 into 10 raised power minus 11, that's Ksp. So I would say Kip is greater than Ksp. If Kip is greater than Ksp, will there be precipitate formation? Yes, there will be precipitate formation. Yes, there will be precipitate formation. Got it? This sort of a question can be asked too, wherein you have to check whether precipitate will get formed or not. Okay. Now guys, there is one small topic left, that is what you call a simultaneous solubility, right? One small topic. It's not going to take more than 10 to 15 minutes. Simultaneous solubility. For example, let's say you have got the same container. In the same container, you have introduced two salts, AB, AC, right? Two salts are there in the same container. I'm writing a term here, X moles per liter. Here I'm writing Y moles per liter. What is meant by X and Y over here? X is something which I call as solubility of AB in presence of AC, right? Similarly, Y I'm calling as solubility of AC in presence of what? In presence of AB, right? Solubility of AB in presence of AC. Similarly, solubility of AC in presence of AB, right? Hi, sir, I got admission because of you. Congratulations, that's great. Which college? Tell me, which college? Now, guys, have a look. 1 gives 1, so X moles are going to give me X moles per liter. So this is X, this would be X. If this is Y, this would be Y, this would be Y. Now, do you see any common ion in between? A positive, A positive. So I would say concentration, total concentration of A positive would be X plus Y. And here you would be adding X, right? Total concentration of A positive in the solution would be X plus Y, here also X plus Y, okay? Now, my dear students, if I ask you to write KSP for the salt AB, KSP for the salt AB is going to be concentration of A positive, that's X plus Y raised power 1, concentration of B negative, that's X raised power 1. If I ask you to write KSP for this particular salt, or the second salt, it's going to be again X plus Y multiplied by what? Multiplied by Y. So how many equations I got here? Got two equations. If I divide the two equations, I'll be writing KSP1 divided by KSP2. KSP1 divided by KSP2 is nothing but X by Y. This is one of the equations. Similarly, if I add these two equations, what I'll be getting? I'll be getting KSP of 1 plus KSP of 2 is equal to, so this plus this, if I take X plus Y common, so it's going to be X plus Y ka square. X plus Y ka square. So from here, you can say X plus Y is nothing but under root of KSP of 1 plus KSP of 2. So how many equations we got? We got two equations. Equation number 1, equation number 2. Two equations we got. Two equations, right? Two equations. If we got two equations, whatever things we are supposed to calculate in the question, we can do that. We can do that. For example, our first point is you should be in a position to make these two equations. And I hope you got to know how did I make these two equations. Now, from these two equations, anything, whatever thing is asked in the question, that can be solved. How exactly? For that, I'll be writing a question and you'll understand what exactly am I talking about. See, guys, a mixture of SrSO4 and BaSO4 is shaken with water until equilibrium is established. KSP for both is given. Calculate the concentration of each ion at equilibrium. This might be a bit lengthy question. Let's see. So first of all, you have taken strontium sulfate and you have taken barium sulfate in the same container, right? In the same container. So this would have dissociated as strontium dipositive aqueous plus what? Plus SO4 dinegative aqueous. This would have dissociated as barium dipositive aqueous plus what? Plus SO4 dinegative aqueous. Okay. Let's say the solubility of this strontium sulfate in presence of this is X and this is Y, right? Like I told you a few minutes back. X is the solubility of strontium sulfate in presence of barium sulfate. Y is the solubility of barium sulfate in presence of strontium sulfate. If this is X, this has to be X, this has to be X. If this is Y, this has to be Y, this has to be Y. Common ion is your SO4 dinegative. So add Y here, add X here because they are present in the same container. So this is something which is happening in the same container, right? Now, you know, KSP1 divided by KSP2. KSP1 divided by KSP2 has to be equal to what? X by Y? Is that? Let's check it out too. What is KSP1? What is KSP1 equal? Let's get it in detail. KSP1 is equal to concentration of Sr dipositive X and this is going to be X plus Y, right? Similarly, KSP2 is going to be Y multiplied by X plus Y again. So two equations. So if I'll be dividing them, so KSP1 divided by KSP2 is going to be equal to X by Y, number one. Number two, If I add them up, KSP1 plus KSP2 would be equal to x plus y ka square. So root and this x plus y, right? So I got two equations. Now guys, what am I supposed to calculate? Concentration of each ion. Concentration of each ion. So basically, I need to calculate the value of x and y first. How do I get the value of x and y? See, KSP of 1 is given. KSP of strontium sulfate is how much? 7.5 into 10 raised power minus 7. KSP of 2. KSP of barium sulfate is 6 into 10 raised power minus 8 is equal to x divided by y. Is equal to x divided by y. In the similar way, under root of. See, under root of KSP1. KSP1 is how much? 7.5 into 10 raised power minus 7. Can I write it as 75 into 10 raised power minus 8? Yes. Plus KSP2, 6 into 10 raised power minus 8. 6 into 10 raised power minus 8 is equal to what? X plus y. So if I take 10 raised power minus 8 as common, 75 plus 6 comes out to be 81. So 81 into 10 raised power minus 8 is equal to x plus y. Or I can say x plus y is equal, right? 9 ka square is 81, 9 9s are 81. So 9 into 10 raised power minus 4. X plus y is equal to 9 into 10 raised power minus 4, correct? Now you can eliminate x over here. X will be equal to, x would be equal to 75 into 10 raised power minus 8 divided by 6 into 10 raised power minus 8 into y. So 10 power minus 8, 10 power minus 8 cancel. So I would say x is equal to 75 by 6 into y. Put this value of x in this particular equation. X would be written as 75 divided by 6y plus y is equal to 9 into 10 raised power minus 4. So this is 81y divided by 6 is equal to 9 into 10 raised power minus 4. This is 9199. So I would say 9y is equal to 6 into 10 raised power minus 4. Y would be equal to 6 by 9. So 3233. So 2 by 3. 2 by 3 is 1.5. 1.5 into 10 raised power minus 4. So this is the value of y. If you got the value of y, you can easily get the value of x. What is the value of x? X value is nothing but it is 75 divided by 6 multiplied by y. It is 75 divided by 6 multiplied by what is y value? Y is 1.5 into 10 raised power minus 4 moles per liter, right? So I got the value of x, I got the value of y. If you got the value of x and y, what was I supposed to calculate? Concentration of each ion. X you got, y you got. X plus y also you got, right? X plus y also you got. That's 9 into 10 raised power minus 4, right? 9 into 10 raised power minus 4. X you got, y you got. So all the things we calculated in detail, right? I might, did I do some calculation mistake here? You can check it out afterwards. 0.6, not 1.5. Where did I mention 0.6? Where did I mention 0.6? So first of all, I was supposed to calculate the concentration of each ion. Concentration of SO4 dinegative is x plus y. X plus y here only we calculated. 9 into 10 raised power minus 4. The concentration of sulfate is over, right? Okay, this is 6 by 9. 6 by 9 means 2 by 3, right? 3, 2, 3, 2 by 3. So just modify the calculation a bit. This is 2 by 3. Y is 2 by 3 into 10 raised power minus 4. So y is 2 by 3 into 10 raised power minus 4. Right? You can check it out now. Anyways, you can have a look on the calculation afterwards too. Sir, you have written 7.5 into 10 raised power minus 8. Where? This is not 7.5. This is 75 into 10 raised power minus 8. Earlier it was 7.5 into 10 raised power minus 7. Here I have mentioned 75 into 10 raised power minus 8. It's correct only. Okay, let me check all the things again. So 75 into 10 raised power minus 8. 10 power minus 8, 10 power minus 8 cancel. So x is equal to 75 by 6 into y. Put the value of x here. 75 divided by 6 into y plus y is equal to this. So this will be 81y by 6, 9199. So 9y is equal to 6 into 10 raised power minus 4. Y is equal to 6 by 9. So 2 by 3 into 10 raised power minus 4. Put the value of y here. Y is basically, put the value of y where exactly? Since x is equal to this by this into y, x is equal to 75 divided by 6 into y, and y value I've introduced here. Yes, it's correct. All the things are correct. Okay, and my dear students, with this, the chapter Ionic Equilibrium is done and dusted. I've taught you this particular chapter in the most detailed manner. Okay, this much detailed I've never taught this particular chapter on YouTube. At least this is the first time I've taught this particular chapter on YouTube in the detailed manner. Okay, perfect. So when I end the session, do let me know in the comment section whether you got all the things properly, and I would expect comment from every single one watching me right. Okay, in the comment section, not here. In the comment section, I would want you guys to let me know whether you got all the things clearly, all the things properly, right? Okay, do let me know in the comment section. Hello, guys.